Good morning and welcome everybody to this morning's workshop on dexterity and multi-fingered hands. My name is Kevin Lynch. I'm a professor at Northwestern University. It's my pleasure to welcome you here today. We've got a big lineup for you. There's a QR code here if you want to add to the conversation in real time. I'm going to show it again at the end of these slides, so if you don't get a picture of it now, it'll come up again later. But we do encourage you to interact with our distinguished set of speakers and panelists today. We want this to be an interactive session so we can all learn from each other. So it's my pleasure to begin the workshop by introducing the people who did all the work behind it, because it was a lot of work. And those are Shuran Li, Michael Gorner, Ken Shah, Haoji Chi, Shihan Liu, Kevin Zhang, Arjun Lakshmipati, Jalil Nasiri, and Abdullah Sukir. So thank you guys. They did all the real work, organizing the industry session, the spotlights, reviewing the abstracts, putting together the program, inviting speakers. So thank you very much to them. Please join me in a round of applause. And also the people who didn't do much work, but were there to help as we could. The advisory board, thank you to the advisory board as well. These are the sponsors of this workshop. Various universities contributed their time and their talent. And in two cases, Franco Robotics and Agile Robots actually contributing funding to this workshop. 3 of our best posters will receive an award later today, winning $500, and we thank our sponsors very much for that. So we're here today to talk about dexterity and manipulation. And this is not a new topic in robotics. So I'll just use as one example this multi-fingered hand from the early 80s in this work on understanding the mechanics of manipulation, published in this mid-80s book. Right? So this has been a foundational subfield of robotics from the very beginning. But many of us would argue that progress in dexterity and manipulation has been slow. And perhaps compared to some of the flashier fields of robotics where in flying robots and drones and walking robots, running robots, locomotion, it seems like dexterity has proceeded slowly. I think one of the issues is that we have so many problems that fall into manipulation and dexterity, right? Every sort of, complex, multi-contact situation where we're doing force control or impedance control or motion control and we're trying to change the state of the world, all of those can be classified as manipulation problems. So apart from thinking about maybe where to put our fingers to achieve a grasp, the field has really been spread out into lots of different individual research directions, and the funding traditionally has been modest. Well, that's starting to change, and one of the big drivers of the change is artificial intelligence. Because I think increasingly we recognize that where artificial intelligence turns into useful physical work performed on the world, when we get it outside of its digital existence, in large part is happening through the hands. Right? This is where AI gets expressed as useful physical work. So now we're starting to see greater and greater investments. I want to call out this one by our colleagues in the UK. This program is called Aria, just launched this year, investing £57 million over the next 5 years to take a step forward in robotic dexterity. So the UK is investing heavily. The US National Science Foundation, just within the past year, funded a research project, an engineering research center for up to $52 million in 10 years to revolutionize dexterity of robot hands. And as part of this, many companies are getting involved in the project. They're joining us in our consortium called HAND, and as well as center partners, nonprofits who are interested in advancing the state of robot dexterity. So lots of investments, some by governments and some private. So here's a lineup of humanoids, and if you go to the exhibit here during the conference, you're going to see lots and lots of the humanoids. This is just one of the examples, or just a few of the examples. These humanoids, by and large, have hands, and those hands need to do something useful. So all of the hundreds of millions and billions of dollars in investment in humanoids has an interest in what the sorts of problems are that we are addressing here today. Things like tactile sensing, highly dexterous motion control, learning and artificial intelligence for our hands, haptic interfaces, user interfaces to make those hands easier to program, advanced simulation so that we can do things like sim to real with many contacts in soft and hard materials. So there's a lot of investment both by governments and private companies in trying to push dexterity forward, and that's the topic for today. And so we're very fortunate today to have a really distinguished group of people here. And by the numbers, we've got 24 accepted abstracts, so thank you to those of you who submitted your work to this workshop, and we'll have a chance to present it out at the poster session, and we'll have 2 of those. We have 9 invited speakers who will be presenting the latest work from academia and industry. 8 of the posters will have abstract spotlights, so we'll come up here and tell you for a few minutes about what their poster is about. We have 7 industry session speakers who will tell you what their companies are doing to drive dexterity forward. And we also have 4 startup spotlights. So in total, 11 companies will come up here and tell you what they're working on. So it'll give you a good broad cross-section of the state of the art, both in academia and industry. And then finally, we're going to have a chance through 2 panels to talk to our invited speakers up here and ask them questions, the things that are most on your mind. This is an eye chart, but this is our schedule for today. We have a block of 3 speakers, starting with Professor Shuran here. Then we'll move on to spotlight presentations of the posters and accepted abstracts. Then we'll have the poster session and coffee break right outside. 2 more invited speakers followed by a panel, so they have a chance to talk to those invited speakers. So if you have a question for them and you don't get to it, the talks will generally be about 20 minutes to 5 minutes for Q&A. If we don't get to your question, the panel will be a great way to delve further. Lunch, 2 more speakers after lunch, then an industry session. So that's when we'll have our 7 companies and our 4 startups come up here and tell you about what they're working on. And then you'll have a chance later, perhaps at one of the tables here or outside at the poster session, to talk to them in more detail. 2 more invited speakers, followed by a panel discussion, and then the awards for best paper, best abstract, best poster, I should say. So with that, I'm going to turn it over to Kenny here, one of my co-organizers, and let him introduce the first speaker. There's the QR code if you want to join the document for live Q&A, and I'll turn it over to Kenny.
Great, thanks Kevin for the great introduction. So our first speaker is Shuran. Shuran's an assistant professor at Stanford University. She leads the REAL lab, the Robotics and Body AI lab, where her research focuses on developing algorithms that enable intelligent systems to learn from physical interaction. Her papers have won many awards and have been very popular, such as most recently the Best System Paper at RSS 2024, which is Yumi, and also Best Paper Award and Best System Paper Award at RSS 2022, and many other awards. Very excited to have Shuran here. Thank you.
Thank you. Okay, hello everyone. Good morning. Thank you for waking up so early to attend this talk. This is the very first talk for the whole conference. I'm so glad you're here. Okay, so today I'm going to talk about cross-embodiment learning for dexterous manipulation. So first, let me just quickly define what do I mean by cross-embodiment, the cross-embodiment problem in the context of dexterous manipulation. So in my mind, I think the cross-embodiment problem is really a multi-layered problem. So in the first layer, the first cross-embodiment problem is the embodiment gap between the human hands and also the various robot hands that you are designing. So despite all the hardware developments in the recent years, we still have a long way to go to achieve the same level of capacities of a human hand in terms of the hardware capabilities. Right? So, and also at the same time, I think it's also debatable whether we really need our robot hardware to match exactly like the human hand. So because of that, there will always be embodiment gap between the human hand and also the robot hand. And because of this, limitation or the hardware constraints, different companies, when they're designing their own robot hands, they actually often try to choose different trade-offs and then which lead to different designs in their hardware. So as a result, you will see such a diverse designs of dexterous hand, multi-finger hand in the market right now, and each of them is slightly different. Like they have different degree of freedoms, different sizes, different strengths and limitations. So as a result, it is quite important for us to have a system or a method that is able to actually handle this robot-to-robot embodiment gap, right? So we have so many different hands. It would be just nice if we have like one algorithm that's able to like control all of them. So today I'm actually going to talk about two slightly different strategies of handling this cross-embodiment problem in dexterous manipulation. The first strategy is that let's try to reduce the embodiment gap as much as possible. In particular, try to reduce the embodiment gap between the human and the robot by thinking carefully about how we designed the data collection interface so that the data collected by the human can be easily transferred for the robot hardware that you care about. And another slightly different strategy is actually try to, instead of making them the same, let's just try to represent the difference, right? So in your algorithm, your policy development, can we represent the hardware design in your policy formulation so that the policy is hardware aware or like embodiment aware and is able to infer different actions or different strategies for different embodiments. And today I'm going to talk a little bit about each of the directions. So first, let's try to reduce the embodiment gap with smart interface design. So this is a question for you guys. Looking at this video, can you think about what makes it hard for robots or AI system to learn from a video like this? Yeah? Occlusions? Yes. Any other thoughts?
No idea how much force was applied.
Yeah. So there are actually like two different levels of issues from learning from a video like this. The first is that human hands is actually way too dexterous for our robots today, right? So there's many strategies that you're seeing here, like how they crack the egg. It actually cannot be realized by our robot today. The hardware it does not have that capability. And the second problem is actually what you guys mentioned, is the information is not sufficient. Right, so either it is you cannot extract the joint angles from this video because of visual occlusions, or you don't know the force information from this video. So there's just like a lot of partial information from a video like this, making it difficult to learn from just like a human hand demonstration. So the key idea for bridging this embodiment gap actually just basically try to address these two problems. One is let's try to constrain the human dexterity or human action so that you can transfer those actions to the robot. And the second idea is let's try our best to record the sufficient information for policy learning. Right? So these 2 points are very important. It's going to come back again and again. So our first attempt trying to realize these principles in our design for data collection interface is this UMI. It's called Universal Manipulation Interface. So as you can see, UMI is basically a handheld gripper that you can hold to collect training data for your robot. So how we actually realize these two ideas? First of all, you basically just force the human to use the same robot gripper as your robot so that there is zero embodiment gap, at least on the manufacturer perspective. And then for the second point, to record sufficient information, we basically mount a GoPro camera on the wrist of the gripper so that it can record the visual observations so that you can use that to train your robot policy. Right? At the same time, you can track the camera motion in 3D so that it gets you the action trajectories that you need. And then you can also track the gripper openings on the image directly to give you the gripper width. So all those are actually the detailed information you need to train a policy. And also we use the fisheye camera to encode enough visual context for your policy to infer what kind of action to extract. And also from this wristband camera, this is actually a pretty smart design so that from this view, there's almost no embodiment gap because you don't really see the arms and the robot body. So this is also help to reduce embodiment gap. So in the end of the day, you can actually use this gripper to do human demonstrations in almost any environment because it's a very portable handheld gripper. And you can actually demonstrate many different tasks, including very challenging ones like dynamic tossing or by manual folding laundries, or like the earlier like dishwashing tasks that you can just whatever task you care about, you pretty much can use this gripper to demonstrate. And then the robot will be able to learn from those data. And what even better is that with this gripper, you actually can transfer the same policy to different robot embodiments, including robot arms, or like later we actually show that you can actually transfer the same policy to a mobile quadruped robot, as long as you have a parallel gripper and a wrist mount camera. Okay, so that's UMI. So what's the limitation for UMI? I think for this audience, it's actually quite obvious, right? For UMI, you actually limit the robot's capability to just a parallel gripper. And then I think for this workshop, that's really not satisfactory. This is not the level of dexterity that we want to see, like at least in the ultimate form of robot manipulation. So because of that, soon after we release UMI, we start working on a follow-up project that's trying to develop a version of UMI that is able to work with multi-finger dexterous hands. And this project is led by my students Handa and also Han. Also, by the way, Handa is on the market looking for postdoc positions, so if you're interested, reach out to him. Okay, so for Dex UMI, we actually still follow the same two ideas or principles when we're designing the interface. First, constrain the human action for transferability, and second, try to record the sufficient information. And let's look at these two ideas one by one. First, in order to constrain the human action, even with using multi-finger hands, is that we want to actually design the a wearable actual skeleton. In the hardware, we try to limit the movement or the joint range to match the target robot hands that you have. Right? So for example, if your robot hand cannot move the fingers side by side, this actual skeleton that the human gonna wear also cannot move side by side. So this really helps to limit the type of action the demonstrator can perform, so that the data that you collected on this actual skeleton is guaranteed to be transferable to the robot hands that you have. Right, so this actual skeleton is actually designed hand by hand, depends on the robot hardware you have. And then in order to record the sufficient information, we actually add additional joint encoders for each of the joints to record those precise joint space actions in order so that you can do one-to-one mapping from the joint space action to your robot motor command. And then because of that, you no longer need to do these retargeting algorithms on top of the data that you collected, because you actually calibrate the motor and the joint encoder so that you can directly get the precise action, joint space action that you need to train the policy. Right, so in our experience, this kind of joint encoder data captured is actually oftentimes a lot more precise than other tracking methods, for example, vision-based methods, because it does not suffer from occlusions, for example. So that gives you the joint space actions. And then also similar to UMI, you can actually wear this actual skeleton to directly collect demonstration data for the task you care about. Right? So this is actually very beneficial, like the ability to wear this device to collect data instead of teleoperating, because this can give you this kind of in contact, like direct haptic feedback when you are manipulating objects. And that is actually part of the reason why people feel like UMI type of data collection interface is more intuitive than, for example, teleoperation. Right? So for example, if you are using a teleoperation device, your operator oftentimes is disconnected from all the rich physical contacts that the robot is actually making. So oftentimes the operator needs to guess what's the contact, what's the tactile feedback from the vision alone, or you always try to like overshoot your action in order to compensate those missing informations. Okay, and then one more thing that we did actually slightly better than UMI is that we no longer just use that haptic feedback during demonstration, we also record those information. In UMI, we actually does not explicitly record tactile information or force feedback, at least in the original design. So, but in Dex UMI design, we actually add additional tactile sensors on the actual skeleton so that the information about contact and tactile is recorded. So later, if you want to train a policy, you can use that tactile information as well. And as I will show you later, for some part of the task, actually the tactile information is pretty important. Okay. So finally, we actually still record the visual observations by using a wrist-mount camera. However, here we have a slightly different, or new problem when you're recording visual information, is that now because we use the actual skeleton, the hardware itself actually looks quite different if you compare to like a robot's image that you mount a camera on the robot wrist. So here we actually have an additional visual observation or visual gap that we need to bridge. So in order to bridge this visual gap, we actually developed a quite simple image processing pipeline using all the machine learning tools in order to transfer the video so that it matches the robot policy input. So from a demonstration video that is collected with human wearing the actual skeleton, we first replay the finger actions on the target robot hand and to record what the hand should look like under those actions. So here you can record this video without any interactions with the object or environment, so it's relatively easy to get. And then from that video, you can segment the actual skeleton and the robot hand respectively for each of the video. And then for the demonstration video, we will remove the actual skeleton pixels and then try to inpaint all the background pixels with just some kind of image inpainting algorithm. So it's actually a video inpainting algorithm. And today, in today's day and age, they work pretty well. And then we can also compute the mask intersections for the visible part of the robot hand, right? So we actually need to remove the foreground pixels that is occluded, supposed to be occluded by the object itself. And then with that, you can combine the background pixels that you just inpainted and the foreground pixels of the robot hand, and you can get a video that is basically looks like a robot hand doing the task, but is actually collected with human hands wearing the actual skeletons. And that is a video or the visual observation we use to train the robot policy. And here is the final robot policy in action. You can see that the robot is doing the task of turning off the stove using the fingers. And then he will the robot will pick up the pen. And you can see that for this particular step, you actually need to use both the thumb and the index finger to stabilize the pen, which is something that's really hard to do with just Umi or parallel whipper. And the last step is to pick up some salts and sprinkle the salts onto the salad. And then that's the end of the task. And actually, to my surprise, the last step of sprinkle the salts, it feels so easy, but it's actually the hardest part. Actually, the robot failed most in this step. And that's especially if you don't have tactile sensing. So here is actually a quick comparison of a robot. If we disable the input for the tactile sensor, it actually don't know how much to pinch into the salt. And that's also because the vision observation in this particular step is occluded. So you actually don't know whether you pinch enough or not. So for this step, tactile is quite important. And then we actually the same idea that you can use to design actual skeletons for many different robot hands. So in this project, we actually try to apply the same idea for two different robot hands. One is under-actuated hand, is Inspire hand, is one of the most popular hands nowadays that's on the market, and also a fully actuated hand, X hand. Right? So actually between these two different hands, for X hand, because it's fully actuated, it actually has more motors. So we need to add, for example, more joint encoders for the actual skeleton design, and also the kinematic structure is different. So we kind of need to design different actual skeleton for them. But in the paper, we actually details about how you can automatically come up with the design relatively easily, so that you don't need to manually design each of the actual skeleton in a very time-consuming way. Okay, so with the different actual skeletons, you can actually collect data for different robot hands. And here is actually two different hands doing the same task that's trying to pick up tea leaves from one pot to move it to the other. And this is quite difficult because it's using the tool, and you need to be very precise on picking up the tool, and also using enough strength to pick up the leaves. And with the actual skeleton, we show that you can do the task with both hands. Okay, so that's the first part. That's about the first strategy, how we can reduce the embodiment gap with smart interface design. So the overall goal is try to ensure that the data collected with human demonstration is transferable to the robot hands and also sufficient for learning your robot policies. However, in the end of the day, we still need to train different policies for different robot hands, right? So, which means that if you come up with a new design of a new robot hand, you kind of need to go through this data collection process again and then train another policies. The old policy cannot be directly generalized to those hands. So that's a little bit annoying. Wherever you tweak your robot hands, that you think is better, but you actually need to recollect data and retrain the policy. So that's why in the second part of my talk, I want to kind of highlight another idea, is that how we can redesign our policy formulation so that we can represent the embodiment differences in the policy as well. So the high-level idea is actually quite simple. So instead of formulating your manipulation policy as fx and takes x, which is the observation of the environment as an input and direct input output action, you actually add the additional input argument to your policy, which is your robot embodiment. Right. So those, the G here is representing the robot embodiment, the hardware design parameters that you use. So that is the high-level idea. So in order to formulate your policy, that's why a critical question to ask here is how to represent the kinematic or the hardware parameters of your robot. Right. So in particular, I think the kinematic structure is probably the hardest one to represent, and then how to make efficiently use this representation in a policy learning framework. So this question is actually handled by this algorithm called graph embodiment transformer. We call it GET. So here's how it works. So for a given robot hand design, we'll first represent the hand as a graph, which is a very natural way to represent the kinematic structure. And then in this graph, each of the joints is represented as a node in the graph, and the links are represented as directed edges. And then for each of the joints, we'll represent the nodes as tokens, and then each of the tokens will contain the local state information with respect to that particular joint, and hardware information with respect to that particular joint. And then the joint tokens will communicate through the attention layers in this transformer network in order to learn the global coordinations between different joints. And then we also add additional bias in the attention score based on the connectivities of the graph. So for example, we can add additional bias on the attention map by using the edge distance or the parent-child biases. And then the rest of the network is pretty standard transformers, and then in the end of the policy, the network will actually predict output two components. One is per-joint actions to control each of the joints. And then also we add additional self-modeling loss that's basically predicting the forward kinematics positions for each of the joints. So what we found is that the self-modeling loss is particularly useful for the robot to actually understand their embodiment encodings. So although you don't use it for your policy, but it's a very useful regularization for policy training. Okay, so in this paper, we actually look at this in-hand rotation task as an example task we study. So where the task is to try to rotate the cube in the hand of the robot. And we study this problem in a relatively slightly more complex scenarios. We want the same policy to control the robot hand with different link lengths, different hand designs. We actually remove some of the joints and links from the leap hand in order to create different variations. So on one policy to control all this. So to train this policy, we first need to procedurally generate a lot of different embodiment designs. So how we do that is basically just take the original leap hand design and procedurally remove and add links and change the geometries of the hand to create a large variety of embodiments. And then for each of the embodiments, we will train the individual RL expert to generate high-quality data for doing the task of rotating the cube. And then after that, we can distill all the expert data that's trained with RL into a single embodiment-aware transformer network, which is a GET network, using behavioral cloning. And then in the end, you actually can deploy this the single policy to a new robot equipper, zero shot without collecting any additional training data, by just providing the hardware parameters to the policy as additional input. Right, so the policy actually never collects training data in this particular robot hand, and is still able to control this robot hand. And then in our evaluation, we actually test with different variations of embodiment differences. So for example, different graph representations by removing some of the links, and new geometries by extending the certain links of the robot hand, and some of the variations that has both geometry and graph differences. And we compared with different baselines that actually does not use any graph encodings, or using different type of graph encodings, like for example, depth first search algorithms. So you can see that if you don't encode the graphs properly, it actually hurts the performance. But in comparison, I think Get0 is always able to achieve better performance regardless of the testing scenarios. Okay, so here is the last slide that I want to summarize my today's talk. So today I talked about this cross-embodiment learning problem for dexterous manipulation, and I introduced two different types of cross-embodiment problems. One is the embodiment gap between human hand and robot hand. Another is just basically the embodiment gap between all the different robot hands that you come up with or on the market. And we also talked about two different strategies for addressing this problem. That is, first, if you can, try to reduce the embodiment gap in the data collection interface by thinking about how to collect sufficient information, but still limit your human dexterity so that it can be transferable to a robot. And then second strategy is try to represent embodiment difference in your policy to train an embodiment-aware robot policy so that potentially that policy can be zero-shot transferred to another robot design. And then all the projects I talked about, here is the link. If you want to know more details, please visit those websites. And that's the end. I'm happy to take questions.
We have some questions on Slido, which I'll ask, and if anyone else has a question, feel free to come up.
Okay.
I guess I'll sort of summarize since there's so many questions and we have very little time. I was curious what you think about sort of the gap between the human and the robot hand for the first work, and sort of, do you feel it's more of a hardware issue in terms of like getting tasks to be, doing more and more dexterous tasks, or do you feel, it's more about learning algorithm problem? Or I know you sort of work on both sides. I'm curious what you feel, what's the limitations right now?
Yeah, I think actually the gap probably is on both sides. It's very hard to like point fingers on only one side.
Right.
But I guess one thing that I do want to highlight is that indeed the hardware, you can easily point out that it's not as dexterous as human. But one thing I learned by doing all this manipulation project is that even with very, very simple hands like parallel jaw gripper, you actually can be very dexterous, especially if you have two of them. So I think that maybe we put too much emphasis on the hardware limitations, and we should think like more creatively about how we collect data or like just make use of them so that they are still capable even with very simple designs. And there's actually a lot of benefits with simple hand design. They break less often and it's much cheaper. Yeah.
Shuran, thanks for the great talk. I want to try to better understand the limitation of a system like Dexumi. For example, I want to know how, for skills like in-hand reorientation, can we learn through the data that we collect by Dexumi system?
Yes, that's a very good question. So just to repeat, for Dexumi, what's the limitations? Like for example, for in-hand reorientation, whether we can learn from Dexumi. I think the answer is probably yes, although we didn't try it. But I do want to mention that for in-hand rotation, it's actually a very special task that you actually don't need vision. So I think that for Dexumi, one of the hardest part is to think about where to put the camera and how to make sure that visual observation is recorded. And I think because the in-hand reorientation does not really require vision, therefore make it easier to actually do human data collection and make it transferable to robots. But I think one potential limitation for Dexumi, in particular in that context, is that for in-hand reorientation, it actually needs a very big hand. Like lip hand can do this task. But if you try it on other hands, like for example Inspire hand, I doubt whether the Inspire hand can do this task. So in that case, because the hardware has that limitation, maybe we cannot do that task.
I see.
Yeah.
Also, I'm really curious, since you already tried Inspire hand and XN in the first work, have you ever tried to get zero generalizable for those two commercialized hands?
Yes, I really want to. Yeah, I kind of need to convince my students to try those two examples. Get Zero actually, we submitted this work earlier than Dexumi work, and also at the time there's not too many Dex hands on the market. I think this year there's an explosion of different hands. So yes, I think follow-up work can consider trying to train Get Zero for like this kind of commercially available hands. Yeah.
Thank you.
Let's take one more question while the next speaker sets up.
Thanks for your talk. So I am curious about the Dexumi. So you're recording joint angles, but I think the differences in joint length would also require like retargeting. So are you like limiting the diversity of like hardware, or are you using like any retargeting algorithms to like compensate like the difference in length?
Yeah, that's a very good question. So the question is that if you have different links, different link lengths, you still need retargeting. So we address this problem through our exoskeleton design. So when we design the hardware, we design the exoskeleton, we try to match exactly as the target robot hand, so that you actually don't need to worry about that part. So that's also the reason why we need to design different exoskeletons for different target robot hands.
I see.
Yeah.
I see.
Good question. Thank you. Thank you.
So next we have Ankur Handa to speak here. Ankur Handa is a principal scientist at the NVIDIA Dexterity team, which is at the intersection of perception and control. He's been working on many great dexterous manipulation works at the intersection of sim to real and also using computer vision for robot hands. He obtained his PhD with Professor Andrew Davidson at Imperial College London, a postdoc with Roberto Coppola, and he's won many Best Paper Awards, BMBC 2014, and Best Student Paper at ICRA 2019. Thank you. Let's have Ankur.
Thanks a lot for inviting me. So my talk's going to be about how we can use simulation to do dexterous manipulation. Okay. So just to give you a flavor of the work I'm going to be talking about, it all started in 2019 when we had our first system that was doing teleop, where it's all done using computer vision. You have 4 cameras watching a robot, watching a human hand and tracking the motion of it and relaying that over to the real robot. So this was one of the first teleop systems we developed and on dexterous hands and arm system, and it was also one of the very first teleop systems in the community on putting together learning-based and vision-based teleop with on robot hand and arm. Then we moved on to trying things a bit more with simulation, where we had our first result on using vectorized GPU simulation to do sim-to-real at scale on a robot hand to do cube reorientation using computer vision again. There was no tactile sensors, there were no markers on the cube, etc. And it was all done primarily using computer vision on a Allegro hand. We extended this work to do a lot more with the hand and arm system, all using simulation. We're still in the process of doing sim-to-real on it, but it was exactly the similar task, but done on a combination of hand and arms. We then also had a system a few years ago where we did grasping, all using again sim-to-real, but the input in this case was not the object pose as it was in the 2022 work. The input was a depth image, so it was directly getting the robot to pick the object on the table using depth images as the input. For some reason this video doesn't load, and then we extended that to use a stereo image. So here the input is stereo images and the robot's basically doing grasping on that. And the last one is where we extended this work to have it running on the Boston Dynamics robot recently this year. Again, the input is the stereo images, and the robot's basically able to pick up arbitrary objects lying flat on the table. So this is the kind of work we are going to be talking about. So just to give you, our mission here on what we do, it's all about building superhuman dexterity, primarily using R as a tool to learn that in simulation and transferring that to the real world. So dexterity is all about working with your fingers to perform intricate, high-value manipulation. It requires arm and body coordination as well as legs for force transfer navigation, but the key is leveraging fingers to effectively do the work. And we wanted to get it to superhuman because we can't be limited by the human performance. This is a very impressive talk from David Silver last year, where he talks about how RL became the go-to algorithm for various big breakthroughs we've seen in AI. But we haven't seen much of that in robotics, and my hope is that after this talk you'll also consider using RL for most of the stuff you're doing. And in parallel, recently we've seen LLMs also start using RL, so the march of RL is happening. It's a little slower, but it's happening. So this is the timeline of the work, so I'll skip the first one, which was all about teleop. We didn't succeed much with it, and instead went back to doing simulations. So my work, this talk will only be about the stuff we do with sim-to-real at scale. So the first work is, again, the Dextreme work, where we have a robot hand. We manipulate the cube so that the pose of the cube in hand matches the one shown on the bottom right. So just play the video for you to see what's happening. So as soon as it reaches the target cube pose, it resets, it gives you a new goal, and it shows the intricate, rich, dexterous manipulation it's undergoing to match the pose of the cube. One thing to remind here is the bottom right is the digital twin that's being visualized live. Because you get the pose of the cube, you can visualize that in simulation and see how well it's doing. So you can judge the accuracy of your pose estimator and how well the robot's manipulating the cube, so just letting you float the hair. Get stuck here at times and then figures out new strategies to match the pose. Okay, I'll skip over the rest, but again, this was all using computer vision to get the pose of the cube, and the pose of the cube goes into a policy to get the next finger targets. So this was similar to what OpenAI did back in 2018, but they had a lot of sensors in the cage that they developed, and it also had markers on the cube, and it was done on a shadow hand, which was super expensive as well. So we wanted to simplify the whole system and bring it down to a point that we can run it on a single GPU when it comes to training and using computer vision to get the pose of the cube, and therefore and run on a much cheaper hardware like Lerrel. But both of these are examples of how scaling up simulations for context-rich manipulation can allow symmetry to happen. So, as an input to the policy, so this is the diagram on the bottom right is basically giving you a flavor of what's going into the network, it's what's coming out. So the object pose is going into the neural network together with the joint angles and the proprioception history and the target orientation that you might want to reach. And it gives you the joint angle targets, so the fingers get there. This is the input we give to the policy. There's a lot of variables that you can lump in based on the privileged information you get from the simulator, but the policy only receives the input that is likely to receive to get in the real world. So the privileged information is only going into the critic. So it's the standard asymmetric actor-critic architecture. One of the biggest, key breakthroughs for this to succeed was the automatic domain randomization. Normally, you would have fixed range of parameters that you optimize over, and then it's manually tuned, and you train your system at scale, and then you find out the policy that transfers to the real world. But if you see in supervised learning, you normally have a validation set based on where you choose the best performing model. So in simulation, what we can do is similar things where you train a policy on a range of parameters, and then you test it slightly outside the range of the parameters to test the generalization of the policy, and based on that, you expand or shrink the range. So randomization paired with evaluation in the loop provides natural curriculum, and it's a source of infinite data. The whole point of this is that you want to train on extreme diversity you can get from the simulations. So we found out that our best vision policy was on par with and slightly better than the one they had in OpenAI, but at the same time we reduced the training time from multiple months to 2.5 days using a vectorized simulation in ICRA. And it's worth reminding that we can go past 50 consecutive successes as well, but it was capped to the 50. So that's just what OpenAI had initially chosen. So one of the other things which I liked about this the work is that you actually get to see, if you have an iPhone, we ended up recording some of the high frame rate videos here. If you have an iPhone, you see how the rich dexterity that emerges out of it when you train at scale. I think it's at 200 frames per second. And it just uses the thumb at the end to flick it. This is when you see where all of this happens so fast when you see it live, but you really start to appreciate the dexterity when you capture that at high frame rate. And this is another one which was accidentally captured, but I think it also shows the issues with working with hands. So again, you end up breaking the hardware more often than you get it to work. So I was sat next to it, and I went to get some water, and then I saw the video that it has smoke coming out of it, which was quite humbling. You end up breaking the hardware quite often. So I think what it suggests that no matter how many layers of robust software you add, you will always feel the hardware at the end of the day. And it's important to have a very robust hardware to run your algorithms on. You can only do so much with software at the end. So to fix that problem, my colleagues, Carl and Nathan, developed these geometric fabric frameworks, which I'll probably skim most of the details on, but just want to show you that that geometric fabric framework allows you to develop much more gentle policies that are smooth and allow you to avoid breaking the hardware over time. So this is the same system, except that you add another control layer on top, which is giving you the smoothness as well as the ability to provide policies that are gentle on the hardware. So normally when you train with Aria, it's bang-bang control there, where you go from one end to the extreme end in the action space quite often. So this is also, if you do the FFT of the policies, you see that the policies we had with Extreme were pretty noisy, and the policies we get by adding geometric fabrics tend to be much smoother. It was also robust to exogenous disturbances. I think here I'm basically trying to be an adversary, and it still seems to work pretty robustly on that one. So for this sort of behavior to emerge, we also had to train in simulation by injecting random forces on the object. And that's why it's reasonably robust to that. So moving on, this is the next line of work where we started to think about grasping with hand and arm system, complete hand and arm system. Before that we only had a hand. So these are three different variations of the system where you see it's taking depth image as the input, and it's able to pick up objects from purely just using this distance data. It's also a closed loop, as you will see that it's able to pick up that object after trying multiple times. So what is so unique about the work? It was one of the first systems for RM manipulation on a 23-DOF robot. Geographers-based robots often have 7 degrees of freedom and 1 DOF for the gripper, and this is 3x the complexity. We added geometric fabrics for inherent smoothness and collision avoidance, and it's doing end-to-end grasping via student-teacher distillation on depth images as opposed to taking point clouds as input. And it is reactive and fast, and it's working on it can work on arbitrary set of objects. So one of the things I want to highlight here is that normally, I think it's probably captured here in the video I want to show you. If you just set up the problem of grasping with the hands, it would end up coming up with these very unusual grasps, which are undesirable. This is not, it solves the problem, but that's not what you want. So what we did here is basically we had a data set of humans grasping objects, and we basically do PCA map on the grasps we get from this, and use that as the action space to pick up natural, to provide guided grasping behaviors here, as opposed to just let the fingers move around independently. So if you have a PCA space on top, the grasps tend to be more human-like, and that's basically captured from watching a human do it from the different data sets, and making that as the action space. So we don't again train on arbitrary set of objects, but with the privileged information using a teacher, which takes in full state information and the object ID and the proprioception as well. And we train a standard actor predict to get the teacher. And then we distill that onto a student, which is taking a depth image. We added all sorts of noise on the depth images that you would get from a real Intel camera. And this distillation is again done using Dagger, which is fairly standard at this point. It sort of became more popular in robotics, especially in SimTrier with the locomotion work from ETH. So that same recipe is adopted here, where you train a teacher with all the privileged information and state vectors, and then you distill that onto a depth image for the student. And then we deploy that in the real world. One other thing I would say is that we were also regressing to the object location as an auxiliary output when we were doing distillation. That helps us sort of get a sense of how well your simulation SimTrier is working, because it's sort of a debugger and checker. If the object location predicted by the network is sensible, it's likely that your SimTrier transfer will go well. Here are some of the results of that. This is the one I'm talking about, the bottom right. In the bottom right, you see this reference frame, which is basically predicting the object position as an auxiliary task. So it's able to predict that pretty well, even when the object's moving. And it generalizes to soft objects as well. And you can see that the graphs tend to be pretty natural and human-like, where it's just going to the object and closing the fingers in, as opposed to just flopping in with fingers all over. And this is the full video where you can appreciate the system. It's sped up by 8x. And you can see at the bottom right that how crucial it was to be able to also predict the location as a debugger and a sanity checker. So that tells you how well the SimTrier is working on that. And then we extended this work to, the previous one was using depth images, we extended this to work on direct RGB. Depth has all sorts of issues with holes in it, and it doesn't necessarily work for transparent objects, and we are so used to, in computer vision, taking images, RGB images, so we wanted the system to be more towards RGB. All we had to do was to have a ResNet embedding going into a transformer and doing cross attention, and it works just as well. So this is what the network sees. It sees two images. There's a stereo pair. It sees two images, and it's doing the same thing, except that the distillation now is done using a stereo pair instead of a depth image. This is what we train on when we do the distillation. We randomize textures, we randomize backgrounds, everything. It's all using no real data here, except that the power of domain randomization here. And this is again the full system that's working on stereo images. Still the behavior is very much the same as you would get from depth. So that was a good, it was reinforcing that you can make things work both with depth and RGB. We extended this work to, in a collaboration with Boston Dynamics. So this is the recent work we had. Takes in a stereo pair again, except that the robot's different. But it's got a three-fingered hand. So this is what on the left is what the robot sees, and on the right is you see a robot basically picking up object with 3 fingers and moving it to a target location. The head movement was also part of the action space, but it was during distillation. So you also see that it's choosing different arms sometimes, and the reason is that since we are able to also predict the object location, we pick the arm based on the proximity of the object. So we train 2 different policies, one for the left and one for the right, and based on the object location, we instantiate that corresponding policy. And the last one is still something we are exploring, which I want to talk about, is the population-based scaling, DexPBT, which we did in 2022, where I want to highlight the rich dexterity that emerges when we train things at scale with hand and arm system. As you can see, it now drops it back and then picks it up, and it's able to get to the desired location. But in the interest of time, I will probably skip most of the other bits here, but I want to highlight the evolution of the student feature distillations for SimTutorial. We started off with Dextreme, which was using object pose, then we did with depth, and eventually closed in on using RGB as the input. So some of my parting thoughts here: simulations are a path forward through building highly dexterous systems. Majority of the grasping systems today use simulations to train, and soon I believe that manipulation systems will also be using SimTutorial at scale, and because getting teleoperation data for complex manipulation is extremely non-trivial. And RL is a recipe for superhuman performance, and most superhuman systems today use RL in some form or the other, and VC is a special case of RL. And direct end-to-end dexterous systems that map pixels to actions are really robust. It is the future given the nature of the real world we see. And that's it.
Great, thanks. I'll ask one question from Slido, and then if people want to come up, we can maybe have a chance for one or two more questions. Ankur, I guess one question for you. People ask, sort of your earlier work is more focused on teleop, and you seem to have moved away from that. Do you feel, like, what do you feel the downfalls? A lot of people are doing teleop now, but why are you moving away from it?
I think if you want to get superhuman performance, RL is the recipe to go. There are lots of issues with teleoperation. It simply doesn't scale. That was one of the reasons. When we did the Dex pilot work, we realized even collecting data for back in a hole was just becoming too tedious and cumbersome. And it was exhausting and tiring. I had to wait for at least a week to get, to recover from it, because I had to focus in on this task, and my eyes needed some rest afterwards. So I think that the scale is the major reason why you don't want to do that. And the second reason is that even after you've done supervised learning, you still need some sort of RL on top to improve the performance that we've seen with LLMs. And that's basically human in the loop kind of thing, which is again slowing you down. You want to remove the human from the system as much as you can.
Yeah, makes sense. Thanks. We'll ask one more.
Yeah, I do have a question. So I know that the grasping the robot use is mostly the power grasp. How would you do the functional grasp?
I think in the Boston Dynamics work, we didn't impose any constraints on the ECU space there, because it was just 3 figures. We only ensured that the grasps are mostly getting the fingertips basically pointing towards the center, so that you don't have mangled or grasping in the system otherwise.
But thanks. But if we want to do the manipulation beyond the grasping, we have to make sure that grasping pose is already functional, and then we can do the manipulation.
So I think that would depend also on the affordances of the objects you're grasping. It wouldn't just be just the fingers itself.
All right. Thank you.
Okay, thank you, Ankur, for a great talk. Next we'll have Tengyu. Tengyu Yu is a research scientist at General Vision Lab of Beijing Institute of Technology and General Intelligence, BIGAI. He received his PhD in computer science from UCLA in 2021, where he worked with Professor Songchun Zhu. His work at the intersection of 3D computer vision, computer graphics, and robotics. His recent works, such as 82 and Any Skill, span generalizable dexterous grasping and manipulation, which I'm sure he'll talk about today, as well as whole body control for humanoid and quadruped robots. Great to have you.
Thank you for the warm welcome. It is my pleasure to share our latest work on transferring dexterous skills from human to robots today. My name is Tengyu. I'm from BIGAI. If you are not already familiar with us, we are a nonprofit research institute located in Beijing. So my topic today is about transferring dexterous skills from humans to robots. But before we get into that details, I would like to ask a question. What counts as dexterous? Because we have seen many progresses in dexterous hands and manipulation skills with them. A lot of works focus on moving objects, picking and placing them, in-hand reorientation. Well, this is a challenging task. By the way, this is the work we did 1 or 2 years ago, which is picking up multiple objects with the dexterous hand simultaneously. So yeah, these are challenging tasks, and it's impressive that we can do many of these nowadays. But the question is, it is still far away from what we can do as our human hands. We are still far from utilizing the full potential of our powerful five-fingered hands. Take a look at these examples. We can use our hands to squeeze a toothpaste, preferably not by that much force, with a controlled fashion. We can spin our pen. I think Xiaolong's work has done pretty well on that task. And we can do magic tricks with cards and coins. We're still far away from them. We didn't finish that task by now, just to reassure you. But we want our robots to eventually match these skills. There are many reasons why we are still far from these kind of manipulation skills, the hardware, the algorithm, the simulation. But today I'm going to focus on the data problem. So I hope you can all see this. Right now, when we try to train our dexterous manipulation policies, these are the data usually come from one of the 4 sources. The first 2 are teleoperation systems. We can do remote teleoperation with, for example, a Billard system, or we do some sort of exoskeleton teleoperation with, for example, Dexterity that Shuran just shared, and maybe with the physical hand, the physical robot hand attached somehow to your human hand. But with these, there are problems. With if you're using a VR system, you don't get the force feedback and tactile feedback. Your hand doesn't stop when it touches something. That makes dexterous manipulation, such as pen spinning, very difficult to tell off, or impossible to tell off. And with exoskeleton systems, your robot hand is somehow blocked, like some space around your robot hand will be stopped or occupied by the exoskeleton system, so that if you try to use, for example, the back of your hand, that doesn't work, right? And also you can do IO rollouts. You can learn an IO algorithm for extremely challenging tasks. Of course, you can do that. That's scalable with compute, but it doesn't scale with PhD brains. So basically, if you try to do a challenging task with RL, you have to spend many weeks or even months to tune the reward function and training schedule, which is notoriously difficult. And finally, we all want to learn dexterous manipulation skills with human videos, but we don't have the underlying states and actions as of now. I hope in the near future our technology can do that. So without these data sources, we're still not able to do this. Why? Because our data collection system they either don't have the tactile or force feedback, or they don't have the ground truth underlying states and actions of the hand. So is there a data collection system that have all of these? Well, the answer is yes. We can use a high-fidelity mocap system, which is widely used in the animation and computer vision industry. So a mocap system, I think most of you should be very familiar with this, is a set of camera around your hand, and you place reflective markers on your hand and on the object, so that the poses can be tracked of both the hand and the object. There are many existing datasets on the market or on the internet of hand-object interactions. I listed only 4 of them. There are more, and only these 4 have more than 10 million frames already. So if we can recycle these data for robot hands, then I think we can solve a lot of problems with this data. So how do we do this? at the beginning of the project, I thought that's easy. That's just imitation learning, right? We have the states of both the hand and object. We can just train our algorithm to track them. Turns out the success rate, these numbers are the success rates, are not satisfactory. So the 34.3% is the single hand tracking success rates if we train a single RL policy on it. And the second 12.1% is the bimanual success rate. Why? Because if you look at the failure cases, mostly it's just objects falling on to the table when we are supposed to grab them. So the problem is that for delicate content-rich interactions that require like force and tactile feedbacks, simply imitating the hand pose and training our algorithm that, for example, that's supervised on the object poses is not it's not enough. You need to really focus on the interaction parts so that your model can understand how to manipulate the objects. So we move on to a two-stage solution that decouples the imitation from the interaction. So the first step, we trained if you can see it. Okay. In the first stage, we trained an imitation policy here, pi that's that takes in a reference human hand trajectory and outputs the action sequence that moves the robot hand to follow that human hand trajectory. So because at this stage we don't care about the object whatsoever, so in this stage we can use the hand-only dataset, which is much larger than hand-object interaction datasets, and we can try this one single imitation policy for all manipulation tasks. So after we train this, by the way, this policy takes about an hour and a half to train, and you only have to train it once. And then after you have trained this policy, you freeze it, and then you, for each manipulation sequence, for each mocap data sequence, you then train a residual action policy that adjusts the imitation policy to finish or to accomplish the manipulation skill. So at this stage, you incorporate the reference object trajectories and also the contact information and the proprioception hand state information with the policy. So now that your residual policy understands how the delicate interaction between the hand and object is. In summary, the pi-R, the residual policy, takes in the reference hand object trajectory, the shape information, which is a BPS encoding of the shape, the hand imitator's action, and the contact information, the proprioception of the robot hand, and outputs a delta action. So in the end, you sum up the actions from the hand imitator and the residual action and the residual policy to produce the action that gets executed in the simulation. So once you have all these, you can then obtain a executable action sequence in the simulation. So how does it work? These are the simulated results that reproduces these mocap sequences. This mocap dataset is the I think it's the Oaking V2. So we are able to boost the success rate from 34.3 and 12.1% to 58.1 and 39.5%, which there's still a gap from perfectly imitating those sequences, but there is a significant improvement. The failure cases are mostly objects being too different, like the object in the simulation is too different from the object from the actual mocap sequence. And sometimes the mocap sequence has noise in it, so we don't have a perfect recording. In this case, we find that we are able to stick the robot hand fingers through the handle of the mocap, which is quite surprising and quite impressive in my opinion. And we have 4 more examples, and I think that's it for the simulations. Okay. And of course, we are in a robotics conference, so the natural question is, how does it actually work on an actual robot? We're able to replay these policy rollouts on real robots. I want to emphasize that this is not like online policy inference. This is a policy rollout from a simulation and replayed on the actual robots. So we're able to open the toothpaste tap or put out a alcohol lamp, uncap a pen, and pour in liquid. So these are Dexter skills that, as far as I know, that wasn't demonstrated before. And what's more, we realized that during our training of the policy, we didn't really use any prior information on how the robot hand should look like, other than having a robot description file for the simulation. So we're naturally able to extend this method to arbitrary kind of robot hands. We experimented on the Inspire hand. This is the tactile version of the Inspire hand. This is just a articulated version of the human hand. We have the shadow hand and X hand. And also, surprisingly, we are able to transfer skills to a Lerrel hand, which is much, much larger than a human hand and have one less finger. So that's surprising, and that's a very nice property of our method. So once we have that, we can get back to the original data problem that we set out to address. Now that we can transfer the mocap sequences into rollup data sets, we can just organize this data set. So we converted the data from open to B2 and also favor into a large-scale data set called DexManipNet. It has 3.3 thousand trajectories over 61 tasks. There's 1.34 million frames, although that number is just time the trajectory length times the frame rate. Notice that this is on the Inspire hand only. So if you want to extend that into other robot hands, or if you want to extend that into other mocap data sets, we have the data, the code available online, so it's quite easy to do that. And also, we experimented on this data set with a lot of the imitation learning policies that we have. We tried with, I think these are implicit behavior cloning, behavior transformer, and diffusion policies. And surprisingly, even with the diffusion policies, we can only get less than 20% success rate. I think this is the simple task of moving a bottle from place A to place B. So with the simple rearrangement task, the diffusion policy can only achieve less than 20% success rate. So I think we are still quite a long way in modeling of these Dexter's manipulation. But then I'm quite confident that DexManipNet can provide a good starting point for people interested in this stream of research. So I'm going to sum up my talk with 3 lessons that we learned and 3 open problems for the future. The lessons learned is that first, if we want to do like human-like manipulation, we have to reuse the abundant human data sets we have. Right now we are doing mocap data sets, and in the future maybe we should extend this to human video sets as well, but that embeds a lot of challenges on its own. And second, we should really separate imitation from interaction, because these are 2 fundamentally different problems. And if we can do that, we get a lot of training efficiencies. And last but not least, if we can disentangle problems, training our policies on a smaller problem is obviously much better than training on a larger problem. What we are still facing, the problems that we're still facing in the future, number one is that our our method really relies on having a mocap system. And currently, the reliable mocap systems are very costly, very expensive, and also you're required to place these adhesive reflective markers on your hand in the object. And these are actually little spheres, reflective spheres. So with those markers on your hand and the object, if you want to, for example, slide a pen across your finger, then these markers will block your way. So what we really need is a low-cost and non-intrusive, like or markerless mocap system that can capture both the hand and the object movements in high fidelity. And also, we would like to, it would be great if we can have the 3D shape estimation from these open videos. For now, what we do is that we just use the ground truth object mesh from the mocap dataset. If we don't have that, the whole training pipeline in simulation fails, obviously. Right now, we have some progress in 3D shape estimation, but the quality isn't good enough for these kind of simulated reinforcement learning. And lastly, I think we all want to learn a generalizable dexterous manipulation policy, which has a lot of problems on its own. How you learn, how you model. I think this presentation solves some of the data problem. Okay, thank you. That's my presentation. I will thank my colleagues, wonderful colleagues that did this work, and this is the link if you want to find more information about it. Thank you.
Thanks for the talk. I'll ask one question from online, and if anyone else has, feel free to come up. I think there was a lot of questions on tactile, sort of how are you getting the data in a robot, in a real robot, and like, what do you feel the role of tactile is in general, and do you feel that's really important for your mocap methods and stuff?
That's a very good question. Tactile is important. It is very important in our system. So in our, I think, let me try to figure out. Okay, so in our model pipeline, we really need the contact information for the residual policy. Yeah, I think for the inspired mocap hand, the tactile information is a grid-like structure. Like for each fingertip, it has some like 9x9 grid or 3x3 grid that has the force information on it. You can quite easily simulate those in ICRA or ICRA. And on the real robot, because we don't have these deployable robot policies right now, but I think most of the new commercial robot hands provide those kind of information.
So that's like a binary thing that you're doing in simulation, or is it continuous values or something?
That's a good question. I think, as far as I remember, those are continuous values. Okay. You have a force, estimated force.
Cool. Any questions, or I'll ask another? I guess I'll ask one more. What do you feel about sort of the sim to real gap? You're doing a lot of rollouts in simulation, and some people say, just do teleop in real, avoid the whole simulation thing altogether. How do you feel about the sim to real gap? Do you think that would be a problem when you're doing real robot stuff, or do you think it's a problem you can overcome?
Oh, it's definitely a big problem in robotics. The sim to real gap is quite significant, and that's exactly why we don't have the deployable policy on real robots right now.
Right.
But I think, according to our experience with other robots, this is not that difficult to address. But it's not impossible. With enough domain randomization and enough randomization of the training sequences, you can obtain quite good results.
Yeah, cool. I think it's great your work came after Ankur's, talking about sim and real world. Yeah,
right.
Great. Okay, I guess that's it.
All right, thank you.
Thank you.
Hello everyone, my name is Hughes. And after the 3 great talks in the morning, we are going to have spotlight and poster sessions. And we are going to have 4 spotlights in the morning and 4 spotlights in the afternoon. And each of the, we will start with the author of Seek Grasp, Sequential Multi-Grasp Dexterous Grasping. So if the author is here, please come to the stage. And we also invite other speakers in the morning to line up on the right, as well as each of the spotlights will have 3 minutes. And there is 1 minute warnings on the left of the stage, and you should probably check. Hi everyone, my name is Yifei, and our work is titled Grasping a Handful, Sequential Multi-Object Dexterous Grasp Generation. And we are from KTH. Multi-object grasp is a very important step towards human-level dexterity, and is inherently a very challenging problem because we have to consider interactions between objects and the complex kinematic constraints of the robotic hand. And there are 2 strategies for grasping multiple objects. Previous work has explored into grasping them simultaneously, and it's very effective and useful when the objects are of similar scale and geometry. But in some other scenarios, for example, I have some object in my pocket, I have to use my hand to grasping them sequentially, and and it's very useful strategy to sequentially grasp when objects are of different scales and geometry features. And on the other hand, in this way we can use the dexterous and effect the fingertips for some subsequent tasks like to spin this pen and press buttons. So towards this sequential grasp generation, we have proposed a grasp generation approach and also a large-scale data set for this purpose. And we employed optimization-based sequential grasp generation. The robotic hand, together with previously grasped objects, are initialized around the target next to grasp target object. And then we have an iterative energy-based optimization formulation to encourage the robotic hand to approach the target object, establish a force closure, and avoid penetrations. With this method, we generated a large-scale data set with 800,000 grasps, more than 500 different objects, and up to 4 objects with 1 arbitrary hand. And notably, this method is also generalizable to different hands besides arbitrary. And we also have tested in the real-world experiments to show that it outperforms the baseline in terms of the grasping stability. And the key takeaway from our work is that grasping multiple objects sequentially is a very useful method. And I think multi-object grasp is a underexplored area in the future that could potentially gain more attention. Thank you very much.
Hi, I'm Jai Chen from Tengyu University, currently a 3-year student advised by Professor Wang. I'm going to present our recent work taxonomy, synthesizing all dexterous grasp types in a grasp taxonomy, which has been accepted as RSS recently. Dexterous grasp synthesis is a long-standing challenge in robotics. Most existing methods rely on sampling or gradient-based optimization to maximize force closure metrics. However, force closure focuses on physical stability and fails to capture human-like grasping habits. As a result, previous approaches struggle to achieve true dexterity. They are either limited to simple grasp types or depend on randomness to generate flexible poses. In addition, these methods commonly suffer from inefficiency, poor contact quality, and tedious parameter turning. Our work tackles above challenges and proposes a novel grasp synthesis pipeline combining human templates, sampling, and optimization. Our method generally works for any grasp type, object, and articulated hand, requiring only 1 human annotated template per hand and grasp type. All parameters are shared across different settings. Our method is very efficient and can synthesize million-level grasps per day. Moreover, the quality of our synthesized grasps is very high. They are contact-rich, strictly penetration-free, and physically plausible. Here are some exemplar grasps synthesized by our method, including all 33 types in the grasp taxonomy in the top here, and the complex object geometries, and the multiple robotic hands. The core of our pipeline is a two-stage optimization process. In the first stage, we densely samples and parallelly optimize the object pose to align with the hand contacts annotated in the human template. In the second stage, the hand pose is further refined using a physics simulator to improve contact quality. Using this pipeline, we build a large-scale data set to facilitate the research in type-aware dexterous grasping. It contains 9.5 million grasps and 10,000 objects, covering 31 grasp types, with each color corresponds to a type. This dataset supports the training of a type-conditional grasp generative model with single-view point cloud inputs. We use motion planning to generate a trajectory and execute on the real hardware. Our real-world experiments achieve 82% success rates on 13 diverse objects and 12 different grasp types. Based on our algorithm, we also developed a UI for annotating semantic grasps with minimal human effort. The annotator only needs to click twice to specify an object contact point and a grasp type. Then the algorithm automatically synthesizes valid grasps in seconds. We have released a web demo and you can play with it freely. Thanks for listening and welcome to my poster for a discussion.
Hi, I'm Joe from CMU. Today I'm going to introduce our work, Normal Flow. It's a contact-based object tracking algorithm that only uses tactile sensing. So to achieve human-level dexterity, it's important for us to track the objects in hand and being able to monitor the contact. Take handwriting as an example. When we write, the pen actually rolls and slides very little in your fingertip. And being able to track those movements is necessary for us to control the stroke precisely. So let me directly show the results. So our approach is able to real-time accurately estimate the object movements based on only the contact. So here on the left figure, you'll see like the tracking results. On the right is the only input, which is the tactile signals. Our approach runs at 150 Hertz, requires no 3D model, and can robustly estimate the object pose across a wide variety of objects, including like those with very little textures, like this ping pong ball shown here. To show the precision of our tracking algorithm, we actually apply it to a very challenging task, which is tactile-based 3D reconstruction, as shown here. So based on only touch, we can very accurately reconstruct the 3D shape of the object, and this is using a technology we just shown, which is normal flow. Since we are able to accurately track the algorithm, track the object, we can stitch the patches together to form a very high precision, high resolution 3D shape of the object. This is something that vision can hardly achieve with this high resolution. After showing the exciting results, I'm going to tell you how we achieve this. So our key insight is to optimize the object pose by minimizing the normal map differences instead of the point cloud distances. Previous work mostly focusing on minimizing the point cloud distances based on, for example, ICP or different methods. And we figured out it's actually can easily stuck on some local minimum. So you can see like the point cloud distances to the object pose is very noisy in these blue dots. And optimizing those can stuck you at local minimum, which leads to loose track. And our approach actually minimizes over the normal maps. As you can see here in the red dots, the normal maps to the object pose is a very smooth curve. So optimizing that can, first of all, it doesn't stuck at local minimum, so it tracks pretty well. And it's going to be very accurate. So eventually, the given tactile images, what we'll do is we first convert them into normal maps, and then try to figure out, use like Gauss-Newton methods to figure out, to minimize like the normal map differences, and in order to find the object pose. Yeah, so that's all about my talk, and we have a live demo in my poster, so if you walk out and you see like a tray table and have a laptop on it, that's me. Feel free to come over. I can show you how the tracking and the reconstruction works, and you can see how robust it is. And here's the code, so it's made available online. You can just download it, and it takes like 2 minutes to set up. If you have a Xiaolong Mini, it's pretty easy to use. So feel free to use it.
Okay, good morning everyone. I'm Xiaolong from Tsinghua University. And today I'm excited to present DoGlove on behalf of the authors. So what is DoGlove? It's a low-cost, open-source haptic force feedback glove designed for calibration and dextro manipulation. So with DoGlove, a human operator can control a robotic hand to perform context-rich tasks. For example, in this video, the operator is operating the left hand to squeeze condensed milk onto slices of toast. Since we've installed force sensors on the robotic fingertips, and thanks to our force feedback system, the operator can actually feel the forces at the robot's fingertips. This allows them to precisely control how much milk is squeezed, more on one slice and less on the other. So how did we make it? We designed DoGlove with a few key goals in mind. First, it had to be affordable. So all components can be sourced for under $600. Second, it had to be easy to build. DoGlove provides 21 degrees of freedom for motion capture and 5 degrees of freedom for haptic and force feedback. It operates at over 30 Hz, enabling real-time control. So we carefully designed its kinematic structure to match the human hand, offering both accurate motion targeting and a comfortable fit. The module joint and finger design uses a cable-driven pulley system to transmit torque from servos to fingertips for force feedback, where linear resonant actuators provide subtle vibration-based haptic sensations. And thanks to the glove's rigid mechanical coupling, we can compute the human fingertip positions via forward kinematics and then map them to the robotic hand using inverse kinematics. The results in accurate action retargeting. And for haptic and force retargeting, we installed 1D force sensors on the fingertips of the robotic hand. The force readings are mapped to feedback actions on the glove. We define 3 thresholds to decide when to activate or deactivate haptic and force feedback. We ran a series of experiments showing that haptic and force feedback can significantly improve task success rates while reducing completion time in contact-rich manipulation tasks. And we also use DoGlove to teleoperate the robot hand and collect demonstrations for imitation learning. The resulting policy achieves high success rates when evaluated autonomously. So that's all. Thank you for listening. You can find more about this project on our website at this link. And also we have brought a sample of this DoGlove. And you are all welcome to have a look on the poster section. Thank you.
Thank you for the speakers. So all of our accepted abstract is now on the website. If you are interested, please check out. And now we are going to have the poster session right in front of this door from 10 until 10:50. And after that, we will come back at 10:50 for 2 more talks as well as the panel discussions. Thank you. Okay, I'll introduce Professor Aude. Aude is currently leading the LASA, Learning Algorithms and System Labs at EPFL, and previously she received her PhD at University of Edinburgh. Her works focus on manipulation, but specifically on collaborating seamlessly with humans and in very dynamic environments. She's won quite a number of awards over the years, so I won't list all of them, including recently IEEE RAS Distinguished Service Award and RSS Best Student Paper Award. Sorry for technical difficulties. Thank you.
All right. I hope you can hear me well. Thank you very much for the kind introduction. That workshop is about multi-hand manipulation. That's probably an example of multi-hand manipulation and certainly multi-brain manipulation. So I think a lot of people think that the hand is the ultimate marvel, the human hand, right? Because of this unique dexterity And I would like to make a case in that talk that I think we can do better. And I'm going to show a couple of examples. But let's first start with very simple hands, as we do have in robotics. With a very simple gripper, this is recent work in my lab, we know that we can do models. I mean, we can typically do here, the complexity is to be able to throw an object and to make it tilt in multiple tilts in such a way that it will land with the correct position orientation. So the smartness here is not in the hand itself, but in the manipulation. It's how much force and torque do you need to apply on that object and release it just at the right time so that it will spin with the right spin to land at the right location. So why should we have multi-finger or multi-limb, let's say, hands? Typically, and that was a case that I was trying to make earlier on when discussing with a colleague, is that we needed to be able to really use all the degrees of freedom and to hold multiple objects in hands because it's more efficient. You can carry many different things. And we hardly ever see this in robotics. If you look at 30 years of grasping, usually you grasp just at the center of mass or at the fingertip, and I constantly say that, when do you hold an object like this? Maybe when you want to throw it, or when you're a little disgusted. But definitely never, as a way of manipulating it. Why? Because it's a little unstable. It's better to hold it in your grip or to hold it within 2 fingers. So for many years, we've been looking at ways in which we could address this issue. And I'm going to go through 4 ingredients to arrive to a stage where not only can we reuse all the degrees of freedom of the hands, but we can go beyond the human dexterity. So the first thing we looked at was the fact that humans hold objects in multiple ways. They never, almost very rarely, hold them really at the center of mass. They're often off-centered, and the reason for this is that often they want to do something with the object. As we can see here, you hold it on the top because you don't want the liquid to flow out. You're holding it at the bottom, it's very unstable because you want to give it to someone else. So how could we generate this? And the first approach that we did was simply to do a nonlinear optimization. It's a complex one, it's non-convex. You optimize for the minimum of torque, and what you're looking for is an optimization problem where you combine both discrete optimization and continuous optimization. Discrete because you're saying, let's find n contact points, here n equals 3, but it could be more, on both the hand and the object, in such a way that I have force closure, okay, it's a stable point, and that also is kinematically and dynamically feasible. And you can resolve that. And the nice thing is that it's non-convex optimization, so you get tons of different solutions, and the funny thing is that all the solutions you get are very close to what the human can do. This optimization was a little slow, so what we did already at the time was then to learn out of all these solutions. Essentially, this is a database that you can generate offline for feasible kinematic and dynamics of the hand. You can then generate this database and learn a distribution. I'm just showing a slice here by taking the PCA. And then from that distribution, you can learn, you can use it at runtime to be able to retrieve a manifold of feasible posture. So you start from some location, and then you say, well, I want to go to the closest grasp in that feasible manifold, and that gives you a variety of grasp. And at runtime, you could retrieve this. And what we found is that those very simple grasps that had been trained solely on a cylinder actually generalized to a variety of objects. I'm just going to really very quickly show you all the variety of objects that we could hold this way, okay? From all those grasps. And of course, you will have to choose which grasp to use for which object, but this could be retrieved in milliseconds. And even very fragile objects. The ingredient number 2 that I really want us as a society to move forward to is to forget about having tactile sensors just at the fingertip, but to have tactile sensors all along the fingers and the hands. So this is something that we did already for many, many years. We had to take tactile sensors that existed, and then we would cover the fingers that you can see here, place by places. And there are many things, there are many nice things that you can do with this. If that video wants to play. And if not, can you press on it? Thank you. Okay, thank you. So that's a very simple control system. Using the compliance, the natural compliance of the finger, and controlling for the compliance with the feedback of the tactile sensors. And this allows us to scan very nicely a variety of objects without having a model of the object, get all of this as a point cloud, and then construct a model of the object based on tactile sensors and construct it. Observe in particular for the glass, how nicely, we will have a zoom on, how nicely the finger can conform with the shape of the object. And this comes very naturally from this combination of the tactile sensors, the pressure is controlled for with the compliant control. We also moved forward with another hand, which you may know is the Allegro hand, 16 degrees of freedom. We also covered it completely with tactile sensors in the front, on the back, and then we designed a null space control in which we would privilege to conform with the object. As soon as you make a contact, then you're trying to conform with the object as fast as possible. So you make just one contact, and then you control for applying all the motion of the hands to maximize the contact. And you can maximize contacts here on any unknown type of object, any unknown surface. The nice thing also is that when you have tactile sensor everywhere, including inside the finger, you can start holding multiple objects within the finger, as we see here. And the other thing that is very nice, which I do every day, is to be able also to explore the inside part of objects. This is also something that I would very much like to have us as a community go beyond holding objects from the outside, but holding them from the inside. This is, by the way, where we need tactile sensors more than vision, because vision can always give us an idea of what is outside, but much less of what it is inside. So having tactile sensors on the outer part is particularly useful. Then, more recently, we looked at how to use all this tactile information inside the hands to very rapidly detect when something is slipping out of the hand, and to be able to build a model of the total contribution of the distribution of mass inside the hand. So we did that. Oops. That's a problem to not be close to the laptop. Yes, if you could click on the video. Thank you. Okay, the next one, please. The next one. Okay, it's skipping it. All right, so I'm gonna have to skip up to talk about it. This was done by using a rectal neural network. And so what we did was to train it from tactile sensors to learn about the evolution, the temporal evolution of the tactile sensing all along the pad, and to be able to build a prediction of how it will evolve to recognize, and we could recognize across many different contents. The ingredient number 3 is to hold multiple objects in the hand. This was something I had dreamt of for many years, is how can we really use all this dexterity and hold of these objects. Now the difficult part with this is to decide which one will I pick up first. Because once you have picked up one object, then it reduces the number of degrees of freedom for picking up all the rest. So we took on representing this. So the first thing that we had to do was to learn a reachability map for every single group of fingers, and to also see how this reachability map will decrease as soon as you add one object. So we can do that obviously knowing the kinematic of the finger. We can learn this for every single group of finger. Then we can do a kinematic analysis, traditional kinematic analysis, and then we can run a very complex optimization to compute all the possible combination of placing an object within this reachability map, how we decrease the amount of space at our disposal, and find the optimal sequence for this. This is again a nonlinear optimization, but the advantage is the same as the one that I mentioned before, that it gives you a plurality of solution, and from this plurality of solution, then you can pick the one that you prefer. So I'm just going to show to you a number of solutions that we had. So we can then learn all possible configuration in which we can hold one object at a time. Okay, so you see it for a ball. Different size of the ball will lead to different type of configuration. Observe that it's not holding it only at the fingertip. It uses a lot on the side part of the finger, and gives you, if you wish, a library of ways in which you can hold any of those objects, being long cylinder, small cylinder, thin, large box, etc. And once you have all this library, then you can choose in a sequencing manner, out of all this library of grasp for any of these objects, which one you should pick up first in order to still have room and not decrease too many of the options that you have for all the other grasps. And we did that for a variety of objects, as you can see that, and you can do it at runtime. and not least, I really wanted us to go beyond the human dexterity, to have a new mobility for the fingers, because I'm personally very annoyed with my hands. I don't find them so good. And the reason why I don't like them so much is that I have a single thumb, and I can only grasp in one direction. So it's highly asymmetric. I had been dreaming for a long time to design a hand, so sensitive. A hand that could have 2 thumbs at least, in such a way that we could potentially use all the finger in combination or by subgroup and be able to hold, for instance, this object and to unscrew it at the same time as we would be holding it. And so essentially having several hands in one hand. And it's not that difficult to create. It was just a question of putting it together. So why is it useful? Typically, if you have a multi-finger hand like this and you want to hold multiple objects, what you have to do, as you see here, is you grab the first one, and then you have to find a complex path, reorient your hand in such a way that you can grasp the other one. And there was also another issue that we faced constantly, and I'm sure you face it too, is that sometimes the objects are too far from your grip. So what if we could have a hand like this, right, that can grasp both sides, and where every single finger is a thumb? Okay, so that's what we built. And thanks to that, you can more easily grasp objects from one side and then immediately pick up from the other one. So it's obviously very efficient. You don't have to reorient your grasp. And then more interestingly, you can actually use your hands as also a, maybe if you can press here, thank you. You can use it as a, okay. All right. It can detach, naturally, and I hope those don't like spider, close your eyes. And then now combining the fact that all the fingers can change role, they can walk, they can pick up objects, then at one time you can decide which of those fingers will be grasping, holding, walking. You can do multiple grasps. You can also use them in combination, as we will see here. There was a lot of optimization going on to decide which finger will be holding and which finger will grasp, how we will place the object also in the back of the palm here, and then ultimately will come and be grasped. And the way that we do this is that we went back to genetic algorithms, combining it also with the modeling of the reachable space and all of this to optimize for all of that. If you don't mind some press again on the video. Sorry about that. Oops. Okay. Yes, it's lagging a little bit. Okay. Yeah, so then in simulation, with the library of grasp that we have built previously from what I explained before, we can then run and find all possible kinematic, all possible finger configuration that will allow us to pick up that many objects, and then we can ultimately build the system. And I'll just show you a last example to just show that it goes beyond dexterity. I wish I could do that with my fingers. It's great to be able to pick, to do a finger pinch, but pick it in a completely symmetrical way. Of course, holding multiple objects, as we will see in a second, on both sides. And you can do that at will with many different fingers and possible stuff. And ultimately, this was what I showed earlier on, is to be able to use groups of fingers to be able to do an in-hand manipulation while the rest is holding the object. This is only the start. We hope to be able to do much more. We are currently redesigning more hands. This one is still very big, so we're going to try to reduce also the size. We're also exploring a lot how can we play with the length of the finger, the placement of the tactile sensors, in such a way that we can optimize all of the dexterity. And I'm going to stop here and thank very much all those collaborators who have been behind all of this work. Thank you for your attention.
Thank you. Do we have questions or I can ask? Feel free to come up if you want to ask questions.
Hi, great talk. I'm Maria from MIT, a postdoc researcher. Have you also looked into how adding or reducing friction can help with some of these in-hand manipulation tasks?
It's an excellent question. No, we have not. Each time that we had to play with friction, we will actually manually change, the tactile sensors or parts like this. I don't know of any material that allows to do that. Maybe you're designing it, but I think it would be fantastic. Yes, so we have thought about it, but we've never explored it. That will make, if we could indeed change at will the friction when you're manipulating, then all of a sudden you could throw an object when you want it because you want low friction at that time, or just suddenly increase it to be able to hold it. Yes, that would be marvelous.
Thank you.
Thank you for the question.
Hi, thank you for the talk. I know you said you haven't done more complex in-hand manipulation tasks yet, but I think, right, with the 6-fingered hand, and especially with the tactile fingers all around, even if you put them on the palm, I don't remember if you did or not, what do you think the possible capabilities would be? Right, because humans, we could grab our phone, do very basic stuff like that, but as you increase that complexity, what do you think would be possible?
I think the possibility are infinite. Infinite, because first of all, we can choose how many fingers we want to have depending on the task. But what I envision is that really we can at will design sub-hands if you want, or will beyond the hands, which is already what the committee is doing when we think of locomotion or multi-body control, and we think of holding an object like this and then crawling by walking. It's the same. This hand is now just a body. It's a body that can do many different things. And what's the next thing that I really would like us to do is to have the hands handing over objects to the other part of the hand, but also flipping them to be able to catch it again. Just explore, all this dexterity that we can do in dynamic manipulation by subgroup. But the real scientific challenge is to design a way in which we could very rapidly allocate those different roles for a given design. What I'm dreaming also of is to work more with people who do soft robotics to potentially at will grow the fingers. When you need a longer finger, like what your colleague was saying, when you need more friction, I would also like to be able to grow a longer finger, or on the contrary, to shrink them in such a way that we can change the body depending on the task.
And as a follow-up, did you try putting tactile sensors on the palm, or is that something that you think would be beneficial?
We have done it on the palm, but the palm at the minute, we have not been able to create a palm that can actually be actuated.
Sure.
So we have tactile sensor in the palm. Unfortunately, the video didn't play, but the one when we were holding the object and it was slipping from the finger, it was all in the palm, and that's how you could see that there is a distribution of mass which changes. So yes, we have done that. We have also put it on the palm on the other side so that you can sense when you're actually exploring inside. But currently, unfortunately, the palm usually is completely static, so we couldn't do much. But I know that there are a couple of very interesting work that are actually using now hands that are soft and can grip and change their shape to conform with the objects. So there is more that can be done.
Thank you.
Great, thank you. So happy to introduce our next speaker, Lerrel. Lerrel Pinto is Assistant Professor of Computer Science at NYU. He earned his PhD from Abhinav at CMU and did his postdoc at UC Berkeley. He leads the General Purpose Robotics AI Lab, RAIL, where they enable robots to adapt in complex, unstructured environments. He does a lot of robot learning and decision making and a lot of dexterous manipulation. He has many great works. He's won many, many awards, such as TR35, Under 35, NSF Career, etc. Very excited to have you. Thank you.
Thank you. All right, let's see if this works. Okay, so I put this real and real over here because in all the work I'll be showing today, there's no simulation. Everything is trained fully from real data on real robots and also real human data. Okay, so to get started, maybe just as a motivation, since we are also in Atlanta, let's see a video of a person opening a Coke can. Now I think this is a simple task that all of us, or most of us, can do quite easily. But if you think about it, right, you have to first locate the object, grasp the object, put your index finger right under the tab in exactly the right point, apply the right amount of pressure, pull open the tab without spilling anything. Right? This is quite hard, but all of us can do this really easily. Right? Now to give sort of more motivation of why our lab looks into hands and trying to do interesting things with hands, there's a sort of like interesting question of why use hands at all, right? Because having hands is quite expensive. If you look at a human hand, it has like what, 27 bones, so many joints, 100 plus tendons inside it, right? It's like so expensive to maintain a real hand. So like, why even have this? Right? Why not just like a grab, like two-finger gripper? So clearly, from a biological sense, there's clearly some indication that having this high level of dexterity, high number of action space is useful for something. So what is this thing that is actually useful for? I think the thing that is really important is that these hands can do a wide variety of things. You can do something as precise as inserting a thread into a needle and also like hold a saw and apply large amounts of force and pressure exactly the right way. The hardware is the same, right? So when all of us are thinking about, okay, how do we create robots that are as general purpose as possible, you cannot do this purely from algorithmic side of things. You cannot just have two-finger grippers that can do everything. You really need this high level of dexterity from the hardware itself. Okay, so here is another study on the GRASP database. I think as Aude mentioned, there are many things you can do with a hand, from all the way from a power grasp to a precision grasp. There's a lot of study into this showing why a multi-fingered hand is important. Okay, so now let's get into some real research. The first thing I want to talk about is how we can scale up real data collection on hands. When I started my lab, I was like, okay, let me first buy a robot hand. So I bought this Allegro hand, spent a lot of our initial startup money on this hand. And so we're really thoughtful on how we can scale this up while being as efficient with the resources that we have. Okay? So if I want to get data on this hand in the real world, how do I do this? One option is you can use this type of cyber glove-like systems that you wear on your hand. It records the joints of your hand and then transfers it onto the robot hand. Right? The problem with this type of system is that it's quite expensive, and for every human who uses it, you need to do like a self-calibration using the system. Okay. Now, if you go on the complete other side of cheap solutions, you can just use an image. So you can just use video streams of your hand, do hand pose estimation on this, and then transfer the hand pose estimates onto the robot hand. The problem over here is that estimating hand pose from just a single image is quite inaccurate. There are a bunch of issues over here. So it is cheap, but there's it's not as accurate as you may want it to be. Okay, so around this time, this is like 2022, 2023, there was this huge explosion of interest in the virtual reality and headset, the VR headset community. And so we were like, okay, can we lean into this new tech that's been created by these big companies like Meta, Apple, and so on, and use their VR headsets for this? All right, here it is. The cool thing about these VR headsets is that A, they are fairly inexpensive, right? You can buy one now for like about $300 as the Quest ones. And if you notice, there are these like small black dots around it. Those are actually all cameras. So they have multiple cameras, which allows you to get this multi-view geometric sense of your hands when they are placed in front of us. So it means that your hand pose detections are going to be really accurate, which then improves the transfer onto the real robot. Okay, so let me show you what this means. The slide will go ahead. Okay, so here is a user. They're using the holodeck system, which is the one we created in our lab. So you wear the headset. As you move your hand around, in the right hand you see the hand pose estimates from the headset, and then in the middle you see the robot interacting with that object, right? Now, because this is a VR headset, what you can do is you can then transfer what the robot is seeing onto the VR headset that the human is seeing, right? And so you can get this real-time mixed reality interaction while working with the robot. Okay, so with this framework to train robot models now, we just follow the straightforward imitation learning route over here. So for a bunch of tasks, we collect a bunch of data. We also do a comparison with doing a teleoperation with just single image frameworks. And we see that if you use this VR mixed reality framework, you get around a 2x improvement in the speed up at which you're able to show this data. Okay? And then there are some tasks, like the harder tasks, like doing a card sliding. It's actually almost impossible to do it with just a single image hand pose detector. You have to use the sort of 3D hand pose estimates to get this work. Okay, the next piece, okay, training a policy. So just as a quick run through over here, if you're looking at a behavior cloning pipeline, input is observation, output is action. In the middle, there's usually a neural network. In our case, the observations are image observations of the hand. We also have information of depth as well. We sort of choose it optionally. In some cases, we use depth, some cases we don't. The action, in our case, is the fingertip. So you can treat each fingertip as sort of like a end effector. So the XYZ of how we want that, that specific fingertip to move, that's the action space over here. Okay, so with around an hour of data for each task, we train this model, and we're like super excited to try it out. We try it out, it just completely fails. Okay, so this strategy is because the amount of data we have is quite small, it does not actually work that well. So to make this work well, we have to make some amount of algorithmic advancements here. And the key ideas is to do visual self-supervised learning and combine it with these non-parametric architectures. Okay? I won't go into too much detail over here because this is sort of older work, maybe 2022, 2023, we have much better architectures right now. The sort of core principle though is that you still have to pay close attention to your algorithms because the amount of data we have in the real world for these hands is much smaller than the other tasks. Okay, so let me show you a few examples of our train policies. So here is a policy for a planar rotation inside your palm. Okay, so that object is an object for which it saw data during training. And over here, the same policy is now being applied on other different objects. And you'll see that the same policy, even though it did not see those objects, it's able to do this planar palm rotation in there. Okay. So here is sort of the other type of rotation, which is, we can call it object flipping, but it's in the other axis of rotation. Again, it's trained on that cube, and over here, it's the same train policy on new objects. The thing you'll notice is that for each object, it actually does it in slightly different ways. So it's not like it's just running an open loop, like an open loop strategy. Okay, so it's actually closed loop over here. All right, so this is some more examples of rotating a sort of tubular object. The video is playing. Slowly. Okay, so let's see if we can. Okay. So I showed you a bunch of successes. It fails sometimes as well. The main failure modes over here is if the object is sort of very far away from the training object. So either if the object is either too small or too large, the hand often drops the object. Okay, so this whole framework is fully open sourced. The link is over there. So if you have a Meta Quest and you want to try it out, everything is fully open. Now, more recently, what we have done is we have extended this framework to doing both arms and also having a compatibility with other types of end effectors. So you can do it with full hands, you can do it with two-finger grippers as well. So this framework is called OpenTeach, and you can see a bunch of videos where the same framework, you can transfer it onto mobile robots like the stretch robot to multi-fingered hands mounted on arms, and even a bimanual arm setup on the bottom right. And this is again fully open source. And it's not just this work, there are like other works as well. So for example, there's the open television work from Xiaolong's group, which also is able to do this using the Apple headset. So if you have an Apple headset, there's also tools for that. Okay, the next question, is vision enough? In all of these things I showed you right now, the policies are fully vision. It's fully RGB as input. But we know that vision is at least not enough for humans, right? So if you look at human hands, for instance, if you look at what's the density of nerve endings, you'll see this incredibly high density of nerve endings on our fingertips, right? It's around like 200 to 250 per centimeter square, right? And this is both like fast as well as slow neurons, right? So this is quite quite a high amount of effort that our body is spending on having good sensing in our fingers. Okay, so what can this actually do for you? So to get this type of tactile sensing on the hands, we still use the Allegro. And on the Allegro, we use the U-skin sensors, which are on the full palm of the hand. Let me show you what that does if the video loads. Okay, so over here the goal is to pick up this smaller object which is inside a larger object. On the bottom right side, the green dots you're seeing, this is the tactile readings from the U-skin sensor. And you'll see over here how for this behavior, you really need to feel the touch. You really need to feel exactly where the finger is in order to locate this object, put your finger inside, and then be able to pick it up. Okay. So this is now quite a sort of new system in the sense that there's not a lot of data on the tactile side out there, right? So if you're training models or architectures on this type of data, how should you do it? So the first thing we did is once we had this hand, we just collected as much of tactile data as we could. So there's a human who's using the holodex framework, moving this robot around, and just doing a lot of this manipulation stuff. Now, while you saw all those videos of interaction, what we really cared about is the tactile outputs, right? Because this is a thing which we don't have a lot of information or data right now. Okay, so with all of this data, we trained a self-supervised model and then train our policies on top of those models. Again, this framework is fairly standard and straightforward at this point, so I won't go into a lot of details. But here are some of the results of that policy training. So on the left-hand side, it's an object which was in training. So it's again a small object inside a larger object. The goal of the hand is to retrieve this smaller object from the larger object. And then you can sort of directly transfer this policy onto new configurations. And the success rate, it really depends. It depends on how far away the test object is from the training object. If the test object is close by, it works. For example, in the top right, it works quite well. But on some of the other cases, it may not work as well. Okay. Here is another example of bowl and stacking, if the slides play. Okay, so here it's a similar example. There are two bowls stacked on top of each other. You need to retrieve the one on top without picking both of them at the same time. And you can now sort of change what type of objects you have over there on the test side. And you will see that in some cases it works. So on the middle of one, it will work. But on the bottom right, because the inner object is too small, the same policy does not work as well. Okay, so this work is also fully open source, fully out there. If you want to, if you have the Allegro hand with the U-skin sensor, you can also use the data set as well, which is also fully open source. Okay, so all of this is cool. More recently, what we were able to show is something which at least I think was really cool is the use of tools. This. Okay, so here is the same hand. What this hand is able to do is able to pick up a wire cutter and then use this wire cutter to cut a wire. Now, to make this happen, along with using the tactile sensor, you also need to train with real-world data in online setting, right? Because when you just directly do a deployment, it does not work that well. But you have to, like, once you iterate from the data collected in real, you can improve the policy and finally end up with something of this sort. Okay. So I won't go into a lot of detail here, but you can sort of push this algorithms to get higher and higher sort of levels of dexterity. How much time do I have here? All right. So in the 5 minutes I have, I'll quickly go over one last work which we are presenting here at ICRA. There's a sort of interesting question of hands and like going beyond human hands, like as Aude had also mentioned. I think one of the really cool things about human hands is that there's a lot of data of human hands out there, right? So if we are to follow the same strategy as like vision or language, where we train on human data, it does seem like having the form factor of a human hand is advantageous because you can now transfer from human hands onto robot hands, right? So let me show you an example of this line of work from our lab. So we have this new work called Hudor, where what it does is, given a video of a human hand doing a task, so in this case it's opening this music box. So I'll just let the video play out. So given just a single human video of this, with online training on the robot, without any teleop data of the robot, we can train the robot hand to sort of imitate this. Okay? So I want to emphasize that this is not a teleoperation based imitation. It's more like a online RL, like inverse RL style imitation happening over here. Okay, so the way this works is actually quite straightforward. So let's say you have a human video, and let's say the robot is doing something. What we do is, from the visuals of the human and the robot, we extract key points on the object. Okay, so you can see these like rainbow colored key points on the object. So these objects have a correspondence from the human to the robot. So we know that these 2 points are the same point on the object. Okay? So now as the video is playing, we can sort of measure how close the robot is to what the human has been showing it to do. Okay? So as the human is doing their task, we can sort of see how close those points are from the robot and to the human. Okay? And now, from this 2 trajectories of points, we can measure the distances between these 2 trajectories. Okay? And if these 2 trajectories are close by, we give the robot a high reward. If the 2 trajectories are far away, we give it a low reward. Okay, so this is a very straightforward, simple way of giving rewards to the robot when it matches what the human is doing. Okay? And so with just this, you can now train the robot in around an hour to solve this task. Okay, let me show. I think I have to be at exactly this distance to go to the next slide. All right, so we do a bunch of experiments in the paper. We show that if you just do pure teleop-based imitation, it does not work that well, especially if you have a lot of these contacts happening. You need a lot more data to get that working. And then we show that for the reward function, using a trajectory-based reward works a lot better than if you use a pure image-based or a pure sort of like point cloud-based reward. Okay. All right. So we also do another fun experiment where we can change the location of the objects during this online learning phase. And we see, sort of as expected, that if you move the object close to where the starting spot of the object is, it works quite well. But as you go farther and farther away, its performance goes down. Okay, so this work will also be at ICRA this year. So if you are at the poster sessions, feel free to find us, and we'll be happy to chat more about this. Okay, so with that, I will end over here. So all this work is done at a lab in New York. So yeah, they are. I'm just presenting on behalf of them. Okay. So with this, I'll end here and take any questions. Thanks.
Great. Thank you for a great talk. Feel free to come up for questions. There was one online that I'll ask. I'll sort of paraphrase it. There's a lot of different touch sensors out there, and you're learning a specific model for a specific sensor. How would you feel, if GelSight came out and the new version came out and you have to recollect the data? Like, what is do you feel there'll be some representation that'll help you between all the sensors, et cetera?
Yeah, I think dealing with touch sensing is hard because there are different modes of touch sensing. Even if you look at a biological skin sensing, there are different modes of sensing touch, even in sort of humans, right? So I do not know the right answer here. I think we are so early in this exploration that we will invariably have to recollect data. We'll invariably have to redo this process, but that's just the cost of doing research in an early field, I think.
Yeah, it makes sense. I think we struggle with the same thing in our lives.
I have a thank you for your presentation. It's brilliant. I would like to ask about there was a slide comparing the trajectory of the robot and the human being. So first, my question is, how did you label the trajectory? Did you label manually?
Yeah, so the easy way is you can use like a segment anything like model, get the initial segments of that, then find the points, right? So you can do a dense labeling of points inside that. Yeah. Then you can use something like a code tracker, like algorithm to find the correspondence of those points from the human video to the robot video.
I see. My second question is, you want to make the trajectory as similar as possible. May I ask what's the function to define the similarity? Because from my perspective, if you want the two trajectories as identical, it may limit its generality because we can accomplish this task in another trajectory, maybe totally different, but we can still accomplish that.
Yeah, I think this is a good question, right? I think this is a question in imitation learning in general, that what you're shown, it may not be expert behavior, it might be one way of doing it. Right now, we have explored with a bunch of things like optimal transport, using just the last frame, DTW. There's a bunch of things we have tried out. I think in certain scenarios, some things work well. We have seen some of the optimal transport on the last frames working really well. So I would say this is still like a engineering style answer where it really depends on the type of task you're solving.
Okay. My third question is, you kept mentioning about the reward you're using. So did you use the reinforcement learning, something like PPO and PPG, to accomplish your task?
Yeah, we use like a DDPG variant with like n-step TD errors. Yeah, so it's a variant of the DDPG style algorithm.
Okay, but as far as I know, like if you use the reinforcement learning, you must have a lot of data for your task. May I ask how much data did you collect?
So this is around an hour of data collection. So if you imagine an hour and then maybe like at a frequency of 2 hertz or something, that would give you a rough good estimate of the total data here. But I should get back to the paper to get that.
Thank you so much.
We have one quick question, maybe. We have a panel after this, so you can also ask the question to everyone on the panel. Maybe just go quick.
Right. I have just one very quick question. So for Hilda, you used pixel-wise correspondence points, right? So have you tried using like semantic correspondence between like different objects within the same type so that you can generalize?
Great question. Yeah, we are beginning to explore this right now so that we can get the model to transfer across 2 different types of objects, but let's say like 2 different cups, right? So yeah, we are trying this right now.
Cool. Thank you.
Great. Thank you. So we'll have the panel now. Can we have the panelists come up?
Oh, okay, so I'm going to start with a couple of questions. So for now, just relax and enjoy hearing from the panel for a moment. And then we will go to the audience and we'll have some time for your questions shortly. So first of all, let's just thank all of our great panelists one more time. What an amazing set of talks we had this morning. Very thoughtful. So I want to start with this question. So one of the very first things that got me excited with dexterous manipulation was watching in this high-speed video of bicycle repair. And I saw, the bicycle repair person, he's picking up tools and using them like very, very quickly with one hand, while with the other hand, he's holding multiple parts together with his other hand. And I wanted to ask all of you to think about, what do you think, like what big breakthroughs do we need to get there with dexterous hands? It could be hardware, it could be software, it could be all of the above, it could be data collection techniques. I just want to hear from you, what do you think are the big breakthroughs that we need to get to that point? And I think we have a mic that maybe we'll just start from your side.
Yeah, okay, sure. Just before everything, I just want to quickly mention, be very careful about your chair. You're very close to that chair. I couldn't focus on what you were saying. I was too worried. All right, so yeah, that's a very good question. I think for
tasks as complex as repairing a bicycle, there are just too many things that's floating around. One thing I think is particularly challenging, and we are, maybe a lot of us are overlooking it, is that the simulation softwares that we are relying on might not be enough for complex manipulation, especially repairing tasks. For example, if you're tightening a bolt or something like that, that what seems like a rigid body interactions is actually relies on slight deformations on the metal parts or on the screw and bolts. If you don't have that tiny deformation, the screws won't tighten, right? So yeah, simulation, if you rely on simulation, you really need those very subtle deformation available in your simulation system. Otherwise, you'll have to like rely on imitation learning from real world data, and that's something that we really need to work on.
Yeah, so I think we are very, very far away for two reasons. I think on the hardware side, we need tactile for sure, right? Like in this example, I'm sure this person is not looking at their hand for each of this stuff. So I think tactile for sure, softness for sure. I think we are just totally missing this in hardware right now. I think on the algorithmic side, it's very hard for me to think about how we will reach there without a curriculum of easier tasks building up upon them, right? So even just using one tool, right? Just holding a wrench and like using this wrench in the right way, or using a screwdriver in the right way, is like so hard to get right now. Right? So I think on the software side, I feel like on the sort of intelligence side, I think we're very far from building even the lowest primitives of interacting with these objects. That I do not see how we'll get there.
Okay, so my answer maybe is slightly different, or like kind of getting to a different direction. Maybe we don't need any of that to get to the level of dexterity that you want. I think the idea that I have is that I think the original question maybe is really centered from how we can mimic human and reproduce like the same capability from human. But if you think about robots, they actually can change tools. They actually don't need to use the same hand to do all the tasks. So if they can have two changers, they change to different tools, they can actually be faster than human. And then maybe we can get to that point without better hand hardware or better learning algorithms, but maybe a very different way of designing the system. Yeah, so that's one idea.
Yeah, I think it's a very interesting question given what we've seen so far. If you really want to crack a difficult problem, you have to understand the full stack, all the way from the right hardware that allows you to solve these complicated things. I mentioned in my slides that no matter how intelligent your software is, you will always feel the hardware. And that remains a key limitation. And I think that Tactile is certainly one way to think about it. But I also would say that I think simulations are improving rapidly, and we shouldn't discount them. And the example that they provided for the nuts and bolts, I think that can be simulated with very high fidelity these days. Then I think the AI part begins where we still struggle to figure out what is the foundation model that we need to really understand the semantics, the perception side that is still sort of underexplored. We very conveniently use RASNet for standard off-the-shelf architectures, which are designed for recognizing cat and dogs. They're not tailored for robotics needs, so that part has to improve as well. And then there's the last bit, which I think is essential, is the last mile. Once you reach a certain level, how do you improve so that it's more robust and improves over time, which is very underexplored continual learning problem. So I guess I've walked you through all different research problems. I haven't given you a solution, but I feel like, yeah, these are bits from my end. Hold the microphone.
Okay, good. That's learning from all of you. Learning from failure. Yeah, so I will not repeat what has been said. I tend to agree with the first speaker that simulation is still far from what we need in terms of contact control, and actually I always advise my lab to not use simulation for all when it comes to control of force and compliance. We do use it, of course, for kinematic control, but you've seen it in the video that we do. We immediately go to the real platform. Hardware is an issue. Motors, actuators, sensors, it's a trouble to get small hands and small enough for sure. And there is a huge amount of work to be done there, and there is not so much interest. To me, today, most of the interest is mostly on soft robotics, which is fantastic. It's a soft hand, but we need probably a combination of the two, how to combine it sort of product. I would like us to go back more to mathematical foundation of grasping and manipulation. Don't take me wrong, I do tons of machine learning, but we lack mathematical foundation. Kevin is organizing a workshop, so we count on you. And a lot of people.
Okay, great. So a lot of things to think about here. Several of you mentioned hardware, and I want to dig into this a little bit more. Certainly you all have experience with working with different hardware, and no doubt many complaints with it and things that you would like to see better. We see several hands around the room, and a number of people who maybe are working on hands these days. I certainly see quite a bit more explosion in that topic. Yeah, I see one person waving in the back. And so give us your wish list. So I would like everybody to tell us 3 things you would like to see in hand hardware. They don't have to be technically possible, at least maybe 1 or 2 of them should be, but 3 things you would like to see that you think is going to get us better dexterity. So that's my second question. And after this, I'm going to open to the audience, so start thinking about things you would like to hear from our panelists.
Sure, sort of 3 things. I have only one wish, really, is to have commercial tactile sensors that I can easily place everywhere that are stretchable and bendable with high resolution.
Yeah, I think I'll also have that as my wish list, the full tactile skin, so you can understand, in greater detail and very dense tactile feedback, and also the degrees of freedom should basically be very similar to what we have in a human hand, although I think there's an argument to be made about whether we want to follow biology or not, but I think given that we have most of the settings in a human environment where the objects are set up so that they can be manipulated with a human hand, it would be prudent to start with that. And I think force feedback would be also useful. That would be critical for many contact-rich manipulations. So, and bring the price down as much as you can. So that's another wish list.
Okay, my turn. I have one thing I want. I want robustness. I want a hand that don't break. And also, if it breaks, I can fix it. So one of the reasons we really like lip hand is that it's very easy to fix. If some of the finger breaks, I can fix it in the lab. I don't even wait for months to ship it and fix it. So I think that is very important, and especially if you think about today's day and age, there are so many learning works. We want to learn on the hardware directly, and we need the hardware to be robust enough for that learning cycles. Sometimes it doesn't need to be that robust, but it needs to be able to operate for a very long time. And then also, if you look at the industry, parallel wafer is a lot simpler, a lot more robust, therefore it's more often used. And then in comparison, suction wafer is even more robust. So that's why it's used more widely. So my wish list for the dexterous hand is to be more robust.
Yeah, I think on a similar line, so we have been making new hands as well. I think we have one somewhere at the back. I think the biggest, this one there. The sort of biggest issue I think with hands out there is repair. It's repair time, repair cost, and repair expertise. If there's someone who has never worked with hardware before, how much time and how much effort will they take to repair something which is which is broken. Because the hands are going to break. Like these are like, the hardware is clearly so far away, we cannot assume that it's not going to break. Right? And so that's my wish list. Just make it easy for us to repair.
I would like to go back to the tactile part. I think for dexterous hands, we not only need tactile sensors on the front side or the inner side of our hand, we need the full tactile sensors on the entire surface of the hand, including the back, so that we can use more, like, for example, spinning the pen. That's one. Number two, I think full active DOF is definitely very important. At least very close to human morphology and human human hand controllability is important. What's the number three that I thought? I can't remember that. But yeah.
Say repair so people.
Okay, yeah, it had to be easy to repair.
Influence there.
I think the most important, the first thing I think of is the full hand tactile sensing. That's the most important thing that I wish we could get.
Okay, so let's take questions from the audience now.
I can filter one from the internet, or
Sure. Yeah, well, let's start with that.
There's a lot of questions on haptics in general, and is haptics important because of teleoperation and collecting data and for behavior cloning? Or do you think sort of haptics is maybe something that's not super useful and not super important right now for robot learning and other applications?
And by haptics, you mean the tactile sensing?
People are talking about tactile and feedback.
Okay. Yeah, in my opinion, that's very important. Tactile feedback, force feedback, those are all very important. Yeah, that's what I think.
So I think the future is not going to be teleop for hands. I think so I would focus on tactile without worrying about the teleoperation part of it, like without worrying about how to transfer this force onto human. Because I think that is just too much of a complexity right now to solve.
Yeah, I think people can still work on it. I think it's a very valuable direction to work on, but I do feel like it is quite difficult. So I think also through the process of working on UMI, I learned that it's actually quite important for the operator or the demonstrator to have the direct haptic feedback when they are manipulating objects. And that really makes the interface feels more intuitive. So I don't know how many of you actually try VR teleoperation. It's very unintuitive. You need to kind of overshoot your action or something to imagine what this feels like when you're manipulating an object. And I think today's haptic feedback device for teleoperation still needs a lot of work. I think I tried it as well myself. I actually need to also train myself to understand the haptic feedback from those devices. So it's not as intuitive as actually feeling the objects during interaction. So I think there's still a long way to go, but it's definitely very important. Yeah.
I think you can go a long way without tactile and haptic for most of the tasks we do, but certainly for very fine-grained tasks where you have very difficult or intricate manipulation there we need it. But I also feel like you can learn a lot from the internet videos, and for the last mile or so you might need that, but you can go a long way without it, in my opinion.
So surely haptic information for fine manipulation in teleoperation is absolutely needed for certain application. There are more and more applications for instance, in nuclear research to decommission or in space where you don't have vision or it's too slow. So assuming that we have the hardware and we will have all the hardware and the bandwidth and everything will be fine, the hardware component-wise, one thing that hasn't been looked at is what is called a correspondence problem. What the robot could perceive, how do we render that in a way that the human can actually interpret that correctly? It's been done for haptic devices that are only for stock sensors, but when it comes to rendering the entire connectivity that we have on the skin, on the hand, I believe no work has ever been out there. Of course, we don't have the hardware, but this would be the first thing to resolve.
Okay, great. Do we have any? Okay, we have a question over there. I think we're sharing the mic, so if you have a question, I think this is the thing to do. Come up and sit in the front, and we'll get to you.
Hi, Ruth. Thanks for the talk. They're really great and very interesting. I was wondering what your thoughts are on success metrics for certain tasks. Like, once we get into longer end-to-end tasks, it's really hard to quantify tasks as just success or failure because it's not descriptive enough. So do you have any thoughts on a quantitative or qualitative success metrics that you can share?
Thank you. That's a very good question. For us, I think if you're talking about evaluation metric on manipulation tasks, I think the golden standard is you evaluate by human. Like if you're working on like very challenging tasks and non-standard or something that's not. If you're working on something that's easy to quantify, for example, moving an object from A place to B place, or placing it into a bin, that's very easy to quantify, right? If you're working on something that's difficult to quantify, for example, make a drawing, or erase something from the whiteboard, for example, the ultimate evaluation metric is simply by how much you accomplish that task, or by human metric. I think I read some paper that what they do is that they split the task into like sequential steps, and you can evaluate on like how many steps are correctly performed, and that sort of gives you a quantitative measure of how good your policy is.
So I may have like a slightly cynical take over here. I think most benchmarks in robotics are broken, especially in the real world. I mean, if you are in research, I mean, I think probably everyone over here knows that no one trusts the numbers in these papers really, because if you reproduce it yourself, it doesn't actually work. I think the true test, the true real test is how well or how easy is it for someone else to use your method, and how easy is it for them to reproduce some level of success on it. So for example, I think the leap hand is a great example where, I mean, I don't know what the numbers are in the paper, but I know that we are able to run it in our lab, right? So I think that's probably where I would nudge people to think more about, like making it easy for others to do.
Okay, so I do feel like we need to think beyond success rates, especially given the discussion about tactile and force feedback. One thing I noticed is that a lot of times when I have algorithm or policy trained with additional sensory modalities, I observe the behavior become more elegant, like become more graceful. It actually, the content is less rough, and the trajectory is more smooth. But I don't know how to reflect it in my evaluation metric. So I don't have a good answer, but I do feel it's a very important question to ask. And I hope that someone can come up with some solution and email me.
Yeah, I don't think there's a clear answer to that. It's a very open-ended question here, but it feels for certain kind of tasks involving pick and place, the evaluation metrics should be pretty straightforward. Cloth folding, for instance, is an interesting example. How do you judge it? You have to have a human sort of look at it and say whether it succeeded or not, or maybe automate that with a VLM or whatever, well, if they have the domain knowledge about that task. I think the third one, which I think LLM folks are also doing, which is crowdsourcing evaluations. Let a human rank it over time and then have the best one bubble up to the surface so you know whether a particular algorithm is doing well or not. Metrics, I think, I don't know the right answer. We seem to always resort to doing Aldo metric, which is not the right metric. Yeah, I don't think there's a clear answer, so I would say crowdsourcing and let a human sort of judge it and build some statistics and metrics out of it would be a good way to think about evaluation.
And very rapidly, to me, I would like to see more of benchmark that actually disturb the system, because I'd like to see the robustness and the ability to recover from failure as part of the task metric, whatever that means.
Thank you. I agree that we really need some sort of benchmark, and just as we are discussing, I think we really need a set of
maybe in simulation, a standardized benchmarking system, so that maybe we have 5, 10 or more tasks, and each task have a set of pre-designed, like well-organized set of metrics that's computable, and that way we can perform a kind of a fair evaluation on how these how models perform. Like these tasks and benchmarks, they don't have to necessarily be like passing these benchmarks don't necessarily mean that they can do well in the real world, but at least we can have a good evaluation or fair evaluation metric on how each model can perform in the simulation system on complex tasks.
I think we're short on time, right?
10 minutes, maybe 5-10 minutes.
Okay. So let's do one thing. I see 3 of you have come up, and so I'm going to give a test to our panelists, and Aude, if you have that's fine. So I'm going to ask you each to give your question, and we're going to have the panelists pass through and address the parts of it that are, that they are most interested in. I feel like this is a way we can kind of be fair and give everybody a chance to be heard. So let's hear the questions, and then we'll go back through the panelists one more time.
Okay, thank you very much. I will try to be very short, but rather to question, I will indicate something which Aude said and nobody noticed. One thing is the sensory motor contingency, which is J. Kate O'Neill from Paris, pioneer. And second is the sensory motor manifolds. And now all these efforts we have heard here is trying to, with hardware simulation and NVIDIA and so on, and data, to try to mimic from the sensory contingency manifold. What they are doing just is trying to achieve the sensory motor manifolds, which are, for example, the Klein manifold, or Study manifold, or Grassmann, or Riemann manifolds. But this doesn't mimic the sensory contingency manifolds. So we have to address this. How we, with this hardware, with all those non-unbreakable hands and everything, what we have heard, to come near to this sensory contingency manifold. That's my point. And that's what Aude said, mathematics.
Okay, my question is around generalization for different types of hardware. So there's some tasks where specialized hardware makes sense, but maybe we don't have the data. So I guess my question is, if we want dexterity and mastery of more specialized grippers, not like anthropomorphic hands, do we first need to go through mastering dexterity with anthropomorphic hands to achieve dexterity and mastery with specialized grippers, or can we directly attack mastery and dexterity with specialized grippers?
Hi, my question is more around commercialization of where we're sitting today in terms of the technology. My context is today we have 4K, 8K videos, right? But we launched 360 or very 2 megapixel cameras initially. I want to understand and have a very simple framework of what is today possible, which can be commercialized at scale. Because right now we're trying to build we're trying to roll the pen. Generally commercialization happens when you can actually solve a problem which is being solved today with multiple humans very frequently. For example, chopping a vegetable or peeling a vegetable. That's been done by so many humans today, every day, right? So I'm just trying to get a sense from you guys, what should I or everybody take back that this is possible today and this is not for commercialization?
Thank you for the presentation. I have a very quick question. So do you think 3D or 4D representation can greatly help the test you have demoed, or just marginally? This is my question. Thank you.
Okay, so just feel free to pick and choose from that, and contribute your last thoughts from the panel. So thank you so much.
All right, that's a lot of questions to remember. I'll try my best. So for commercialization, I think you just have to try out a few tests and see what kind of tests we can do, like robustly and reliably. Because research and commercialization are totally different species. You have to be very, very reliable, especially if you want to cut something. For 3D and 4D representations, I think they are definitely very important. But what we are trying to do, what we are trying to solve right now is that if we can learn something from pure 2D, because that gives you the least, like if you had to plug in a 3D or 4D representation there, then converting from 2D to 3D and 4D are error prone, and so we're trying to avoid that. Yeah, that's.
Yeah, I think maybe the first question I'll try to answer is the specialized grippers versus a general purpose hardware. So I think the central question is, why are we doing this type of research? I think when you look at specialized gripper, the reason to do that type of research is to solve a very, very specific problem, right? So if you're in a Amazon like fulfillment thing, you want to solve something very, very specific, and so that makes a lot of sense. I do not see how that should be tied with a multi-fingered or that sort of a dexterity problem, right? At least the reason I like to work on this multi-fingered hand stuff is like a core intelligence question. It's not as much of solving tasks right now. It also answers the question on the commercialization side. I do not think we are there with a multi-fingered hand to solve like commercial tasks at a high level of performance at a price point that will be meaningful right now. So I think it's very much an open research question where things like math models and things like 4D, 3D representations are all going to be useful things to research and study more.
So I will just focus on answer the last question, the 4D 3D representation. So actually, if you know me, my PhD thesis is about 3D representation, like 3D thing understanding. And then I think during my PhD, like depth sensor is a big enabler that allows me to do a lot of things later, including in robotics, that make it possible. But if you look at today's my presentation, all the policies I train is vision only, that does not have depth, does not explicitly use 3D information. But I do feel like, so I think my today's opinion is that we don't really need to rely on explicit 3D information, like for example, rely on depth camera. However, I think the internal representation that what the system learned should have understanding of 3D or even 4D, like the correspondences. But we don't need to enforce it, because that becomes a constraint or limitation. And then if you think about it, you have camera moving in the 3D space and you're learning how to manipulate objects, and I think it's an implicit requirement that they need to understand 3D. But maybe it's not like a constraint, yeah.
Yeah, I think so. There was, in the last work we showed Dexter RGB, we had an auxiliary loss which was predicting the 3D location of it. So I think there's a way to probe whether your network has learned some representation rather than imposing that it must go through that bottleneck where you have a 3D, 4D representation. The reason being that end-to-end systems works far better. We've seen that with every big breakthrough with machine learning. But you should be able to pull out and extract those representations if you need it for debuggers and sanity checkers. But shouldn't be imposing explicitly. In my opinion, that's my view. Regarding the commercialization, I think most systems today tend to focus more on the industrial tasks, which is basically pick-and-place insertion, bag-and-hold style things, which we do primarily with jaw grippers and hands, although seem like a natural choice as well in certain settings. But I think there's a good case to be made that if there's a special sensor tailor-made for that task, you might not want to change that. The cost of introducing new things is significantly high, unless there's a big return on investment in there. I think your question was about the specialized versus general. I think it is all dependent on the task. I don't think you can a priori set that you have to use a particular sensor. But for most day-to-day activities, if you want to send morphology, then I think it would be best to look for something like anthropomorphic effect, as opposed to industrial settings where you might not need that, at least as of now.
All right, so let's really thank our panelists. Oh, did you have one more thing you want to? Okay. Let's thank our panelists one more time for all of their activities and sharing their thoughts. All right, thank you, everybody.
Hello, good afternoon, everyone. Welcome back to our session workshop, and we are honored to have our first speaker here, Professor Oliver Brock, and he's the Alexander von Humboldt Professor of Robotics at the Technical University of Berlin, and he's also an ICRA fellow and was president of the Robotics and Science and System Foundation from 2012 until 2019. And Professor Bruce level the robotics and biology level focus on embodied intelligence, grasping manipulation, soft material robotics, and the application of the algorithm and the concepts from robotics to computational problems in structure, molecular biology. So now the stage is yours. Welcome.
Thank you so much. Thanks. I this morning decided to change my talk in response to the things I saw and heard this morning. So somebody was here on stage and said, gave their talk, and then at the end said, oh, but we're at a robotics conference, so I should show you how this works on a robot. And I don't think that that's what it means to be at a robotics conference, right? I think the whole presentation should be about robotics. So, I don't know, I decided I want to talk a little bit with you about how we should progress as a discipline. Maybe the first thing I would like to point out is that generalization has always, always, always been the objective. Today it feels like people from machine learning feel like they invented the idea of generalization. Right? But this is a quote from the proposal that John McCarthy submitted to organize the 1956 workshop that basically coined the term AI and that is considered to be the beginning of this field. And already there you can read the quote, it's about generalization. So let's just agree that all of us want generalization. And the question is not whether or not, but the question is what's the right way of getting there. And please note, this is an empirical question. Right? We should, as a community, pursue different research approaches. But because it's an empirical question, this requires that we compare different research approaches to each other. And I don't think that that's what we're doing right now. I am convinced that the best manipulation approaches today are not based on learning. In terms of, and I'm saying that based on the functionality they provide and based on how general they are with respect to a long list of generalization criteria. So, if this is true what I'm saying, and I'm founding that based on empirical evidence, then why is it not that in a workshop like this, we're actually rolling up our sleeves and we're comparing learning-based and non-learning-based approaches to see for which type of problem, which of these answers, solutions is the right answer. So, here's one video which is completely learning-free. It's actually sensor-free. Right? There's zero sensing in this video. And I don't know. I mean, I think, compared to things we've seen this morning, this is very comparable until it starts moving around. Right? Now your policy that's palm up is palm down, palm sideways. It doesn't matter anymore. Right? So here's a degree of robustness that I would like to see some machine learning, and there are machine learning approaches that can do this. So where it's possible for us to compare empirically, we've done that. So here you see in the middle plot that compares empirically. The orange baseline is this other machine learning approach. I'm not going to say it because I don't want to bash on people. And the performance factor of improvement that we obtain from our method is in blue. Right? The numbers are factor of improvement. So I don't know. I mean, I would love to elaborate on an empirical comparison. I think that's absolutely essential for us to progress as a field, that we really analyze what method is good for what kind of problem. And in my title, I used the word periodic table And those of you who've known me for a while know that this is one of my favorite examples in science. I think the periodic table of elements is really amazing because it structures the space of anything anybody wants to do in chemistry. For all eternity, whatever a chemist will do will remain compatible with this table. Right? This table doesn't mark the end of chemistry, like all questions are answered now. It marks the beginning of chemistry as a solid science. And so I think that, you know, we have been doing manipulation for several decades now. I think notions like form closure and force closure were promising to be the early kind of components of a periodic table of manipulation. But they have been proven useful as descriptive elements, but not as generative elements, not to generate behavior. So I think we should actually analyze what have we done as a field and what are components that we could say are a periodic table of elements, in the sense that from now on, the successful research in manipulation should comply with it. And I'm not saying I have the answer, just to make that clear. I don't have the answer, but I'm gonna start like this. This is one of the earliest known periodic table of elements by Mendeleev. It was found in some closet at St. Andrews University. And obviously it's wrong, it's partial, it's incomplete, but it is an attempt to do this. So I think we need to be courageous and make incomplete periodic tables of elements so that we can progress as a field. And then in the remaining minutes I have, I'm going to try to very briefly tell you what I think are components, that could be components, right? Could be components of such a table. The manipulation we do is based on this hand. It is highly compliant, and that is by design. The idea is that compliance is a very powerful tool that eliminates many of the problems that we're facing, like the complex contact dynamics, uncertainty, actuation uncertainty, modeling uncertainty, and so on and so forth. Let me show you what I mean. Here the hand is holding a cube. These tags are there so that we can actually get ground truth of what's going on. And Alexander is a PhD student who is pulling with a force sensor into different directions. And by pulling, he's injecting energy into the hand object system. And when he's letting go, this energy is being used to restore the original state. Right? So we have created here, by configuring the hand in this way, in some sense a funnel, right? Some controller that is implicit in the hardware that rejects disturbance and gets back to the original state. Right? This is incredibly powerful. And this, as a bottom level, really helps with much of manipulation. Here's another example. In this example, the only finger that's being actuated is the thumb. And that's why it's interesting to watch what the index finger, which is not actively actuated, is doing. So we're going to actuate for half a second, start, now stop. This is when the actuation finishes. But this entire system continues to release energy to spin the wooden ring between thumb and index finger. And the index finger is moving in perfect coordination to the thumb, without that being controlled explicitly. So the hand is doing this control for us. We don't need to do anything. I think these are observations, and I could go on, but just summarize very briefly what I think the power of using compliance at the lowest level in manipulation, what the power that's provided by this. So here's my initial sketch of a possible periodic table of elements, and I'm going to build it step by step. On the left we have the hand, and it has all this interesting morphological computation built into it. We're going to characterize these as funnels that self-stabilize. And they can be static funnels, they can be funnels that get moved over trajectories. Then we can generalize these funnels by realizing that actually if I hold an object with index finger and thumb, or with 4 fingers and thumb, it's the same kind of opposition space. We can start composing funnels, and finally we can do sequencing. We can do good old-fashioned simple planning, and I'm claiming these elements are enough to hopefully eventually solve all manipulation problems. Right? If it's a periodic table of elements, and we don't know if it is, but if it were, then that should be true, right? That really allows us to do this. Okay, so we have the hand, we've abstracted the thing. Let me show you. Here are some motions of different objects. You see pure motions, if you want, along X, along Y, along Z, and then rotation, roll, pitch, yaw. Right? So we can perform these motions on objects. And this provides a level of abstraction that completely hides above that level what the hand is doing. The hand is doing the thing that we ask it to do, and we can simply command the hand by asking that the object move along X, rotate around yaw, whatever, right? So we very quickly get rid of the complexity of the hand and are only starting to deal with the object itself. So here's another example. Focus on the middle. There's no object in the hand, but this is the strategy that is being executed. You see again, the index finger, the middle finger, sorry, is not actuated, it's passive. But now if you look at all the different objects around it, they're all executing the exact same policy. But they're very different objects. And you can see how for all of them, the middle finger is performing an orchestrated, coordinated motion for free. We didn't have to pick that, it just happens. Right? So this shows that this controller that abstracts from the complexity of the hand to just commanding the motion of the object generalizes to all of these different objects. And by the way, these objects are relatively different. I should say, in all of these videos, there's a tag, enable tag on the objects, not because we're using that for control. This is still completely sensorless control, just open loop. But we're using it to get ground truth, so I can give you plots like this. So here you have, from the previous slide, the trajectories along X, Y, Z, roll, pitch, yaw, for the different objects. The different colors are the different objects along time. And you can see that this abstraction from the complexity of the hand to just the raw coordinate frame of the object works relatively well. Right? We commanded a yaw, and a yaw is what's happening. So we have this abstraction now where we can create funnels that leverage the properties of the hardware at the level of commanding the object motion. Okay, opposition spaces is a level of abstraction on top of it. I'm not going to go into that much detail because I'm going to run out of time, but the idea is that in some sense these three graphs should be identical, right? They have the same opposition space. We can call in figure 6 the 4 fingers, we can call them a virtual finger and be done with it, right? This is the same thing down here. We create virtual fingers to abstract particular configurations of the hand. This allows us to adjust the same controller to different object sizes, right? Because a small object you might grasp like this, a big object you might grasp like this. And again, this is an abstraction that we introduce that simplifies it. Actually, I'm not going to talk about how we compose things, but the idea is that we can compose several of these to make them more robust. That's kind of a very simple idea. I'm not going to show how that works. Now it gets interesting, right? Because now we have this idea that we can command, in some sense, an independent motion of the object to be manipulated without having to regard very much what the hand is doing. And this is the precondition for doing planning, right? And it's kind of weird that we can simply do planning. Let me show you how we do it. Here, by the way, is the space that is spanned by this hand. We can generate now, with these primitives, the space that is reachable. Every node in this graph corresponds to a particular hand object configuration. We can simply generate this graph and search it. On the left is a simpler graph that corresponds to the, let me say, traditional RBO hand 3. And on the right, we added a second thumb to the RBO hand 3. It looks freaky, but it turns out it makes it so much more powerful. If you can, you should try to grow a second thumb. It's very helpful. But you see that the graph is much, much bigger as a result. But this is actually not the space that we plan in. The space that we plan in is super simple. It's just the primitives that we have are the nodes and their edges between them. So I don't even need to show it. It's a graph with 5 nodes. And within this, we simply can plan. We're at the beginning of this. We haven't really come up with a planner that really generates arbitrary plans. But here's the first plan that we generated. It's actually sequencing 3 different primitives, and it's making them fit into each other so that we actually have rotation here about the radial, the ulnar, the proximal, and the dorsal. No, just 3 of those, of these 4 axes. And again, it's the same skill, and you can see how it generalizes across all of these different objects. So, putting all of this together, we get, I think, highly competent, still sensor-free. We're going to integrate sensors later to make it even more robust. Still sensor-free, in this case only in-hand manipulation, that is very, very robust. I could show you hours of videos of accelerating this skill, slowing it down, changing the object, changing the friction properties. I mean, whatever you can think of, or whatever we could think of, we tried in terms of generalization. And it works. The 2 students who have done this are Alexander König and Adrian Ziele. And I want to close, again, kind of thinking about this proposal for periodic table element of manipulation, right? The idea here is that we started recognizing that the compliance of the hand really solves the hardest problem of manipulation for us. And then we introduced a series of levels of abstractions that led to something that is so abstract that it's usable for good old-fashioned AI planning. It's literally graph search in a graph of 6, 10, 20 nodes. Right? This is not a complexity. There's no learning. There's no sensing. There's no data. There's no CO2 produced. And it is very competent manipulation. So I really think that that is some empirical evidence that these conceptual levels should be something that we consider. By the way, that you can use these as inductive biases if you want to do learning, right? What I'm saying is not a battle between learning and non-learning, right? What I'm saying is we need to analyze the problem to come up with the right inductive biases that allow us to solve the problem no matter what method you pick, right? And so I went step by step to build this up, but if you now want to execute a plan, it actually goes the other way around. If you execute, you take the general plan, and this is not instantiated. It's not instantiated to your object. Yeah, I mean, there's just lots of parameters that are missing. The point is, you can fill in these parameters as you're executing your plan. So I think one of the basic elements methodologically that we should apply here is that we generate general plans that are not instantiated, and that get instantiated at the moment we have the right information. We have the object in our hand. We know how much friction there is. That's the right moment to complete the plan. And so, yeah, I would say that these first 4 levels then get subsumed in this last tile of the execution stack, where the details are being filled in as we run. So, this is not really a proposal for a periodic table of elements. This is a proposal for starting to discuss what the periodic table of elements could be for manipulation. My point to all of you is, I think we've done this for long enough. We have enough excellent work in this field that we could start discussing this rather than where we get the next batch of training data from, right? I think being together here in one room in a workshop, it makes sense to structure our field to try to come up with the right way of doing this. So that would be my appeal in response to the things I heard during the discussions this morning. Thanks.
Great, thanks for your nice talk. So now I see there's one question from our Q&A platform. Could you explain what each node represents and which edge presents? Is the graph just for one particular object, or do you have to make the graph completely for each other?
So this is a graph here where the node represents a particular object hand configuration. So you could call it a grasp if you want, right? So in this notion, in this depiction, a node is a static moment of the manipulation, and the arches are controllers. But this makes it very difficult, right? This is a complicated space. If I showed this to you as the dual, where the nodes are the edges, so to say the controllers, this would be a very simple graph, and what would happen is that the edges are simply transitions. So this is just to show to you that with an additional thumb, we can reach obviously many, many more contact states because we have an additional thumb. That's why the graph is bigger. But the point is, based on our level, on our abstractions, we can now even generate this graph, right? It's not a continuous configuration space anymore. It's a graph of specific equivalence classes of contact points that we can span and search and obtain using the controllers.
Yeah, so hi, Brock, nice to hear. My question is, I think the proposal is very attractive if we can construct such a periodic table. So in your example of the spinning with 2 fingers, you mentioned that could be an element in your proposed incomplete periodic table for robotic manipulation. Can you explain why?
You mean this?
This one. Can you explain why? Why does the index finger not moving producing such a motion?
So you're asking, why do I actuate for half a second and then I stop actuating and this keeps playing out?
Yeah.
Okay. Basically, the whole system, the finger and the object, together with the actuators, is a physical system, right? If I inject energy by inflating some of the chambers, that results in more pressure, say, on the object, right? Because the finger is trying to bend. And now these forces and energy is in some equilibrium that is slowly tending towards a lower energy state. And this is exactly the behavior that you see. Because the finger is physically coupled to the object, when the object rotates, the finger rotates along because there's friction between the finger, right? So it turns out that the idea of hand is a good one. Many configurations of the hand lend themselves to manipulation, right? We didn't plan this. This is a consequence of the way the hand is built.
Yeah, I understand, right? This is all very attractive, but how important do you think to be able to explain this to the level of, say, if I use the level of rigid body kinematics, or if I model this as an Euler Bernoulli beam?
Yes.
How important do you think we explain to that level of detail?
Not at all.
Not at all.
Well, it's almost impossible to do that, right? Because you would have to have highly precise models. You would have to do some very fancy either model approximation or some finite element analysis. The whole point is that you don't need to. Right? I mean, if you write software, right, and then you write one software that does sorting and the other one that does user input output, right? The user input output is not asking for guarantees from the sorting. It just assumes the sorting works. And I'm saying the hand is an active player in our manipulation system. The hand knows how to do certain things. Let the hand help you. And don't ask questions. Right? You're using the hand in the way that the hand is helpful to you. You can ask whether you can model it or not, but in order to build a system that performs fancy, competent, robust general manipulation, you don't need to model everything.
Okay, all right, that's all. Thank you.
Thank you. Thanks for your great answers.
Can I ask one quick question?
Okay, yes, please.
Yeah, thank you. Sorry about the taking your time. So yeah, thank you for the very inspiring talk. My question is, you talk about building a periodic table for manipulation. The periodic table, in my opinion, is very fascinating because it models the whole, all the elements with 2 variables, right? The number of electrons on the outermost level.
Many more, but okay, yeah.
Right, but fundamentally, like the simplest way to understand it, and also the number of layers of electrons. What do you think are the key variables for manipulation?
Very, very, very good question. And I should clarify, right? To me, the periodic table is an analogy.
Right.
I don't think that it will look like this, right?
Of course.
So very good question, right? Because in chemistry, what's complicated are the constituent parts, right? The different atoms. The interactions between them are relatively simple. They're covalent bonds, single, double, triple. They're disulfide bridges, or there's a very small number of simple interactions. In our systems, it's the opposite. I think the components are relatively simple, but the interactions between the components are very complicated. And so therefore, I think the elements, in quotes, in our periodic table need to be things that make these interactions simple, right? That allow us to structure the interactions so that they are simple. And if you look back at the step, that's all what it's about. Every one of these tiles is making the interactions simple and predictable so that in the end, good old-fashioned AI can solve the problem.
Okay, thank you. That's my question.
Thanks.
Thanks again, Professor Brock. And up next, we have Professor Xiaolong Wang, who will be talking about dexterous manipulation with imitation learning and reinforcement learning. He's an assistant professor at UC Santiago. His specific interest lies in learning 3D and dynamics representations from videos and physical robotic interaction data. And these comprehensive representations are unified to facilitate the learning of human-like robot skills with the goal of generalizing the robot to interact effectively with a wide range of objects and environments. And he is the recipient of NSF Career Award, Inter-Rising Star Faculty Award, and Research Awards from Sony, Amazon, Adobe, and Cisco. Please join me in warmly welcome Professor Wang.
Thank you for having me. This talk is about generating the last batch of training data. Especially about human data. So this is actually a paper title. If you worry about the dash can be cited from Google Scholar, we validated it can be. So before talking about collecting human data, I want to talk about where it is coming from. So we basically, I think it's already 1 year ago, have this teleoperation system that basically use Vision Pro to kind of get the human pose and then use it to teleop the robot to do some manipulation. So a very cute thing in here that I like a lot is basically in our teleoperation system, our head can move, the robot head can move along with the human, and then sync what the robot see to the VR system directly. So this is what the student can see actually his own head, the back, because the robot is staring at his head. So this allows us to do some remote teleoperation, for example. So we have a collaborator, a girl who is from MIT that is doing teleoperation with our system from remotely at Boston to control our robots at UCSD, so he can do some of insertion tasks. So by having this egocentric system, basically you are syncing what the robot sees in real time to the teleoperator, and the teleoperator is, the Vision Pro is capturing the hand pose from the teleoperator, and then can convert this into the robot hand and then do this teleoperation. So this means stop. So it's not specifically because it's cool, because this is the, once the model recognizes this, means stopping the system. So we can train autonomous policy from this. And then, so this is actually keep inserting these scans autonomously. And then what I really like actually is basically, is especially what the robots see. So essentially in this imitation learning paradigm, we are actually also training the head action as well. So it's not just hand and arms are moving, but also the heads are moving and having an active vision. And another thing I like about this is basically, I actually worked on a lot of vision before, still working on vision now. So essentially this reminds me a lot of egocentric videos, right? So if you ever work with Epic Chain, Ego 4D and all these videos, you see a lot of these cooking and egocentric videos that are human hands doing things. So this is actually essentially almost the same, but just instead of human hands, we have robot hands now. And then another thing about this egocentric is that we actually conduct experiments like teleoperation doing the tasks like this. And we actually in the lab, we have 3 teleoperation projects going in parallel at that time. So only this system can do this task because apparently capturing, observing from the egocentric view is very important to do this kind of dexterous task. If you're seeing teleoperating from the third-person view, it's really, really hard for the operator to do the task like this. Right, so I give a brief introduction on teleoperation. And then as we are developing the system, I really feel, wearing a vision pro obviously is a lot of pain, right? So it's generally just having human do teleoperation is not that scalable. And then if you really think about, if you go to the very first videos that I show, when the human is teleoperating the robot do things, the human is really doing the same thing, right? It's just the same motion. The robot is also having the same motion. So the human doing things and the robot doing things, they are really just a 3D transformation away. They're really not that different. Another thing is that, again, going back to this egocentric video perspective, it just looks a lot like human egocentric videos. So this really makes us think, can we actually have these 2 points of alignment that actually brings human data into the training pipeline? So that basically leads to our recent work on humanoid policy as human policy, that we try to have a bunch of relatively smaller scale of robot data, and then a lot of human data, and then do training together, right? So this is examples that how human data and robot data can look alike. So below is the human data, and above is the robot data. So it's capturing with the same Vision Pro. One is actually streaming what the robot see into the Vision Pro. The other is just see-through, directly using the cameras from the Vision Pros to capture the video. Right. So in terms of where to get the data, there's certainly a lot of claims that if you have not worked in this field before, in general, also in vision, you will imagine that you want to collect YouTube videos and then using learning from YouTube videos. But surprisingly, actually, there's not that many useful YouTube videos out there, because when people upload videos to YouTube, it's usually just like cat videos, right? It's like funny videos, right? So videos that has most views. It's not boring videos. So that we kind of actually already observed this from 2016. We have a paper called Charade. Basically, it's like Hollywood in homes, that we actually asked Mechanical Turkers to record their home videos and then use that as a new data set for activity recognition. So here is the same. So you don't actually, even a lot of data set out there, it's very hard to find videos that is actually useful for your task, that is aligned with your task. And then another thing is that you kind of need very, not just task-oriented, but also high quality. So actually, if you collect data just from RGB, if you want to do pose estimation on hands, the 2D works well, but the 3D hand pose are still not that working well. Even use run state-of-art hand pose estimator, it's actually kind of, the projection looks very good. So you have 3D hand estimated and then you project to the frames. It looks very good in general. but is it actually doing the right projection? There's always the confusion between the depth and the scale, right? It can be a very large hand and actually just very far away and projecting the image, or it can be a very small hand and actually very close in depth and project to the frame. So that is actually general big problem. With this recent advance in this VR thing, so we actually directly leverage the hand pose estimator from Vision Pro and collect data wearing the Vision Pro. So here are some examples, actually, some tasks that we do that align with the robot tasks we are going to do. So we are able to collect actually 28,000 demonstrations, actually just in 2 weeks, so with a few people. And then the 1,000 demonstrations actually takes a month or two. So it's just much more scalable when the human is doing the task compared to teleoperating the robot to do the task. And essentially, right, the problem is, the key in here is really the high quality of the data that you have, not only just very clear view, but also very good hand pose estimator. So we use Vision Pro to do that. If you have enterprise license, you can have this main camera access. If you don't have enterprise license, you kind of just stick the Z camera on top to record the video. You can still get the pose, but you don't get the vision. So there are different options. Right, so just give you an example of how it looks like. So essentially, so this is what we collect video look like, and then the pose of the hands is very smooth and very accurate over time. So I think what is really important to get the videos with this high quality of data. Okay, now we have this data. How do we do the training? I think the framework we propose is quite interesting in here, as the title shows that we are not going to train a robot policy. We are actually training a human policy. So just take your mind a little bit away from all the robotics. Just think about, now can we actually train a policy on what the human will do, right, in the next frame. So this is essentially what we are doing. We are actually converting the robot demonstrations into human demonstrations first, like the upper part, human teleop, and then get the robot demonstrations. But then actually the robot demonstration is doing some forward kinematics to convert back to the hand pose, a 6D wrist pose and 3D hand pose key points. So it's a little bit silly in some sense, because why don't we actually just use human teleop poses? So if you think about it, this is actually human teleoperation going for inverse kinematics to get the robot demonstrations, and then you do forward kinematics to get you back to human hand poses. So we do find that there's basically some errors when we're doing IK, and then so basically actually building on top of the robot data to do forward kinematics give you try to eliminate this error a little bit. If you do directly human teleoperator poses, the training results are not as good. From the human data perspective, so essentially what we try to do is really align what human do and what robot do all together into the human space, okay? Now this alignment is a little bit challenging in the sense that when we are doing teleoperation, we are all very careful, right? We have the hands, but the hands breaks a lot, so we need to be very careful. And then human also, when human doing things, we are just very fast. So we basically tune some hyperparameters there. We try to slow down and interpolate the human demonstration. So essentially you slow down 4 times around that. So you just interpolate the human videos doing 4 times longer. And then you basically have the same data, human pose doing things. Okay, now we are aligning humans and humanoids. They are all into the same human pose, space. And then we basically train a transformer that takes the current state to predict what is the next action, right? So the state includes, if it is a robot image, then image plus the state, the pose state. If it's a human image, then it becomes the human image plus the the hand state and key points. So the output is going to be what the thing is going to do, humanoids in this hand pose space in the next time frame. And then in training time, you basically can use the for the human data, you can use human data to supervise where the hand pose goes. And then for the robot data, you can convert again the robot actions, the robot pose into the hand pose domain, and then use it to supervise. And in deployment, you basically, once you have this human hand pose, you can do inverse kinematics again. So just pretending now it's not the teleoperator, it is the legwork doing teleoperation, right? So it's a human policy doing the teleoperation. And then the human policy becomes a teleoperator, and then you can convert basically the predicted hand pose to teleop this robot to become actual autonomous policy. So the key is really we are trying to really just align everything, no matter what robot it is, we try to align things into they are all just human, so in the human space. So if you imagine, we also actually collaborate with CMU people in Guaya's lab. So we have another H1. So because our H1 we buy it much earlier, and then we do a lot of modification, and then you can see this H1 and that H1 is the two embodiment. So essentially, to make to make it work on two robots, you really just need different IK. So it still can be the same policy, but it's just becoming project to different robot space. So I think that is actually a very interesting and advantage of aligning things into all becoming human, because it's going back to different robots. It's just different projections. Right. So. The main thing about adding human data is also like the out of distribution part. So essentially, there's a table in here. Sorry, and then what you need to look is just on the very right number. That if you do imitation learning with only robot data, and then you do imitation learning with both human and robot data, so that generalize like unseen objects and unseen locations, it generalizes better. And then here is a very toy experiments that we try on location generalization. So I'm not sure how do I do it. So it's hard. So in each grid, in each 3x3 grid, we construct it as just for easy for evaluation. So we basically has this 3x3 placement of objects. So you have seen some dot cell inside this 3x3 grid. That means that our robot data is only constructed or like in robot demonstration, the objects are only placed in these two cells. Okay, corresponding to the color there is basically yellow and green. So we put a lot of objects in green, less object in yellow. And then if you do ACT imitation learning, you actually find that it generalizes to the pad in the blue in the center, but the yellow pad has much less accuracy. If you train all together with human demonstrations, then it generalizes spatially better. So that's what this means. So here are some results basically showing that it's just really, we are constructing, again, I will think this is a little relative toy example. How much do I have? Okay, so basically only training with robot data is kind of easy to overfit, that you are still picking things on the air. So co-training helps it. And the pad, again, does not necessarily have to be there. It's just when we are doing evaluations, it's much easier to put a pad there to take the counting. And then this is an experiment on just swapping cup, right, from left to right, right to left. So we are actually training robots. Demonstration only contains one background, and then human demonstrations contains a lot of different backgrounds. So then there's basically can combine these together. You can generalize to actually robot executions in different backgrounds. So transferring the diversity of the human demonstrations into the robot execution. And then this is some other grasping. All right, this is across different objects, so you're training on less objects and then testing on more objects, and then again leveraging the human demonstration, the fact that the human demonstration can go to grasp more objects. Here is some proving results, basically just also some location variant experiments. So in general, we are trying to show that when you have scarce, like little robot demonstrations, you combine a lot of human demonstrations with diverse appearance and also diverse locations, diverse objects that can help the robot policy to generalize. So certainly this is not our first attempt. Actually, this goes back to 4 years ago. So this paper is a series paper, but actually we start submitting it in 2020 and go for 2 years of submission to get accepted. So this work is actually doing very similar work that you collect human demonstrations, convert it into 3D space, and then do retargeting, and then you do limitation on the top. I feel like there's a lot of alignment in this work. So I want to talk about this work is because what happens in these 4 years, like what happens, why it's not working that well then and it works better now. So first thing, actually, again, so this is actually in our lab that we try to do data collections in a more clean way. So even if it's very clean, you can see the hand pose and object pose are still not as very good back 3-4 years ago. And computer vision, people generally consider this is too easy, right? So one thing that is different is hand pose is much better now, right? So the video I showed earlier. And then object pose estimation, surprisingly, is still not very good once you have like occlusions and things. But then now we don't bother this anymore. So we're just training not directly from state, but from RGB observations. So that doesn't stop us much now. And then, and basically we have better robot system now, right? So data collections in robots is easier now. So back then we didn't actually train with robot data at all. It's only human demonstrations, and then we do RL on top. So having a little bit more robot data helps a lot. And then finally, we have much better kind of network now that can actually combine human data and robot data. So these are the changes. So a lot of things I would say is not really our contribution, right? So it's more like the community is pushing things forward, that we have better hardware, better network, and better mechanism to do things. In some sense, we are just redoing the things we did 4 years ago, but then better in many ways. So then it kind of works better. So that's kind of my conclusion here. So I'm going to finish soon. So then we have been only talking about real world data, right? So the missing part I have not covered. Maybe in future talk I will do is the simulation part. So we have some works that we are basically training with large simulations, and then we try to do sim-to-real transfer on this simulated data to real robot experiments. So this is some recent work that we have in RSS, and then we're happy to talk about this later as well. So if any questions, please go ahead. Thank you.
Thanks a lot for your great talk. Due to the time, we only have one question time. How can the humanoid data collection approach be extended to robotic hands that are not anthropomorphic?
Right. So I do think that it's kind of important in some sense that why we do humanoid robot is in some sense is actually aligns with the human morphology pretty well. That's actually kind of important, especially actually when we are doing these tasks. For example, to be honest, this thing, a floating hand policy will not directly transfer to real world that with policy with an arm. So this is still very tricky on solving IT there. So actually, we need to train this picking policy with an arm as well. So the alignment there is quite important. If you are collecting, if you think about human demonstrations, actually just also floating hands demonstrations, right? So you get the wrist pose and you get the 60 pose, everything. But imagine that is still just floating hand. So how do you convert this whole floating hand policy that with the robot with an actual arm to do things? So there, the alignment between humans and humanoids are kind of important. Yeah.
Thanks a lot. Now, we will move further to our exciting industry session.
Okay, thank you.
Hello. Hi, I'm Shihan Liu. Next, we're going to move to the exciting industry session. We have 11 talks from 7 industry guests and also 4 startups. So first, we are going to welcome Aria from UK, Advanced Research and Invention Agency. Welcome Jenny from Aria.
Hello, I'll be brief because I feel a bit of a fraud here in the industry session because, as mentioned, I'm not representing industry, I'm representing a UK government funding agency. But we do fund a lot of industrial work. We're quite a new agency. Aria stands for the Advanced Research and Invention Agency. We're loosely modelled on the ARPAs from the US, inspired by their success. And our mandate is to fund science and technological breakthroughs for societal benefit, for the good of everyone. Our model is that we have a number of programme directors, of whom I'm one. Programme directors identify what we call an opportunity space, so that's an area of science and technology which we consider to be important, but currently underserved relative to its importance and ripe for exploitation. My opportunity space is robot hardware. So I came to Aria very excited about what's happening in robotics, but clearly there's a lot of interest in robotics, and a relatively small amount of government funding isn't going to shift the dial on things like humanoids or AI, reinforcement learning, where lots of big players are investing. But hardware felt like an area that was somewhat underserved. So within the general area of hardware, I'm funding work on robot dexterity specifically. So I'll say a little bit about what we're funding. I was very happy in the panel to see the comment come up about what hardware do you think is most important for dexterity. And I think we've pretty much hit everything that was mentioned. So the first thing was tactile sensing, right? I think the request was for tactile sensors that could cover an entire hand all over the surfaces and are bendable and stretchable and work like an electronic skin. We're funding several different approaches to that end, both in academic labs and in various industry startups as well. We're funding a startup that works on stretchable electronics exactly to try and improve that aspect of electronic skinning. And I could talk, I've only got 5 minutes to go on and on. We are, the question of robustness, I think that was absolutely central as well, and we are funding people building manipulators who place a lot of focus on that. I think that's really important. Something that didn't come up in the panel that we're also funding is novel actuators. So I have this belief that electronic motors aren't really necessarily appropriate for robotics, and mainly what people are using because they're there commercially off the shelf available. But what would an actuator look like if you could develop it specifically for robotics? We're funding work in that area as well. And then the other main area that we're funding is to try and co-design robot bodies and their control systems. So we heard a really interesting talk from Oliver about how you can simplify control through the design of the hand. And I would like us to be able to do that in a more principled and planned way. How could we, do we just have to rely on figuring that stuff out, or could we have a large search space where with modern optimization and generative AI techniques, we could try and find places where the particular design of the hardware is greatly going to simplify the control needed to do a particular task. So we're funding work on the kind of mathematical and computing approaches that are needed for that. I must be nearly out of time, so I will stop there, but I'm very happy to answer any questions, either now or later.
Next is Contactile.
I apologize in advance. This is my 3rd expo in 4 weeks, and I've lost my voice, so I sound like a 12-year-old boy. Okay, cool. So my name's Heather. I am one of the co-founders and CEO of Contactile, and our whole reason for being is giving robots a human sense of touch. I think I just disconnected it. There we go. So we are, thank you Aude for the introduction, because basically exactly what Aude said is that it's going to take a lot of technology to build these humanoid, or not humanoid necessarily, dexterous, versatile, generalizable robots that we all dream of. And there are various companies working on various bits and pieces, and our focus is on touch. So we had a very specific kind of motivation for the sensors that we've developed, and that was to solve the conundrum of how do we measure static friction. So when we hold objects in our hands, we rely obviously on there being friction between our skin and the object. And it doesn't matter if we measure all the forces involved, if we can't measure the friction, how slippery that interface is, then it doesn't help us enough to be able to hold that object. So that's our entire reason for being. So our sensors are more than just pressure sensors or 3D force sensors. We actually measure a whole bunch of tactile parameters that are essential if you think about the physics of manipulation. So they measure 3D forces at each sensing element, and then across the array, global 3D force, global 3D torque. We detect slip, and we also measure the coefficient of static friction. On top of that, the sensors are highly customizable, modular, robust, and easy to repair. So this is the sensors in action. If you really want to see or feel to believe, then we have a booth downstairs, booth 921, so you can come and actually touch the sensors yourself. But here they are, so 3D force at each sensing element. Probably should have sped this up. Probably skip ahead. And then globally 3D force and torque. Slip and friction is harder to do in a video, but anyways. So the value of these sensors is really what they can do for manipulators, or rather end effectors. So basically they enable something that we kind of in-house call Goldilocks grip. So not too hard, not too soft, just the right amount of grip force at the right time for no matter what you're picking up. So that force is basically calculated based on the forces and the friction that the sensors are measuring in real time. And so that enables versatile handling and manipulation of any object. So yeah, this is Goldilocks grip in action. I don't know why that's not autoplaying, but obviously 3 different objects, completely different sizes, shapes, and materials. And at each object it grips using just the right amount of force to prevent the object from slipping. And you can also get real-time dynamic reactions where if the object obviously gets heavier during the grasp, it will adjust the grip force accordingly and grip harder. So yeah, that's just a very simple example, but I hope it gets the point across. So we have sensors, grippers, anthropomorphic hands, everything on display at booth 921, or you can come and see a very condensed version of that booth in the back a little bit later. I have questions or not? All right, questions at the end.
We'll be saved to the poster session and the coffee break.
Thank you.
All right, let's thank
So thank you very much. Good afternoon, everyone. Thank you very much to the organizers for having me today. And I'm Francesco Clemente from Prensilia, and Managing Director at Prensilia. So Prensilia is a spin-off company of the Scuola Superiore Sant'Anna University from Pisa. That was funded by researchers of the Robotics Institute working there. And basically what we do is to develop robotic hands. During the years, Prensilia was founded in 2009. We have been developing mainly 2 robot hands. One is called H2 Azzurra, which is to be thought about as an open research platform. I'll tell more about that later. And then the other one is Mia hand, that is let's say newer device that is focusing more on industrial application as well as out of the lab tests and research and development. So when we develop our hands, we basically think of this kind of graph where we basically have functionality on one axis and the cost of owning the device, which is a financial cost, as well as also complexity of having a system, so the difficulty of using it. And this relationship is usually non-linear. sometimes you have a need, and then the complexity starts to get higher and higher because you have to pack more and more functionality inside of your system, let's say. Of course, the position of Disney depends on the boundary conditions that you set, so on the requirements, of the general requirements that you have on hand, so on the final size that you want, the weight of the hand, but in relative terms, basically what we do is trying to be somehow in that sweet spot, so to maximize the functionality and reduce the cost associated with using and having the hands. This allows us basically to have devices that have a limited weight inside, so both our devices are self-contained, all of the mechanical and electronic components are inside of the hand. Then we use a lower number of actuators. This allows us to use larger ones so that this improves the performance system in terms of grip force and speed, and then still allows us to perform the grasps that are used by humans in 80–90% of the activities of the. So by thinking at these general principles, let's say, we developed two devices. One is called H2 Azzurra, which has 11 degrees of freedom and 5 motors inside the palm. Is driven by tendons, so it has an under-actuated transmission that allows the fingers of the hand to adapt to the shape of the object in a, let's say, mechanically intelligent way, and is also instrumented with tendon tension sensors and fingertip force sensors. And this has to be taught as an open platform, so you can basically take out the sensors that are in the hand and put your own sensors directly connect to the controller of the hand in order to integrate your solutions in the device and not to have external components that may be bulky and not very reliable, let's say. On the other side, we more recently developed Mia Hand, which is slightly smaller and lighter, almost 500 grams, and also has less degrees of actuation, so 3 motors. But on the nice part, let's say, we have high performance, so large grip force, up to 50 newtons, and speed, so opening and closing in less than half a second. And the transmission is more reliable than the previous one, as it's based on links and rigid gears, and this allows for also easier sim-to-real transfer. Also, it has different force sensors embedded in it that we will be showcasing on the back of the room, and it's also ready for integration at different levels, so ROS or Python or whatever you're using now. Yeah, we will be showcasing the hands today in the back of the room, and we also have a booth, and hopefully we see you there. Thank you very much for your time.
Cool. I really liked your talk, Oliver. Thank you. I think too often we get together and everyone talks about what we're doing and the progress we've made, but the whole big picture of why we're doing it is very critical to reunite on. I didn't have time to change my slides, so this is what we're doing. But I'm just gonna talk. I have slides of 5 minutes of videos, and I'm going to blab about it, sometimes about that, sometimes about other stuff. At Sanctuary, we've been focusing very heavily on dexterity and power too, and these are like two very conflicting things, right? So we've got these high dexterity hands that can do complex kinematic manipulations, be very delicate, but then how do we also get the power of the human hand? That whole spectrum from, you know, the delicate touch to the firm grip is something the human hand does better than any other piece of hardware we're aware of. So this is something we worked on. We're using hydraulic actuation to close some of this gap between what the power of the human hand can do and some of the delicate interactions it can do as well. Making progress, not all the way there. And you know, one of the things I note here is, why are we doing this? There's a lot of, like, if we could build something like a human hand, we could do all the things human hand can do, right? Can we build something strong enough, delicate enough, covered in tactile sensing, now incredibly easy to service and really cheap? And we can't do all of these things. So it's really important, back to Oliver's question of, like, what's important and how do we anchor back to that? I don't have answers to that either, just highlighting how critical it is. But yeah, we've made great progress with this system. I'm very proud of the kinds of things we've been able to do. You're seeing some videos doing some interesting manipulations. One of my favorite is this one recently. We've been doing in-hand manipulation, and in this particular task, it was trained in simulation, and we're doing this in-hand rotation task with this 500-gram weight, which doesn't sound like much at all. I remember seeing this, and my first thought was like, so? And then I picked up a 500-gram weight and tried to do it. This is incredibly difficult to do. At about 1 kilogram, it's very difficult, and 2 kilograms, impossible. So great progress, and I think a demonstration of strength and dexterity together. Not as strong as and dexterous as the human hand, but we're getting there. On the other side of that, how can we be incredibly sensitive? So my background, most of you probably know me from Syntech, is in tactile sensing. We've developed some new tactile sensing technology that can also be compliant, very, very, very critical to performance, and sensitive. This is a difficult thing to do. Touching a domino and not knocking it over without vision is a difficult task for people to do, and we've developed sensing technologies that can get there. The big focus with our tactile technology is about durability rather than capability. We want to have the compliance so that we can collide with objects and not get to high forces and have that wiggle room to react to that information and not break. And we've gone very simple with how this technology works. Just compliant, durable, doesn't break, top priorities, senses something useful. More B-roll on tactile sensing here. So yes, right now we've got sensing on the fingertips. This is sort of a pretty coarse resolution sensor. You can see about like 7 cells of resolution there. But very, very exquisitely sensitive and something that's kind of easy for us to make and cover the entire hand too. Another thing I want to highlight, none of this is for sale. We're not selling anything at all here. We're actually buying. And it's super critical that we can inspire you guys to develop the next generation of technology that we want to incorporate into this system, right? So getting the alignments of like the things that we're trying to actually solve so that that becomes the next generation of research, new policies, new technologies, get it up to a certain technology level. This is the kind of stuff that we want to put into our system because we do want that human-like dexterity and that general purpose capability. It's phenomenal the range of energies humans can do from, not knocking over a domino to like imagine all the power I can do with like a body check. It's phenomenal. I know no other system that can span that many orders of magnitude and what it's able to do. And the hand's such an incredible thing about it. On touch and embodiment, this is my favorite video. I hope audio works, otherwise you all come listen to my computer. We get these, Rich Walker and I, we did the tactile telerobot forever. You may have seen that, the one that Jeff Bezos operates. The favorite thing to do is for us to take pictures of people feeling the robot for the first time because they all go exactly like this.
Oh my gosh, touch sensors. Yeah, are they working right now?
I can't tell. Oh, yes, they are.
Everyone gets so excited.
That's crazy.
People get so excited, we would take pictures of them. Everyone's face lights up the second they can feel things. So super important for embodiment. Thank you.
Up next is Shadow Robot. And then will be Meta, and we're going to welcome Meta again after that.
So thanks everyone. I'm glad I didn't prepare any slides because after all of us talk, I just throw them out the window. We've been having an internal argument at Shadow for about the last 15 years on how to design robot hands. We got to do a really interesting new design of robot hands a few years ago for Google DeepMind. And if you go down to the exhibition area, you'll see us on stand 113. Please come over and punch the robot hand because it likes that. One of the things we focused on there was a concept that we stole from another area of engineering called high availability. As I said earlier, you're going to break your robot hand, so you want to be able to repair it as quickly as possible once it breaks. So we designed that from the ground up to take a long time to break and then to be very, very quick to fix when it did do so. But we still don't know how to build robot hands. We still don't know what the right methods are, the right algorithms, the right design choices, the right approaches, the right policies to train them. As Oliver says, we have no periodic table, we have no design handbook, and we lack standards, we don't even know how to measure dexterity. In fact, I would wager that if we asked everybody in this room to define dexterity, we'd have about 150 different definitions of dexterity. And for our field, I think that's a real problem. If we can't define it, we can't measure it, we can't evaluate it, we can't test things. So I was going to suggest that we had a panel discussion here where we all got here and the industry people argued about the definition of dexterity, but I'm not going to do that. Instead, I'm going to throw this open as a challenge to all of you. Please, I'm around until the end of Thursday. I'll be doing a tech talk on Thursday morning at 10 o'clock in the exhibition area where I will talk about the design of a robot hand with high sensitivity, at great length. Do come and ask me about that there. But right now, I'm just going to say it would be really, really interesting if we could, as a community, agree on only 2 or 3 definitions of dexterity that were practical, useful, applicable, and measurable in benchmarks that we could scale. Until we do that, I think we're going to be right at that point where if you can't weigh the atoms, you can't line them up on the periodic table yet. So I think that might be the next step for us. Thank you.
All right, it's Meta, and after that it's Robotera.
Yeah, that's really nice. Thanks for inviting me for the presentation. So today I'd like to briefly talk about our recent work on dexterity gen, which we want to really pre-train a large-scale foundation controller for general dexterity. And so when we try to tackle the dexterous manipulation for multi-finger hand, a natural question arises, why we want to do this? A simple answer is that the world are designed for human, like the tools are designed for human hand. Definitely you having a multi-finger hand that's similar to our human hand could do better. But if you think a little bit more, for example, the current task that we're doing, for example, pick, place, and do some in-hand orientation, we can also easily achieve with a parallel gripper with the arm. For example, if I'm just trying to reorientate my phone to another pose, instead of doing a super challenging in-hand reorientation, I can move my arm. If I want to reorientate, rotate the phone, I can also perform this parallel regrasp in order to achieve this task. And seems this slightly easier. But why are we still super interested in those super challenging in-hand dexterous manipulation? I find an interesting perspective is actually coming from human. Why we do this is because we do that. Human naturally perform those tasks because it's so simple for us. I can easily reorientate my hand and reorientate my phone and begin to look at YouTube or Instagram. Well, also when we're trying to learn large-scale robot policy, we really think the data sets matters a lot. We run to train teleoperation, there's like huge data we require, but teleoperation is super hard to get and also super time consuming. So an interesting thing is that human data goes far beyond the scale of teleoperation. So where I think the dexterity really shine over there. And at Meta, we do really interested in dexterous manipulation from all the way from tactile sensing to touch representation to learning dexterous rotation policies and also reconstructing and post estimation. But here today, I really want to talk about this project we are really working on last year that we're trying to go beyond pick and place and really solve the challenging teleoperation or manipulation from human to robot. Imagine if we want to do some human policy learning, we want to do teleoperation because it's simple to get data. But actually for those super challenging dexterous tasks, it's super challenging. If you're trying to tally up a hand to rotate a ball, you could try, but it's almost even impossible. So because there's embodiment gap and when you teleoperate, you don't have any feedback. So our goal is actually to tackle this problem and find a method that can really go beyond that, can really teleoperation, for example, for dexterous task. And so we actually view this as from another perspective. How about we train a large-scale model, just like if we use ChatGPT to refine my email, it's like you give a prompt and it give you a better email that is being written. So similarly, we want teleoperation in the way that you don't directly sending the raw command to the robot, but instead you should have something to refine your action. And that's what we call our project here, DexGen. And at the very beginning, what we do is to have some large-scale pre-train from simulation, where the main task is just grasp-to-grasp transition, where you really want to do it from a large scale. Like for each object, we generate using sampling-based method to generate large-scale grasping data set. And then you're trying to train policies from picking any of those grasps to transit. And so this is done in a really large scale. We collect over 10 billion transitions in total in order to make it really large scale, really foundational. And in the end, after we're having those, we're trying to train some policy, and we do use diffusion. But in the end, we want to go with a teleoperation style, where human or some other policies providing a reference trajectory. And you want your diffusion to either follow this trajectory, but also doing the task better. One particular approach that we've taken is called partial diffusion, which is super popular in image generation. And also there are some approaches in robotics also doing that, where you partially adding noise to your human action and diffuse it back. And another approach that we do is gradient guidance to guide your sampling procedure in order to go to the human action. And in the end, this is what we achieved, and I will just let it play for a while if there are any questions. Show something more. Yeah, so definitely checking our website. There are definitely a few more things. We really want to do it in a generalizable way, and yeah. And if you are interested, please check our website and also the Meta Careers website for joining us.
All right. Our last industry guest speaker from Robotera. And after that, we're going to have 4 startups: Alonic, Fluid Reality, Sensible Robotics, and Zera Robotics. All of them are going to give the talk, give a 1-minute spotlight talk. And here we go.
All right. Great. So great meeting you guys. I'm from Robotera, and my name is Wang. It's my great honor to talk about the X-Hand, which you probably listened this morning by Professor Shuran and so on. And we're going to talk about what we can do for robot learning. Just a little bit of video so that we get the... This is Xiaolong, but actually it's quite smooth and fast. Pinch for the thing and dynamic in-hand manipulation. It's just a teaser. So that's the way we show how we can contribute. And about us, Robotera is founded in 2023 in Beijing. And we are quite famous for this running demo in Gobi Desert, if you see it on YouTube. And later I'm going to introduce our founder, Jian Yichen. And then right now he's an assistant professor in Tsinghua University. And recently we have ICML 2025 spotlight paper and also several finalists in workshop, and he's actually from the classical control groups for the robotics, but right now he's doing more like learning-based research. And for our company, we have a fleet of products. We have actually humanoids, bipedal, platform, and wheeled, and also our X-Hand we're gonna introduce today. Plus, we are shipping out joint modulars as well. What's unique about X-Hand? Okay. First of all, it's full actuation. We have 12 degrees of freedom and we have 12 degrees of control. So there's no under actuation. And also the side sweep degree of freedom of index and thumb fingers. This is the thumb finger and this is the index. And this is the exact location of the degree of freedom. And second is what we call direct drive. So we have a little bit of cheats in this terminology because usually when we say direct drive, there's no reducer between the motor and the payload. But we did put a reducer between the motor and the payload. So the whole size is about the size of a human finger. And what this brings us is the smooth back drivability, as well as the impact resistance. So feel free to drop it, feel free to crack it, feel free to be free of worry. So, well, except for side swing, there's additional transmission. Otherwise, there's no additional transmission for each degree of freedom. There's some basic numbers. I will go very quickly. 12 degree freedom, 15 degree of side swing, and the Kappanji test 6 dots, and payload high. I won't go much in detail, and which is very fast. We are dynamic. It's 10 clicks per second for finger. It's like the professional gamer's speed in clicking. And also sensitive. Our tactile sensor had 27 to 70 degree of contact area, which we'll cover a bit later. So another contribution we're showing to the robot learning community is that we ourselves have been pushing this learning end-to-end model forward. So ERA 42 is our big model for manipulation. And actually it's based on the paper called the Video Prediction Policy, just recently get elected about the ICML Spotlight. You can check it out online. So we show the capability of this hand. These are all autonomous by the prompt. The screwdriver wise, we have additional side view camera right there, which ensures precision. Pipette is really a challenging test where usually Inspire hand cannot do it. So feel free to see how it works. Okay, I'm gonna skip it. So, contribution to limitation learning data efficiency, 3 points, which important is size of a hand. It's the size of a hand, exactly the size of a hand, and the backdropability. And later, what you really care about is tactile sensing. I can play this video very quickly. 3-dimensional tactile sensing at the fingertip. And no more videos. Okay, next one. And this is simulation, which is going on by our collaborator. I won't be able to go to too much details. What's going on right now is working on this. And last, okay, this video, maybe no. Oh, right. What you care about, reliability, DIY, and instant care. Okay, good. Let's skip it. Feel free to jump to our demo session there.
Okay, thank you. We will have the 4 startups. Can you guys line up? We'll have a quick lightning talk. And I'll pull up the slides for each of them.
Okay. So, hey everyone, I'm Benedict, founder of Alonic, and what we're doing is we're building the production technology to make it feasible to create such biomimetic and complex mechanism as that finger over there. What we're doing is building software and hardware, production machinery, that enables you to produce a mechanism like that finger in a single continuous process very quickly and affordably. This is essentially how it looks like. So what we do is we grow the functional tissues over the bones that we pre-produce, which means that we are capable of completing like any kind of 3-dimensional design in this sense in a very strong way, because the fibers wrap around each bone, leaving no weak points for contact, and even the tendon routing can be, and processes like that can be completed during production. So this is essentially the process in video, in a time-lapse video. And the process, what looks like, is that first you produce the scaffolding, then you use our software to design the structure. And that has like a slicing feature inside, which translates your design to patterning. And then you just need to integrate the mechanism. That is an inherently natural, like very safe and compliant bio-inspired realization. So, So the comparison, so this is like how a generic production value chain looks like, but instead of like having hundreds of components, each with different logistics and storage and machining pipelines, instead of that, you only need to produce the bones, and we have the functional layers produced by your braiding tissue mechanism. And then you increase your throughput, reduce production cost to an absolute fraction. And so yeah, please stop by our booth and see the hand in a live demonstration if you're interested. Thank you.
Hello everyone, my name is Joe Mullenbach. Fluid Reality makes a new type of high-resolution haptic feedback technology. This is what it looks like. This actuator is the size of your fingertip. And we're doing this using a brand new actuation technology called electroosmosis. That allows us to create a very large number of pixels covering a large area. Allows us variable shapes and sizes and very thin and flexible actuator arrays. We think this is important to all of you because you can't be dexterous if you have dumb fingers. And we think high resolution touch is the solution. So we've demonstrated this in different types of haptic feedback gloves, including this one, that is essentially pressing shapes into your fingertip to feel edges, contact, etc. Two important things. We are demoing a new glove in partnership with Manus at the OptiTrack booth here. That will be available in very limited quantities later this year. And we're recruiting. So if you work in manipulation, I imagine many of you here do, please send me a video of something cool that you've built at joe@fluidreality.com, and hopefully we can talk during the conference. Thank you.
Hello everyone. Thanks to ICRA and the TABX startup organizers for having us. My name is Brian with Sensible Robotics, and we are a tactile robotics company in Berkeley, California.
Hi, my name is Alex. I'm from Zen Robotics. We make high-density 3D tactile sensors. So each sensing point can measure 3-axis force, so not only pressure, but also the direction of force. At the same time, they are small, 0.1 ground force resolution, fast, and so on. We also integrate them in robot hands and grippers and make the tactile AI software. So for example, here we have integrated 368 3-axis tactile sensors and temperature sensors, so about 1,500 measurements, but they need only 1 or 2 cables to collect all those measurements because all the information is digital. And then we can also grasp fragile objects. So in our booth downstairs, 832, 832, we also show, for example, that we grasp origami. And yeah, we also show a new gripper, so that the thickness is only 6.6 millimeter for 15 sensing points. And in the back, I also have one sensor, so it can measure both on the inside and on the outside, which would be useful, for example, for bin picking. So basically it covers all sides, but at the same time it's only 10 millimeters thick. And we also work on the tactile AI, so for example we can detect slip very fast, and our customers have also used it for slip prediction and so on. And yeah, so our customers use it, for example, cable insertion, EV charging, warehouse automation, so you can detect the object weight, object hardness, then you can adjust the grasping force. You can detect the ripeness of tomatoes. We started the company in August 2018. We already have more than 50 customers worldwide. Some of them are big customers, and currently we have 25 team members. And we are spin-off from Waseda University in Tokyo. Yes, thank you. Booth 832 also if you want afterwards. Thank you.
Thank you for all the industry speakers. Yeah, it'd be great if they have all their booths and everything. We can check them out afterwards and answer questions and stuff. Yeah, how does it go?
Okay, next we are going to have our spotlight session. Okay, we invite our speakers to line up on the right, and each of the spotlight is 3 minutes, and you will see 1 minute timing signs in front of the audience. And we'll start with the paper, Not Twisting Your Arm, and yeah, please come to the stage.
Hi everyone, my name is Vatsal. I want to share with you an interesting hand architecture that we've been working on. And basically the question that we're trying to answer is how we can reorient objects without the need of complex control, sensing, perception, all of these things, right? So we heard earlier today about how we can actually think about manipulation from the object perspective, right? Just want to command roll 20 degrees or pitch 20 degrees or basically just object level commands and how we can do that. And the approach we took was to look at parallel mechanisms, right? There's been decades of work in this area, thinking about parallel mechanisms. And essentially, when you grab an object, you form this kind of parallel mechanism with the object itself. So you have these kind of closed kinematic linkages that are very similar to a parallel mechanism, and you can think about these robot hands based on these kind of parallel mechanisms. And based on this approach, we built the Sphinx hand. So this hand essentially can do spatial rotations of the objects in roll, pitch, and yaw without knowing anything about the object, without any kind of tactile sensing or external perception. We're just kind of doing open loop commands to the hand itself, and just using the inverse kinematics of this parallel mechanism, of this spherical parallel mechanism, in order to do the kind of motions of the object. And the really nice thing about these spherical parallel mechanisms is that you get these revolute joints, and the axes of all these revolute joints are intersecting at a common point. And the really interesting thing about this common point is that it's always fixed with respect to the palm of the hand. So no matter what the object shape is, what its size, if you're moving around, it's always fixed in a particular point. Right? So now basically your wrist axes, if you imagine your wrist of a robot arm, now those axes are all the way up very close to the object itself, and you don't get these kind of parasitic motions that you would typically get when trying to do reorientation with the wrist of a robot arm. You can just do that with the hand. And again, like I mentioned, when we kind of take this parallel mechanisms and we convert them into hand, we have to do some kind of modifications to them. We basically have to think about grasp stability and motion quality, essentially looking at singularities and so on, and how the force transmits through the fingers. But once you take care of all of those things, you can essentially do open loop manipulation. I'm going to show you some of the ways that we have kind of tested out different kind of ways that this hand kind of can do these open loop manipulation. So here we're doing teleoperation in the object space. So the operator is just commanding, again, roll, pitch, yaw motions to the hand, and we can do these kind of untangling tasks. And again, because it's just a parallel mechanism, we can do very automated type of tasks. So here we're just detecting the socket axis using the Ruko tag, but then the hand is just orienting the object or the bulb to that axis and then screwing it in by aligning it to the axis. And you can do this again because the hand is very accurate, just like a parallel mechanism is. So I'll skip the video just for time's sake, but you can come and check out our poster and see the rest of this video as well. And again, because you basically have a wrist-like hand, you don't need to use really complex or really 6 or 7 dot arms. You can use these 4 dot arms. So we're just using the 4 axes on this robot arm, and then doing still the typical type of manipulation tasks that you would do, like pick and place or plug insertion and so on and so forth. So we're really excited about using parallel mechanisms to design robot hands because it allows us to do this kind of open loop manipulation. And if you want to learn more about this, come check out our poster, or you can also scan these QR codes. Thank you.
Good afternoon, everybody. My name is James Wynn. I'm currently a graduate student at Northwestern University Center for Robotics and Biosystems. So today I want to present some recent developments on a biomimetic dexterous manipulator called BIGAI hand. So I'm pretty sure you've gotten this impression by now that there's a need really for a low-cost, affordable dexterity, and which is precisely the goal for this project. I'm designing a highly dexterous manipulator with less than $500 total BOM cost. So you might also be wondering why it's called biomimetic. So this not only because of the fact that it's antagonistically tendon-driven, it's also had to do with a particular linkage design on the tip of each finger. So when you look at the human finger, the most distal joint direction motion on that is somewhat coupled to the one next to it. And on BIGAI's hand, I designed an anti-parallelogram 4-bar linkage, which, when you have the parameters right, can quite faithfully mimic this particular distal versus proximal interphalangeal joint trajectory. And it's got 16 degrees of freedom, and 10 of which are located in this proximal cervical sleeve region connected through PTFE sheath. So this, while increasing the friction by a little, this does make every single finger very, very modular and very easy to service. When you have something in that actually fried, you can very easily just pop it on and place it. And on top of that, because it's using an N configuration tendon routing, it does need to be tendon tension a little, which I designed a very interesting spring-loaded tendon pre-tensioner towards the back of it. Now, moving on to the software part of it, all the control package is developed based on ROS2 control framework, where on the very bottom level, you have some joint level position control, and on top of that, I built also some motion shadowing / teleoperating utility based off that. It can be teleoperated based on VR or using just RGB data input. And this particular demo, I'm actually using a Quest 3S, and I wrote an app for that. And because I integrated a RealSense D405 wrist camera to it, there's also some pretty interesting utilities to that, where you can actually do some pretty interesting drill level calibration just by placing an April tag on that. And the nice thing about it is you don't even need to know the precise the ground truth position for those tags. And because it's got pretty good pretty well posed kinetic chain, you can also solve the numerical IK problem very, very well, very, very fast. So yeah, some quick benchmarking. It achieves all the grasping taxonomy poses, and it reaches 9 out of the 11 Punji score. And it's not great particularly on the force right now, but it can lift a lot. So yeah, in case I didn't mention it, it's a fully open source project where you can find all the CAD and software on this GitHub page if you scan the QR code. And there's also one that's actively under development right now. So yeah, tuning in for some more developments. Thank you.
I'm Wang, presenting our recent work in Northwestern University Center for Robotics and Biosystem, which is about completing hand multi-finger rolling using tactile sensing. So basically, this work in this work we enhance the rover hand dexterity by integrating passive compliance and tactile sensing onto the fingertip. We learned from human manipulation that they play a pretty important role for successful manipulation. So our work is based on our previous work. The first is about compliance sliding regrasp. The second is about developing the VideoFlex, the tactile sensor, which gives us the contact location and contact range information. So this work is about using that VideoFlex tactile sensor and develop object manipulation by using rolling contact, built by 60-finger contact mechanics. So due to the time limit, I will just show the demonstration videos first. So in these videos, we can see we managed to grasp the object and either rotate or screw the object to the command angle. Yeah. So we start with model the contact. So basically trying to understand the kinematics and the contact mechanics of a compliant fingertip rolling on object. Under assumptions such as linear stiffness, small displacement, and quasi-static. So the first problem will be for the contact mechanics. That is given all end finger anchor twist and the current configuration, find the object twist and all end fingertip twists. We managed to find the cross-form solution for that. So the control problem will be the opposite. Given a design object twist, the change of external range and the current configuration, find the optimal joint angle velocity to actuate the robot hand to achieve the object motion. So we developed our control law, which will be the feed-forward term of our control. So based on that, we built our robot experiment system, and then we developed our feedback control loop. And for this experiment, for the rotating and the screwing experiments, these are all the parameters we use. And here we show the results and basically the raw data from our sensor. And for more details, please check our poster. Thank you.
Hello, my name is Anya, and today I'll be talking about RUCA, Rethinking the Design of Humanoid Hands with Learning. So RUCA is an open source tendon-driven hand. It has a cost of $1,300. And as you can see, we do teleoperation. And we can do a lot of other policy learning as well, and just generally some cool tasks. So the kind of initial motivation for this project was that we were working with a lot of hands at our research lab, and we were having a lot of issues with them, and we were mostly working with direct drive hands. So hands like the Allegro and the Leap hand. And this means that there's motors in the joints. And this has a lot of advantages. So the hands are super precise, and you know the exact state of the hand, and this is great for learning. But it has the drawback of these hands are really big. So the usual solution to this is to do a tendon-driven design where, the motors are put into the forearm, and so you have a really compact design, and hands like the shadow hand do this really well. and they're able to maintain really precise manipulation because they have sensors all throughout the hand, and it's really great for dexterous manipulation. But the issue is this can get really expensive really quickly, and people wanting to just start out with hands can't necessarily buy a shadow hand. So how can we design a hand that is precise, compact, and affordable? So we decided that to get compactness, we needed to do a tendon-driven hand, but our hand has no proprioception in the fingers, so how do we have precise control? We use data, specifically data from the Manus motion capture glove. So we put the Manus motion capture glove onto the robot hand, and we do a random walk collecting data of the fingertip positions in 3D space, as well as the motor positions. Using this data, we then can learn a sequential model, taking the fingertip position and outputting a motor position. Using this method, we're able to do a lot of different tasks, and this is all teleoperation videos. If you want to learn more about the specific controller architecture or the robot hardware, how it compares to other hands, you can come visit us at our poster. We also are doing a demo at the ICRA Expo on Wednesday, where if you want to try teleoperating the hand, you can do that there. And if you want more videos, information, code, it's fully open source, so all the CAD files, they're all on our website at this QR code. Thank you.
Okay, then that's the end of afternoon spotlight session. We will come back at 4 p.m. for the next thematic talk as well as the panel discussions.
Invite the speaker station now. We are so happy to have Professor Bicchi here, who will be talking about learning to manipulate and be manipulated. He leads the robotic group at the research center EPFL of the University of Pisa. He is the head of software robotics, lab for human cooperation and rehabilitation at IIT. He is the editor-in-chief of the International Journal of Robotics Research, ICRA. He has been the founding editor-in-chief of the IEEE Robotics and Automation Letters. He has organized the first World Haptic Conference, today the premier conference in the field. And he is the co-founder and the president of the Italian Institute of Robotics and Intelligent Machines. His main research interests are in robotics, haptics, and control system. Now, let's warmly welcome Professor Bicchi.
Thank you very much, Wang, and everybody for enduring the long day and being still here. Yeah, so the title, I tried to find a title that could attract some attention at this time, but it is indeed related. So yesterday I was in a meeting of the Hand Consortium that is, and Kevin Lynch gave a nice talk, and I stole a picture of this presentation. Here it is. The 8S of hands. Hands should be soft, strong, sensorized, lean, sturdy, serviceable, standardized, and suitable. Suitable for what? Suitable for doing fine manipulation, basically. So I think this is very nicely summarizing what we are after. And then also motivates a long story. Hands have been, artificial hands started probably earlier than 1912, but in a survey we found some 170 hands in the last century or so. I must say that today, or these days, last year, many new hands are there. Probably 10 or more percent should be added to this count. So this is impressive. The number of new hands that we see, the number of new tactile sensors that now are professional, while they were only prototypes a short time ago, it's impressive. This is very encouraging. Things are booming again, blooming. But going back, these are a few hands that mark the history. So Jacobson's Utah MIT hand, 1984. Was a hand with 16 joints and 32 actuators. Later on, slightly later on, Salisbury at JPL and then Stanford developed a hand that instead has 9 joints and 12 actuators. And here you see some videotape recording of dexterous operations, including measuring friction coefficients, recognizing object by their texture, finely manipulating, reacting to slippage, tracking a surface that were done back then. One of the problems with those hands, why don't we, why are we still about doing hands today? Well, one of the problems was that they were fragile. There were motor boxes that were connected to the hand through transmission cables. They would break up very often. Not that, as far as I understand from the talks today, not that today that doesn't happen. It does happen a lot. Hardware breaks. But, that's one of the motivations. Another motivation was that it took a long time to first fix them and then program them because of the complexity, the number of degrees of freedom that had to be programmed. And the number of times the hands used to break, or still break, explain why most of the times what we see in planning is rather timid. We consider manipulating on the tip of our fingers and very gently, not to break the hands, I think. This is different from what humans do with hands. We use the hands much more daringly. In all these activities that you see here, we trust the hand and we use the environment and the hand in the environment in a very daring way. So I think grasping is also daring, and rather than just doing on the tip of our fingers, we use the whole hand, and we also use the hand in the environment. We leverage the environment interaction to shape the hand. So in this way of allowing more daring manipulation came soft hands. I think soft hands have been changed in paradigm since some 10, 15 years perhaps, that introduced compliance and robustness to adapt and comply with the environment and be robust there. So here are a few outstanding designs. Some are completely soft, like on the one on the right from Oliver Brock's group, or some are compliant, mechanically compliant. But all of them have this feature of having a deformable structure. And this raises the question of counting the degrees of freedom and the degrees of actuation. So how many degrees of freedom has a soft hand? It depends, but if it's continuously deformable, it really has an infinity of degrees of freedom, because you need an infinity of variables to describe completely the system configuration. In most cases, it's not infinite, but it's a large number. And then I differentiate, like many, with the degrees of actuation. So a controllable variable corresponds to an independent input, an actuator, a model, if you want. So these are two different things. You can imagine an under-actuated mechanism. Our hands are, especially soft hands, are under-actuated. They do not have as many motors as the degrees of freedom. The human hand itself has 19 degrees of freedom, maybe 23 if you count the palm, and 40 plus degrees of actuation. So you have more actuators than actuators are only unidirectional. Muscle can only pull, cannot push. So you really count half by them, and then you are pretty much completely actuated in balance. And the question is, how many degrees of freedom and how many degrees of actuation should an 8S hand have? One inspiration for us has been the work that we have been doing in prosthetics for many years now. And here is the situation that you have in prosthetics. Basically, you have cosmetic hands, then you have the hook, and then you have more and more degrees of freedom. On the right, you have very dexterous hands. Now, you can ask yourself, okay, all those patients that can afford a very dexterous hand will definitely go for the dexterous hand. That's not true. Even people who have both a high dexterity hand and a hook, they tell us that when at home they prefer the hook. Or simpler hands. Why? That's complicated. But the things that they can do with a hook or with very simple hands is incredible, and they do that with less attention requirement than the high dexterity hands, and they are in control. And they use the hand in the environment in a creative way to do things that are really incredible. So we also did a soft hand that is 19 degrees of freedom and 1 degree of actuation, only one motor. We are using bio-like mechanism to design so that we have compliant joints, we have rolling joints, and we have tendons, so you can really do this, which is something that is, as for sturdy, is what we had in mind. The hand can be strong. A soft hand can be sturdy, can also be strong. This is 80 kilograms. The guy is strong himself. And again, sturdy. You can just move it around in the environment. Manuel Catalano here is one of the main designers, is taking advantage of that in ways that you can imagine. So, as far as sturdiness goes, we are there. Again, how many degrees of freedom we need, and how many degrees of actuation. Now, I will distinguish in two, for grasping and for in-hand manipulation. Now, grasping, here is a picture that by itself, I think, answers, we need all 19 degrees of freedom that a hand has for grasping, even for the simplest grasping of capping or uncapping, especially uncapping a jaw. You see that all joints are flexed in this picture, right? So with another hand, I mean, our hand is using all of them independently. Now this doesn't mean that we think really where to put all the joints of the hand. They let them go where they may. In a sense, they will take the shape. So it is this daring manipulation that we do. We have the hand manipulated by the environment. The shape of the hand is dictated by the environment and the task. It's the environment that provides the missing impulse. If we have more degrees of freedom than degrees of actuation, we cannot move all degrees of freedoms, all joints independently. So who controls them? Who provides the control if you don't have the motors? It is the environment. It is our use of the environment that manipulates our hand in the shapes that are functional to the task. So the problem is changed, simpler in the sense of a lower number of actuated degrees of freedom, for instance 1 in our case, more difficult because soft hands are continuously deformable in an infinity of possible shapes through interaction with the object. So if you want to give a soft hand, any soft hand, not just ours, a given shape, you probably have, you can do that if you interact with the environment in the way that will shape the hand in that way. Here is an example here. And again, those missing inputs that are. So here are a few examples. The hand has, again, 1 degree of actuation, but can take the shape of the environment. Here is the human use of a simple hand with only 1 degree of actuation. And you see that by exploiting the environment interaction, something that Oliver and us have been discussing for a long time, right? You can exploit, you can elicit behaviors of the hand that are not at all true. And even kids, here is a kid using the hand for the first time, picking a coin from a table, where she does this, the shape of the hand is, using the table to shape the hand and the object and pick it up. This has been brought in robotics only to a limited extent. Here is an application where the hand can pick a card from a deck in a rather nice way. You couldn't do that if you didn't allow the environment to manipulate your hand. But there are many more things to do, and I've seen very interesting talks this morning and the early afternoon. I think I didn't see yet attention to how you exploit the environment to help you shape your hand. So I'm sort of bringing this to the table. Can we program a robot to use a soft, simple robot hand as effectively as the humans that we have seen can use it? Of course, we're thinking of where exactly placing the fingertips for maximizing grasp measures might be less important, but when you learn something, you have to learn not just the object and the task, you have to learn the object, the hand, the environment, and the task, and how to complete it. So don't be timid, and don't avoid interaction. Reason about them, and use them. Okay, so I think this part I will go very fast because I have little time. This is basically showing that we know what learning is and we are using it. So just a disclaimer. But this is one example of where we are using these manipulation or being manipulated. So it's the story is about finding grasps, whole hand grasps, and we do a rather simple thing, which is we take objects. We divide them up in boxes through an algorithm that is due to Danica Krajic's group. And we generate grasps for the boxes for a catalog of, sorry, this is going ahead by himself. Here, sorry. Oops. What's up? Here it is. Oh, gosh. It showed before, and now it's disappeared. So, okay, don't. Yeah, this is what I wanted to show. Basically, we learn how to manipulate boxes. Right? A catalog of 60 different boxes of different shape and different ratio. And then we apply this grasping to the boxes that subdivide and organize, in some sense, the point cloud of the object. And if you do this, we basically do a decision tree regressor trained to grasp on sample boxes by a human operator, and the model generates candidate grasps for a go from, generates demonstrations, and then we select all grasps according to measures. One is how well the box fits the object. One is how well the force is applied on the object, the wrench that is applied. When we do the demonstration, we measure the forces that are made there. This is work by Wang and Franco Angelini, who are in the room here, and if you have questions, they will be happy to answer. One is used to score the alignment between the gripper and the object, penalizing those that are outside the physical limits. And the final one is the potential collisions of the gripper with the hand itself that are not intentionally there. The grasp selection policy then searches within the physical, kinematical, admissible constraints the best solution. And here is an experimental validation with using our hands, many examples of grasping and using the whole hand and the object itself to constrain the shape of the hand. And not everything is very new, so this is not very new. Our method works better than others. I haven't seen any paper where your method doesn't do better than others. Nice thing is that, hands are not only ours, there are many, many hands. The method works even with a Franca gripper. And here are the demonstrations, and here are the results. Let me go to a closure with how many degrees of freedom when in-hand manipulation. So again, theoretically, I would like to remember this basically. So the minimum number for allowing you to move arbitrarily and a grasped object in space is 9 joints. That's why, because every contact point on the surface has to move arbitrarily in 3D space, assuming that there is no fixed contact. And then 3 by 3 makes 9. And then you at least 9. And that's why Salisbury had 9 joints. That was a very clever analysis at the beginning. But we are starting from the other way. We are starting with soft hands, and we are trying to save on actuators in some sense. So we just say, okay, 1 is good for grasping, 2 might be good for manipulation. And then we have a 2 degree of actuation hands with the same 19 degrees of freedom. And here are the in-hand operations that you can do with this 1 more degree of freedom. Here are some implementation of this in a hand by a spin-off or a group, where you can do, for instance, double object manipulation, which is something that we have seen several times today, or watering the plants and so on and so forth. If I have 1 minute, do I? No? Okay, so I'm closing with this. I'm okay? 1 minute? Okay. So there is much more you can do with soft hands again, and we just scratch the surface. Here is something that a person can do with a 2 degree of freedom hand in terms of manipulation. Now this person is remotely controlling the hand with EMGs. And you see that the same hand can do things that are pretty interesting just because the person considers the hand as his own and controls his hand. His EMGs are reflected into the hand, and the hand does some interesting operations. So I think we have to work more on this. There is a possibility that we have on top of which I hope some people will follow up. Thank you.
Thanks for your great talk. Here has one question from the audience. First, he's fascinating demonstration of the environment shaping the hand, and he's asking, could all the tasks issued also be performed by 1 degree of freedom hand, like open drawer, extract items, and draw a card, like a 2-fingered gripper, or does it need more conformability?
Question is whether the task that we have shown here, could that be done with 2 degrees?
1 degree of
freedom. 1 degree of actuation, I think yes, because we demonstrated them. How many fingers? I think 3 fingers might be good for many things, but for other things 5 are better. And of course, looking like humans is not a religion, but it helps in some cases. The world is made for our hands, so it's easier to design hands for the world than changing the world for our hands. That's a classical answer, I would say. Thank you for the question.
Okay. And then you still have time for 1 more question. Actually, this is from me. And I see soft robotics are really popular, but what do you think, when will the real wave and the time for soft hands come to each lab? We have a bunch of posters and papers submitted to this workshop, but most of them are still the traditional hands, not soft hands.
I don't know if I would like to have soft hands in every lab. I'm fine with soft hands in some labs. What I would like to see is to see hands in the real world. rather than in labs. Labs is okay. We started doing this because we wanted to have hands that could be used in prosthetics. And in that case, I think we had some success. Also wanted to have hands that could go in industry and last more than a few days or weeks. And also there, I think we made some impact. Others have made even more impact. There are soft hands in industry now. I still think it's the way to go. Our hands are soft in the sense that I give it to the term. Right? And there are 8 S's. So I think that's the way to go.
Thanks a lot. Yeah. Professor. Thanks a lot. Now let's move to our last speaker, Professor Josie Hughes. He is an assistant professor at EPFL, where she established the CREATE Lab in the Institute of Mechanical Engineering in 2021. Her research focused on developing novel design paradigms for designing robot structures that exploit their physicality and interactions with the environment. This includes the development of robotic hands, software manipulators, and the automation system for applications focused on sustainability and science. She has a member of Best Paper Awards and was awarded the ICRA IS Early Career Award in 2024. So let's warmly welcome Professor Hughes, please.
Thank you so much for the invite to be here today. It's a real honor to be among such fantastic speakers, so thank you very much. And thank you for bearing through to the end of the day, but we're almost there. So before we want to start, I'm just going to acknowledge the 3 people whose most of the work I'm going to talk about from my lab, Cheng, Kai, and Kieran, and Cheng is here, and please do talk to him. So, in my lab, we build a variety of things, be locomotion, robot hands, lab automation, robots for agricultural systems. But one thing that I'm really interested in and ties these all together is robustness. How can we bring physical robustness to these kind of systems that can operate in unknown or uncertain environments? And the one approach I take to this is embodied intelligence, how we can exploit the environment, how we can exploit the design to achieve this. But focusing more on dexterous manipulation. It's a really exciting time, I think, to be in this area. I think we've had huge advances in the past years, and then more recently we've had this growth in performance from availability of hardware, large AA models. I'm missing a lot of things here, but it's exciting. But I want to be controversial. What is going to happen next? Are we going to hit a bottleneck? This is not sustainable perhaps in the way that we're growing, in the way that we're accelerating in the last year, 2 years. Are we going to hit a complexity in the limited complexity and physical structure of our hands? Is this limiting our ability, as Antonio said, to exploit the environment? Are we also limited in our complexity of sensing and perception to really understand and exploit the environment in an intelligent way? And I want to look at what are these barriers and how do we overcome this potential bottleneck to try and not just come close to human dexterity, but can we go more? Can we show performance that becomes more than that? And for me, this really is about this physical intelligence. How do we learn from biological systems and take this perspective of brain-body environment, exploiting how we design these systems, how these systems exploit the environment to develop more complex and dexterous and robust behaviors. So this approach of embodied intelligence is something that obviously we see a lot in self-robotics, and I think there is a lot we can transfer from this and take into dexterous manipulation. So I'm going to talk about the approaches we're taking in my group to take these principles and apply them for dexterous manipulation. And like many researchers in this field, we start from the human hand. We're looking for bio-inspiration. But one thing we've been particularly looking at, inspired by the work of many of you in the room, from Oliver, for Antonio's work, is distributed stiffness. And if we look at the hand, we have different levels of stiffness, from the skin, for contact, from our fingers to our wrist. And obviously in human hands, we also can have variable stiffness. So we've been looking at the different magnitudes of where it's placed and how it contributes. And we've used this inspiration of distributed stiffness to develop what we're calling our adapt hand. And this is a hand where we can vary the stiffness of the skin by replacing and using different skins. We can tune the stiffness of the finger joints through a series elastic actuation mechanism. And we can use a variable stiffness control of the robot arm. And we've matched this to a human. So we take a human, we do put their hand in an instron, we characterize skin, we characterize joint stiffness, wrist stiffness, so we get a reference point. And from this, we can develop our adapt hand. And we've been looking at what is the emergent behaviors once we exploit the environment. We have to exploit the environment here to really leverage this distributed stiffness. So we've taken exactly the same controller and performing this constrained manipulation task of picking from the surface of this table. And what's really interesting is with the same controller, we can grasp all of these different objects from a very small washer to these big heavy objects. But we get very different grasp types. If we look at the different grasp types, for example, we get with these objects, we can see, depending on certain object geometries, we lead to different grasp types. But what's also quite interesting is the grasp types we get are quite similar to that of a human. So this confusion matrix is looking at the similarity of a human grasp type to that of our distributed stiffness one. And we're hypothesizing that this kind of arises from matching this distributed stiffness. And we've been interested in trying to compute or trying to measure how this compliance helps. Because we always say soft compliance is useful, but can we actually put some numbers on this? Can we try and compute this physical computation that is happening through this compliance? So we've looked at creating this kind of antagonistic setup where we've got one robot introducing noise and error into the placement of these objects. And we can perform long, multi-hour experiments with autonomous grasping. And we can swap objects over. And with this, we're looking at measuring the robustness. So what error with respect to the sentinel or the palm allows the robot still to pick up. And trying to build both a model of this and looking at how our model to our predicted and experimental results matches. But also really running long grasping experiments. So we had a 14-hour experiment here. And I think the other kind of very practical thing that emerges is this compliance really helps just because the hand is physically robust. We can bash it on the table. And this actually is, I think, just a really practical thing that is really important to advancing our robot hands, having the robustness that we're not just breaking, we're not just fixing them all the time. Now, we've heard a lot today about learning, and the key next step is teleoperation. We can use this to gather lots of demonstration data. And so far in this hand, we match the kinematics, we match the stiffness. But we've been trying to look at, if we really want to close the embodiment gap between human and robot, what are the other metrics that we need to do this? And we've been looking at workspace, specifically in the thumb, skin conformity, but also the passive compliance. So with this, we looked at these metrics, and we've looked at what do we need to do next for our hand. One big thing we identified was the skin conformity, having a continuous skin, such when we conform around the object, we have this much better contact, and we have much more stability in grasping. So with this, with trying to better match this embodiment, we've been then looking at how does this improve the dexterity and the extent of intuition by which we can have this teleoperation. So just to show a little bit more detail, this here in the second row here is on our adapt hand 2 with this improved skin conformation with the continuous skin over the surface. We were really amazed at just this simple geometric change to the skin and the effect that could have. So now we have this new version of the hand, which we can perform teleoperation. We can do grasping of single objects. We can do multi-object grasping, if I move it on a little bit. We can pick up 2 cubes in a row using this Apple Vision Pro, as we've seen before. And what we can see is with this improvement, with this conformity, with this improved thumb workspace, we can significantly reduce the time, the execution time for manipulation. So if we look between in the green and the blue, green is our old and blue is our new hand. But if we compare this to human, it's still painfully slow. Painfully slow. But we do also see that in the wrist motion and also the joint space, we get an actuation profile that's perhaps more similar to a human. So, why is this slow? One of the big things we have is we don't have any feedback. Now, there's a lot of fantastic work going on in this, but we've been looking at, could we have shared control with teleoperation? Could we offload some of the control to the robot, and then the human is doing this high-level planning? So we've implemented some very simple sensors just for contact and a rough approximation of force by adding to our series elastic actuation some potentiometers that measure the spring displacement. So now if we have contact, we can detect this with our potentiometer-based sensors. So we have contact sensing. We use this to then trigger on contact force control at the finger level. So now, if we want to hold multiple objects, or if we want to actually have stability, this can be offloaded to the controller. So we've looked at how this increases failure and also makes this teleoperation process a lot more efficient. So first of all, we've looked at, again, the process of picking up 2 boxes, which is hard just with normal teleoperation, and it's even harder when we increase the mass and the weight of these boxes. And what we see with this shared controller is we get a much higher success rate, we reduce our failure rate, so we can make this control a lot more intuitive. So, now we have more intuitive teleoperation, we can move to behavioral cloning, imitation learning. And we're looking at combining high-level planning with the VLA, with low-level dexterous planning with the diffusion model, and looking at how we can leverage this compliance to have stronger environmental exploitation. So one is very practical. It's easier to create demonstrations. We can knock into the table. We can give demonstrations when we're interacting with the environment. This means it's easier to teach examples such as error recovery with this piece of paper. We can also teach policies, we can give demonstrations of manipulation tasks where we're really exploiting this interaction with the environment. So for example, sliding objects across the surface of the paper. And also, this gives us a different modes and options for manipulation. But once again, we want to try and compute, again, what is the role of this compliance in these hands? How is this actually helping? And how can these diffusion models leverage the compliance? So in the version of the hand, we can turn our series elastic actuation on or off. So we have essentially a rigid-ish, because we still have soft plastic in the joints, and we have a compliant mode. And this, we've taken a very simple task, that of turning a knob. And we've chosen this because it requires some dexterity, but also we have a quantitative metric to benchmark the amount we turn. And with this, we've looked at how does the diffusion model perform with compliant and rigid. So one, we're looking at if we change the size of the knob or we interject some noise, how does this affect the amount turned? And we see here with the compliant mechanism, we have much stronger performance. We can also look is if we train the diffusion model with and without this contact information, how does this affect the performance? And we can then, again, see for this particular task what helps. So we really want to try and look at to what extent can these diffusion model policies and others actually exploit the compliance within these hands. Just as a little side note, we're also applying this to other soft arms. So these are some of our soft arms, where we again have some teleoperation. And with these, we really need to exploit the environment, for example, to go through this gap. So on the left, we have training demonstrations. On the right, we then have, again, a learned diffusion model policy trying to enter this gap. So these policies can really exploit compliance. We just need intuitive ways of teaching and giving demonstrations. Now, we can move to bimanual. One approach is we take 2 of these hands and we put them on some arms. But this is painfully complex. This is really difficult. It's a really fragile system. There's lots of things that can go wrong. So Paul, who's also here, has been looking at actually how can we maybe create a more flexible system that's a bit more easy to use, a bit simpler, and that we can actually explore a little bit more some dexterous manipulation policies. But also, can we explore the role of the variable width of shoulder? Because in a fixed bimanual system, we have a very rigid coupling between the 2 arms. And actually, if we're mobile, or we have additional degrees of freedom that we could exploit if we move away from the very closed human paradigm of a fixed shoulder. So with this robot, we can move the 2 arms on cables, so we still have some constraints, but we can optimize the shoulder width for the given task or given object. So Paul here, as you can see, teleoperating the robot, has developed this teleoperating system. We have this 2 arms where you can also have control of the width of the arm. And this allows us to capture data very fluidly, very easily for dexterous tasks, be it harvesting, opening a tape, taking the lid off a pen. But what I think is quite interesting about this is field deployment. This is modular, this is extensible, we can fly it in luggage to Atlanta for the competition, we can take it to the field and we can deploy it to capture data readily and easily. So again, there's something about having a system which is actually deployable, that is not too fragile, that we can actually collect data in a meaningful, scalable way. So, the last point I want to talk about is non-anthropomorphic hand designs. And this takes so much inspiration from the IIT hand, so it's a bit scary going after you. My postdoc Kieran has been working on for a while this open parametric hand. This is a 52 parameter design of hand. So we have different parameters for the joints, the fingers, the morphology of the hand. And we can single print this, and we simply tension the tendons to stabilize these joints. So we have this ability to now have this parametric design and an anatomical tendon routing, and we again use synergy. So we're using one, or if we're really going crazy, two motors here to then operate this hand. But we can explore very different morphologies. We can explore a human hand, a hand with two thumbs, the hand mirrored from an eye. And we really want to look at how does this design space, how does this morphology affect performance. So I'm not going to talk today, but we do a lot of work on the synergies and this actuator box to be able to have and explore synergistically different series elastic approaches to that. But we can see different approaches. For example, our human hand is good at lifting. If we have two thumbs, we can have some really interesting grasp types in terms of interacting with multiple objects. If we mirror an eye hand, we can get some really good kind of grasping performance, for example, for climbing. And we can look at how the low-level finger properties match to the higher emerging grasp level behaviors. So for example, in these different three hands we're exploring, we can look at the stiffness properties of the fingers and the abduction, the hooking in different axes, but also how this matches to the different grasp level behaviors for different objects and the stability. And very interestingly, the two-thumb design really performs quite well and has some really interesting emergent grasp types there. Now with this, we really want to, again, with this very simple 1 degree of actuation, exploring and this ability to rapidly print, explore a really wide design space. And we tried to structure this design space in a way that we think is interesting and allows us to explore different scientific questions. So for example, we can take the approach of looking at primate niches or looking at evolutionary processes. We can look at paleometrics or the role of growth or scaling. Or, looking forward, we can look at generative design approaches or maybe taking more traditional gradient-based optimization approaches. So we've been looking at how we can take our design space and already apply this to optimize some of these morphology-inspired hands. For example, taking indexes, well known from literature of different species with dexterous hands, matching to different human hands for prosthesis applications, leveraging large language models or generative design, or leveraging more typical optimization techniques using metrics, for example, based on the workspace. We're now, though, also looking at, can we make this into a tool for capturing data? Can we move away from teleoperation, like we saw with the Yumi hand right at the beginning today? Can we create a data capture device? Here this has two motors, two buttons with continuous actuation, where we can use this hand to collect training data. So you've got 3 cameras on the hand, and then we can readily deploy this to explore 2 things. How does the morphology affect how this hand can be used for everyday tasks, like making your coffee, opening doors, tidying up the lab in this case? But we can also use it as a data collection mechanism. So looking at it to capture this data of actuation and image to train other diffusion model policies. And here we're looking at single hand, but also bimanual. What happens if we have a human hand and a second one with another morphology? How does that affect our ability to manipulate objects? So, looking forward, I'm really interested in how we can really perhaps overcome this trade-off between dexterity and generalizability. I think we have these real kind of differences in approaches in terms of learning and control. But I think the one key thing is, wherever you are on this Pareto front trade-off, compliance, exploiting the environment is always going to push forward these capabilities, and we need to look at how far we can push this through these approaches. And I think the other thing is, how do we leverage these different approaches and controllers and the learning approaches and maybe have different methods so again we can overcome some of the limitations or challenges of them. So just in terms of future directions, at the moment we're looking at musculoskeletal growing and adaptation systems, these hierarchical control, and again how we can then integrate low-level sensing and control to offload some of the computation. And with that, I just want to thank all the fantastic people in my group whose work I get to talk about, and thank you for listening.
Thanks a lot for your presentation. I got one really kind of funny question, and his question are the hand-based grasping bananas?
Sorry?
So I think maybe in one of the slides for the grasping experiment, and then the hand failed to grasp the banana. He thinks this is the easy case. How does it happen?
I think the banana it can grasp. I think at some point when the banana goes outside the center of the hand, it fails a little bit. But to some extent, it can definitely grasp bananas.
Okay, and then also I see the design of your hand, for this hand, actually instead of a solid palm, you are using actually 4 links instead. So what's the insight here?
So this is also partly on a fabrication limitation, or at least we're starting with in this hand just the open palm. We now also have a parametric skin that goes onto this. So we have a lot of compliance anyway in this structure because we have a lot of passive tendons along with a few actuated ones. But now we also have a parametric skin. So we have the parametric design, parametric skin, and the skin helps a long way. I think there's a lot that we can do with the palm as well.
Okay, and there is one last question from the audience. So for the teleoperation for soft robot hands, and compared to the traditional the other robot hands, for the teleoperation part, are there some difference? Is the method compared to the method?
I think you have this under actuation property that you have to deal with, so it's not a one-to-one mapping if you have a fully actuated hand of joint angle to the under actuated hand. So I think there is a bit of a challenge in how you do that mapping. But again, I think there's so many advantages to have with this, and we don't need all these actuated degrees of freedom.
Yes. Great. Are there more questions?
We have a question here.
Yeah.
I don't know how to get over there. I can
be
loud.
Yeah.
I'll try. Yeah. It was a very good talk. Thank you. I enjoyed it. The last slide, you were contrasting generalizability and dexterity, and it kind of left me a little dumbfounded. Can you explain that a bit more? Because I always thought dexterity is how we get more generalized, but.
I think this is also work in progress, so I'd very much appreciate any feedback and discussions on this as well. So dexterity, I think dexterity within a single task, but then I think generalizability in the task domain. So maybe the complex of, we could be very dexterous at one specific task, but can we have the same policy that can be dexterous over a wider range of tasks? So maybe task generalizability versus dexterity for one specific task. But again, this is work in process. Would appreciate any discussions or thoughts on this.
Thank you for your talk. A lot of fascinating material. I had a question about the design. I think you mentioned that you're using, at least for some designs, using series elastic actuators, and then they're pulling on tendons. And if the tendons are soft, what's the point of this SEA? So I just wanted to get your thoughts on, if the SEAs are not softer than the tendons, are you really getting much benefit out of having SEAs?
Good question. So in the tendons, we have a pretty inextensible, obviously to a point. I would say the softer element is in the plastic. So in terms of stiffness, I think in terms of extensibility, the tendons are probably the least extensible. Then we have the plastic, which then is somewhat elastic, and then we have the SEA. So for sure, the SEA is a lot more compliant than the other order of magnitude, so we see quite an effect from that. But we also have some of the work where we're making it variable stiffness, and there we see the problem is the upper stiffness is not limited by the tendon, but the plastic structure. So we need to rethink that a little bit if we really want to have that length. So I agree completely, the SEA only makes sense if that is the lowest stiffness, but I think for us, it's the PLA structure that's limiting us rather than the tendon.
Thank you.
Really quick one. You mentioned flying it over to Atlanta. Is there a demo?
Yes, in the competition. So Cheng and actually Paul at the back. There's a competition on teleoperation and bimanual things, which is fantastic. Thank you, whoever has organised that. So the teleoperation 2-1 system there. So it's looking at both teleoperation and how you can capture data, but then also training different models of that. So that's in the competition area. I think the actual competition is on Thursday. So watch out for that.
We still have time for one last question.
Thank you for the great presentation. Actually, my question is about the shared control. You said that the shared control can have a better performance, but I didn't saw how do you do the shared control, and how do you share the control between autonomous controller with your human hands, and how to do that? Yes.
Yeah, so I did rush over this very quickly. So we have these contact sensors. So whenever a finger makes contact with the object, then we work out which finger it is and in which direction it's pushing, and then we maintain the force at a constant level for that finger. So the idea is then, because we don't get any haptic feedback, because we haven't got any haptics, that then that's handled. So as soon as each finger makes control, you switch onto that controller.
By using the tactile feedback,
yeah.
do the autonomous control and also the human.
Yeah. Yeah. So then, especially when multi-finger grasping, you can kind of grasp one object, then you forget about those fingers and move to the others. Just without the haptics, it was otherwise very challenging.
Because we also do the shared control and hand calibration and hand design, so maybe sometimes we can discuss with you.
Sounds great. Thank you.
Thanks a lot. And now let's invite all our afternoon speakers and our panel host, Professor Ankur, to the stage. We now will have our panel session.
Howdy. Well, what a great day, focusing on dexterous robotics. Wonderful speakers, so you all introduced yourselves already. I'd like to maybe just get us started with some provocative questions. Take a deep breath. We've been talking extensively about hands, so let's flip it around. If you were a hand, what would be the perfect arm to move your perfect hand? So we've seen different kinds of hands. We know there are intrinsically actuated hands, extrinsically actuated hands, hands with more thumbs than you think might be right. But what's the right arm to deploy these hands? What would you be looking for in a mate if you were a hand?
Not sure I know the optimal, but one thing that we found very important is that the wrist is close to the hand, and the joints are intersecting.
And there are three.
And there are three, of course.
Yes.
Yeah,
right.
That is crucial.
You're right.
If you have the wrist here, you are in trouble.
Okay, so
wherever you want to take, the real world, take something out of a box or do anything, having the motors before the hand is really nasty.
It would be good. So there are really two things. You said final distal link length and 3 intersecting wrist axes. Other things you'd be looking for in the perfect arm for your perfect hand.
So you already know the answer.
I'm not, this is a top of professor.
This is a test. Okay, I see. Yeah, I mean, I agree with Antonio, right? I think that...
What else? What else? We all agree with that.
So for the rest, I don't care.
Really?
Yes. I mean, come on. Ideally, we'd have some free-flying helicopter attached to the hand, right? So the hand could go anywhere.
Very long range of motion.
The arm is in the way.
So how many degrees of freedom does a helicopter have?
6.
Are you sure about that?
Somebody Google it. Somebody asked ChatGPT how many degrees of freedom. Yes, I'm sure about it.
They don't always fly that way, but okay. There are usually some holonomic constraints in a lot of these things. But infinite range of motion is what you like. Big range of motion.
Yeah.
Okay. All right. So what about the range of motion of the wrists? We said there were 3 axes. What would you like in the range of motion? Oh, you went infinite, of course.
Yeah.
But what would you settle for?
Small distance, infinite degrees of wrist, anything.
So the human wrist is very narrow.
Yep.
Right, and it's because of the extrinsic actuation. So it drives you to what? To the apparently drunken shoulder motion, is what you're saying. So
that's how I dance.
Sexy was not one of the S's. So, but if you have a narrow wrist range of motion, and you're doing teleoperation with a dexterous hand, you quickly discover how short your arms are, right? Because you're wanting to do what Oliver did, which is move the shoulder around, right?
At the end of the day, we only care about where the wrist is. So as you say, if we can have our helicopter flying suspended arm, we only want to plan the wrist location and
the 3 degrees of freedom of that wrist.
And then with anything upstream, how can we reduce the complexity of that planning?
Okay. Other thoughts on the perfect arm?
I think we also go past just a tabletop thing. We saw moving robots now. So it's not just about how wrists can move, right? So how the whole robot can move. Yeah. So I think this is something that we are reaching to as well. So it's not just dexterous anymore. It's also body needs to be dexterous. Yeah.
So other than a helicopter, what other very large range of motion robot is there that could move a wrist around? A humanoid, right? A mobile manipulation system, right? And so when you have a narrow wrist, you find you're having to constantly reposition your shoulder to make up for that, right? And so having the ability to move around would be nice. What about strength? How force resolution?
Yeah, I think the thing that I have been searching for recently is also try to find something that is high payload. It seems actually once you have the robot can move around, that kind of constraint that how much payload you can have in the arms and the motors you can use. So that's interesting problem that is actually a little bit contradicted, that if you are more flexible, then you actually might need to reduce the strength. Yeah.
So Kevin, was one of the S's safety?
No.
But if we make it so strong, then we need to worry about safety, of course. So definitely strong enough to move the hand around. What is a high? I think I saw. What was the maximum load you demonstrated a hand picking up? 40 kilograms. Wow, that's a big manipulator. Hold 40 kilograms. All right. Okay, so sensing. What would you like in a manipulator for sensing?
A microphone and a loudspeaker.
Speaker is not a sensor.
It's part of...
Okay, but you want a microphone.
And a loudspeaker.
And a loudspeaker, all right.
So the loudspeaker makes a noise that gets transmitted and modulated, if you want, by the entire system. And in the sound signal you record, everything is encoded. And using the right smart computation, you can extract from one frequency profile a lot of stuff.
How about force and torque sensing in a manipulator?
Yeah, you could do that with the microphone.
Right. What about other ways to do force and torque sensing?
Hold on, I gave you Does my answer not count?
No, it counts.
Yeah, I think this is a nice approach. We have seen really impressive advancements, I would say, with respect to 3 years ago. Now tactile is coming along. It's still sort of like you have to decide where to put it. It's not everywhere. So maybe this is kind of a holistic sensing. Right? I've seen, you might not have got it, but he has this hand where basically he has a speaker and then collects the answer. I've seen something
which is superhuman.
It's
right?
superhuman. It's different from human.
And yes, and in vacuums that doesn't work, but there's something that's equivalent. There have been a bunch of capacitive-based systems that could do proximity to just prior to contact, to be able to sense an object, would be very, very useful.
It works in vacuum because
sonar works in
sound
vacuum.
travels through
in vacuum.
matter, right?
There is also this technology of EIT, electrical inductance tomography. That is very interesting.
And that's superhuman. All right.
I think there's a short term and a long term. I think there's fantastic things with image-based tactile, but honestly, I think the size challenge is that I think if there is a lot we can do if we could just have contact but over a whole finger, having not necessarily huge force resolution, but being able to know, am I making contact or not? Because manipulation all comes down to contact. And if we can have contact over a whole finger, over a whole farm, I think that would give us, in a really reliable way, that would give us a step change. My money is on electrical impedance tomography. I think all of us, though, is very nice. But doing it multimodal and neuromorphic, because then we can have the speed. So EIT, multi-layer, multi-receptor type, and trying to have that in a really scalable way. So we can have a continuous skin with contact in a really reliable, robust way.
So in your presentation, you at one point said something that I think we've all felt. You said so painfully slow compared to human. So if you think about closing that gap, I'm sorry, was speed one of the S's?
Can be now.
Okay. but it shouldn't be slow, right? We don't want slow. Okay, but it was so painfully slow. So think about, and we've been there. What can close that gap to bring it up to human speed? Think about what do you think was holding us back there?
Nothing.
So why is it so painfully slow?
I think exactly what Antonio said. They're not. We're going slow because we're worried about breaking them. We're worried. We put in delays. They need to be more physically robust so we can get that speed. So we can dare to be more. What was the word? I've forgotten.
Sturdy.
Sturdy.
Yes.
Sturdy.
And we're also debugging the systems, right? I mean, you're developing it while you're debugging, so you want to be able to see what goes wrong. And then when it works, you don't spend time speeding it up, you just take it. But in principle, these robots are superhuman fast.
I really don't think that the mechanics are slowing down hands. I mean, Jacobsen hand used to whip cream with a finger.
16 notes.
Yeah.
Right.
And that was with a make a change. And it's the software that is very slow.
So, the example, as you were saying, it was so painfully slow. There was an object on a table, and you're reaching for the object with your robot arm, and an initial contact occurs, and it scoots across the table a little bit. Then you adapt, and then you go in for the kill. What a human does is that incidental contact, it's already there, and we don't have to accidentally shove it.
I think there are some phases of your manipulation that need to be slow if you're making and breaking contact. And then those are also slow in humans. But to give you one example, we had developed an open loop in that manipulation skill. And then just before going home at 2 o'clock in the morning, the students decided, let's try it at twice the speed. And they tried it and it worked. And they repeated that 4 more times, always doubling the speed, and each time it worked. To the point where the skill that was programmed at, I think, 20, 40 seconds, lasted 0.8 seconds. And you didn't see anything anymore, but it still worked. So I really think we can do speed.
So is it that most of these systems are mechanically, they have been slowed down, and people made gearing choices thinking no one would ever go that fast, and so they geared them down. Are we going to get to the point where we will change speed ratios? Because I think mechanically, like Utah MIT hand, most of these are geared slower. When will we start to see that? So back to the arm, how fast would you like an arm to be able to go helicopter fast?
I can deal with a very slow arm because I'm not in a speed race, right? I'm interested in the principle of it. And if I had understood the principle and now I could do everything that I'm interested in, then I would worry about the speed.
And you're chasing an object around on a table at the speed that an object can move around, right? So we're trying to get ahead of it and not let it move faster than you.
I guess, a question what would be a case as a human where you were exploiting more of these dynamics? I think it would be very interesting having more dynamical interactions between an arm and a hand, but are there, in the sense of manipulation, when do we exploit dynamics as a human? Because I think we're very much working in the quasi-static domain, and as Oliver says, that allows us to understand them. I do think that scooping up the table is interesting, but if we go 25-30% faster, we're still probably in the quasi-static regime. So it would be interesting to look at this dynamic.
So the the table world, which a lot of manipulation happens on a table, and it's a planar world, and the dynamics are different in the plane. So what people often do is they make contact out of that plane because they know it's stiff out of that plane to push an object down. We saw in the multi-fingered hand holding an object down on the top of the palm. That's that plane up on top of that hand is another plane. And so pressing down, holding it down, when we're interacting with things on a plane, we know that it's usually stiff in the direction out of plane. So we tend to push on things harder there and then let things slide. But other kinds of sensing, beyond what we've seen today, what other kinds of sensing would you like to see in a robot hand? Do we hear anybody talking vibration today?
Sound is vibration.
Okay. And being able to feel clicks, and when you're doing assembly, being able to feel the high frequency contacts.
Yeah, I would say vibration is number one. I mean, if we have to make a hierarchy of what is important in sensing, like first synergy of sensing, I think vibration is really high. To the point, I mean, again, the experience in prosthetics, the things that people can do with even rigid traditional prosthetics is incredible. They have zero sensors. It's very hard to do anything better than what they can already do, basically by using only the vibrations that come from the tool to the socket, to their receptors, the remaining receptors in the stump. So they do incredible things just because of that. And vibration is definitely number one.
Okay, I think I've annoyed the panel enough. Let's go to the audience, see if you can annoy them more than me. Questions coming in from online. It seems like much of the grasping and manipulation we've seen today focuses on static grasps and manipulation. Even the compliant hands are moving objects slowly, in hand and otherwise. It seems to me that we manipulate things more dynamically. Do we need to close this gap, and how do we?
I think I already answered that, right? I mean, the in-hand manipulation skills that I showed, you can just accelerate them to the point where they're super highly dynamic, and they still work unchanged. It means that the dynamics are not strong enough to overcome the restoration effect that the compliance of a good grasp introduces.
So the forces of the fingers are greater than the acceleration mass.
I mean, it's just a disturbance at that point, right?
Okay. All right, other questions from the audience? We'd like to ask each other questions.
Friendly fire.
All right. Go.
But if somebody else wants to answer,
I think Oliver. I think Oliver makes a good answer to that.
For the audience, you can come directly in front to ask, or then we can.
Okay, here's another one. In what year? Oh, this is good. In what year will a robot make a pizza by exploiting centrifugal force when stretching out the dough?
1984. That I think has already happened.
It's mostly for Oliver. Earlier you made a comment that you could use the sort of like the sonic. I assume you're releasing the sound wave like through the structure of the robot. You could use that like sonic sensing strategy to sense like force at work, and I didn't quite understand to myself like how that would be possible. So I was wondering if you could go into more detail on that.
Sure, happy to. You can also send an email. I'll email you the papers. But the idea is that since we have a compliant hand, any external force will change the shape, the state, physical state of the finger. And so that changes the way sound gets propagated. It's like a guitar to which you attach, I don't know, stickers, or you drill in another wooden board or something like that. Right? That changes the sound of the guitar, and you record that. And if you know how to extract from that recorded frequency spectrum the right state that you're interested in, then you can.
Yeah, you're relying on the stiffness of the deformation of the material itself.
Yeah, well, compressed material resonates differently than uncompressed. Yeah.
Perfect answer for Anthony, because he's a musician. Let's do one more from online. We've had a lot of discussion today about finger dexterity and how they matter for manipulation. In the meantime, there are 8 bones constituting the carpal region with interesting kinematics. Is there a need to explore and examine general carpal palm kinematics?
Yes.
I personally think the palms are underappreciated.
I agree.
So, yes.
Yeah, I had a few slides after the too many that I showed, having a hand with a flexible palm and showing how it can grasp more. Yes.
And maybe again also in this superhuman region, I think there's a lot we could do to also exploit actuation or deformability or morphing of the palm. I think Aude had some example this morning, and so I think, yes, the palm, we don't have to be limited by humans as well. I think there's a lot we can do there.
Yeah, we do think, I think we use this electro hand for a long time, and then the palm is always a problem there. And also, I feel like a lot, going back to tactile sensing, is also on fingertip, but actually when you grasp things, the most of contact is also on the palms and in the finger. So actually, like tactile for palm is not really quite there yet as well.
And yet it's the easiest because it's so broad.
So we just upgraded our hand actually to have superhuman palmar flexibility, and it makes things a lot easier. So this is
palmar flexibility.
Well, so there's degrees of freedom in the palm, and we have actuators in them.
Which axis? What motion? Cupping. Okay.
Yeah.
All right.
Okay.
Yeah.
These.
Metacarpal.
I don't know the chemical terms.
Metacarpals. Yes. Okay. Okay. I think we have one from the floor.
Great talks, and I'm from Robotera. We make X-ray. I just have a question. As a hand manufacturer, it's really important for us to understand, for tactile sensing or for the torque or force sensing, which one you want first, or is it have to be coupled, or have to be combined, or have to be used together, or just tactile is enough?
I don't always want to go first.
So I would say normal force and then shear, but I would say the biggest thing is it needs to be reliable. I think I would rather take something that is simpler, has less information, but has reliability, resilience. We need to be able to have environmental interaction, I think. And so I would much rather have something that we can bash it on the table, that we can really treat it in a really harsh way and exploit those interactions, but have less sensory information for now. But then force and then shear.
Similar, so I think even very simple sensing, we have some works that just have binary sensing over the hands. That's already very useful, and also at the same time, we do also do sim to real, and that's incredibly easy to do sim to real. So I would also have very robust hands and then very simple sensing, actually good for sim to real as well.
All right, I think we've got some from the floor, and I've got one more. Let's go to down there. And we were doing so good. Another question.
Yes, so I work on the side of robotics and manipulation and prosthetics, and something that I don't see very often is I see a lot that robots pick up cups, but they're always empty. So how do we integrate sensors that can tell whether or not there's a liquid in there, and that we're okay, kind of coming back to this robustness, that we're okay with getting
either the prosthetic hand or the robot hand wet? And then also, how can we tell whether this was like a really hot cup of coffee versus just a glass of water?
Well, Oliver's hand will just shake itself dry.
Yeah, I mean, you can shower with the hand, or you could go into a fire because it's heat resistant. Silicone is, I think, 450 degrees or something Celsius.
And flexible down to -90.
Exactly, yeah. So, do it.
So, okay, we go to one online. If you had a physics engine that provided highly accurate contact forces for soft deformable objects, how might you use that for the design of compliant hands?
Definitely, I mean, co-design is a huge area. I think we don't need to be limited to one hand-based morphology for all tasks. So I think physics engines, if we can then use these for design optimization, I think that's very exciting. Coming back to, I think, also the very nice point made about sim-to-real and contact sensing. I think there's a lot of work done with perfect sensors and design optimization or co-design when we assume we have these perfect sensors that can get all this amazing contact information, which is not realistic. So I think if we're going to develop sim-to-real policies, we also need to be very aware of simulating or being aware of the limitations of our sensors and not being unrealistic.
Just add one more. So it's interesting. So we do recently also find if you have these advanced sensors, sometimes differentiable, but then actually training a neural network using these informations to make the neural network as a differentiable sensor somehow is providing better gradients or more stable gradients compared to using the differentiable sensor itself to do some co-design. So I think that is also a very interesting area to study.
Yeah, I agree that co-design is really, really, really important and maybe the ultimate scientific challenge in robotics to really understand how to do that. I think we're very far away from it. And I don't know, I'm not sure that a really highly accurate simulator would help us solve the problem. I know many people are trying, and I know that I'm kind of alone in that opinion, or Josie and I are alone together, if that's possible. But I mean, I think that it's clear that we don't have a simulation that actually matches the world exactly, and I don't think it's inherently possible to do it. Maybe I'll briefly try to sketch the argument.
Well, that's a big statement. You just said you don't think it's inherently possible
yes.
to simulate soft materials.
Well, with the computational paradigms we have available today.
With today's computers, you don't think it's possible?
Yes.
So I will just say, when you watch the ultimate robotics laboratory on Earth, Hollywood, doing CGI, it used to be you could see it was fake because the hair wouldn't blow right, fabrics wouldn't move in the wind. Now we're down to contact. And when you watch contact in the movies, that's where you can still see that it's CGI, not real. And you think that will be for how long?
No. I think humans are much easier to fool than reality. Right? We will believe this is a real simulation.
I want to believe.
But it won't be actually a real, it won't correspond, it won't transfer, right? And yeah, I mean, this is a longer discussion. We only have 1 minute left.
Bring us up, last thought, Oliver.
No. I mean, next year we should meet and discuss, sim-to-real gap versus doing real robotics in the real world. What's the better way? But that's a cliffhanger.
All right, next year.
Okay, all right. So with the last of the awards, I'm going to go ahead and just say some closing comments to close out the workshop. So first of all, I'd like to start with just extending a huge thank you to all of our speakers, moderators, authors, the wonderful audience for taking the time out of your day to come spend time in our workshop today. Our sponsors, Franco Robotics and Agile Robotics, and
Of course, none of this would have been possible without a wonderful group of organizers, as well as a very, very helpful advisory board. So I'd like to extend a special thanks to that team, and we really hope that this workshop helped spark some new ideas, potential collaborations, and new connections. I think to echo Professor Hughes's comment, I hope I'm speaking to the choir here when I say this is a very, very exciting time to be in this field. And I think we're going to see a lot of incredible advancements in dexterous manipulation with multi-fingered hands, especially in the upcoming years. So with that, stay curious, keep pushing the boundaries, and we look forward to seeing all of your continued active engagement in the community. So goodbye, and please enjoy the rest of the conference. Thank you.